this work has been, the work I will talk today is mostly based on this paper, which is done with my student Sharon Moitra, but it will draw liberally from earlier work with my former student Rahana Chakravarti, who is now a postdoc in Dresden, Max Planck Dresden. And these are the two papers that we will kind of draw upon to build the formalism and then go on and talk about it here. So let me start with bipartite entanglement entropy. So what are you trying to do? You are taking, let's say, a big system and dividing it into two parts, which you will call A and B. Okay, these are mutually exclusive spatial regions. And you can then write a generic quantum state of the big system, uh, which has very delicate phase relations. It's of course built out of Hilbert spaces of degrees of freedom which reside in B, also degrees of freedom which reside in A. So I'm thinking of the whole system together. And there is a delicate phase relations between the degrees of freedom in A and degrees of freedom in B in a generic quantum state of the full many-body system. And one way to write this state is to do what is called the Schmidt decomposition. So you can always write a state when you have these two bipartite divisions of the system as sum over alpha, lambda alpha, psi alpha A, tensor product with the psi alpha B, where psi alpha A and psi alpha B are states that reside in the Hilbert space of A and B. Okay. So in general, you do not have a single term here. You have a sum over alpha. And once you have this, you can also look at what is called the reduced density matrix. So you erase the information about the degrees of freedom in B, which means trace over the degrees of freedom in B, and you will end up with a reduced density matrix, which will look like P alpha, psi alpha A, where P alpha is nothing but the mod square of the original Schmidt values. Okay. So this erasing of the quantum information now leads to the appearance of classical probabilities, because this density matrix can be thought of as considering states psi alpha taken in an ensemble with a classical probability P alpha. Okay, so essentially tracing of these delicate phase relations or what you would call quantum information has led to appearance of classical probabilities in your description of the system. And then you can calculate entanglement entropies as entropies of this classical probability distribution. The von Neumann entropy is P alpha log P alpha with a minus sign, which is minus trace of rho A log rho A. And you can define a bunch of Renyi entropies by taking trace of rho to the power n, taking its log and normalizing it properly. And these are again related to P alpha to the power n summed over alpha. So roughly speaking, the entanglement entropy will tell you how much classical information is required to compensate for the loss of delicate phase relations that you are doing by tracing over degrees of freedom in P. Okay. So with that notion, we can ask, okay, why should we calculate this complicated object? By now, this has almost become a paradigm in condensed matter. This, of course, came from quantum computation and quantum information theory, where having entanglement can be treated as a useful resource. And if you have entangled states, you can do certain things in quantum computation which you cannot do otherwise. People have looked at phase transitions by looking at the scaling of entanglement entropy with the size of the system. And the critical states we will come back to towards the end of the talk. They have logarithmic scaling with the size of the system, subsystem. People have tried to detect topological phases with entanglement entropy. And here the idea is that if you look at the scaling of the entanglement entropy with the size of the system, the subdominant order one answer will often have information about the topological degeneracies and so on. And so it has been used to look at topological phases. A large class of systems where it has been used is understanding thermalization. So in principle, in many-body localization, where you are thinking of a strongly disordered state which does not thermalize. And one of the criterion that people find out is whether, for example, the excited states have entropies which are scaling with the subsystem size. If it scales linearly with the subsystem size, then it is most likely that they will end up thermalizing the system. Okay. In fact, Aarti actually talked a little bit about it yesterday. Then there is this whole program of whether you can understand quantum gravity from entanglement entropy. Don't ask me too much about it. I'm not an expert on this. So in general, entanglement entropy has come up as a very useful thing to calculate in quantum many-body systems. How do we calculate entanglement entropy? Actually, so there is a conformal, if you have a conformal field theory, if you are at near a critical point which has conformal symmetries, etc., then you can calculate using the structures that conformal field theory afford you. And this has been old work starting from Wilczek's work in 1994. There have been celebrated works by Calabresi and Cardi in 2004 and 2009. This also resulted in calculating this in some field theories with very complicated boundary conditions. More recently, Krishnendu and Nicolas Dupuy has also looked at some of these issues in a new way. Then there is operators, and for if you go to non-interacting systems, there's this work by Peschel and others, which says that you look at the one particle operators and calculate some correlation matrices, and then from that you can calculate entanglement entropy. The most so varied in some sense is the numerical calculations with increase in computational power. You can diagonalize larger and larger matrices, and I have only listed a few names. This is ... goes on up to very large class of names. For example, in studies of MBL and so on, it's mostly been done using numerical calculations. Okay, so that's the status. And why is it hard, for example, to have analytic approaches if you do not have, let's say, very spatial symmetries and stuff like that? And that comes from this question that you have to first calculate the reduced density matrix, which is a trace over half of the system or the B part of the subsystem. And then you have to square it, and then you have to take a trace. Okay, so trace of powers of the reduced density matrix has problems because when you try to do this, here it's already a matrix, and so when you do row A, for example, you would basically like to have a row A of ij, row A of jk, and this fact that you have to match these boundary conditions doesn't allow you to write it very nicely as, let's say, in field theoretic languages and so on. And in general, hence, it's hard to produce approximation schemes for non-local quantities like entanglement entropies. Okay. So what's our goal? We will develop a new analytic technique for calculating entanglement entropy of non-equilibrium systems. We have done it for bosons and fermions. But today I'll focus mainly on system of fermions today and not talk about what happens with the bosons. Okay, and to do that, we go back and try to look at an old question of Wigner function, which was started by Wigner in 1932, when he was asking to what extent can quantum mechanics be written in terms of classical distribution functions. Both talk about probabilities. Can you write quantum mechanics in terms of classical distribution functions? And the answer that he came up with was, if you have a wave function, you look at the wave function at a slightly different locations, chi star x plus y, x minus y, and then you Fourier transform in the relative coordinates, integrate and do this, and that basically ends up giving you a Wigner function. And why should you look at this complicated function? Because if you are interested in calculating quantum mechanical averages, then you can write this f as f of xipi and times w of xipi, and then actually integrate over the phase space. So in that sense, this is closest approximation to a phase space distribution that you have. Problem? W is not positive definite. Here is a view of W for the ground state of a harmonic oscillator. There, here it is for n equal to 1 state. And you can see here things will be negative. So it's a quasi-probability distribution. It can be negative. And negativity of W is an indication of the non-classicality of the state, in the sense that you cannot obtain this by some effective classical stochastic process. So that was Wigner function in 1932. In between, there has been a lot of development for bosons, I mean, part of which actually ended up going into, let's say, Roy Glauber's work with quantum optics and so on. But today we are interested in fermions. So our question is, can we define something like a Wigner function for a set of fermions? Okay, and this answer was given by Cahill and Glauber in a paper which is slightly less cited than their very celebrated paper on bosons for Wigner functions and things for bosons there. Uh, and the idea is that you need to look at coherent states, and you need to look at displacement operators for fermions. Here, zeta and zeta bar are Grassmann variables. However, when you do that, it turns out that you cannot just work with a single displacement operator. You need to think of two kinds of displacement operators, D and E. And the important thing to note is that D and E are related to each other by e to the power I pi n total. So that is the parity of the total number of fermions sitting there. And that's the relation between these two displacement operators. Why do you need this? Because you usually want to do a lot of algebra where you want to write a delta function. And it turns out trace of D times E gives you the delta function over the Grassmann variables. And also you can write E in terms of a complicated integral over D. So you can do the algebra much simpler if you are working with these two operators, and in the end convert everything into D by using the fact that you can write E as a function of D. Having done that, you can look at the following quantities: chi D, which is trace of rho times D, and similarly trace of rho times E. And these we will call Wigner characteristics of the particular density matrix. And we can also define things called Wild symbols, which is take an operator A, instead of rho, take trace AD, and that's what we will call the Wild symbol. Okay, and similarly, there is two Wild symbols for D and E, two Wigner characteristics for rho, which we will call chi D and chi E. Okay, and so then you can even define Wigner functions by doing some Grassmann Fourier transforms, etc., etc. But note that these are Grassmann valued functions of Grassmann variables. So these are not really physical measurables. These are things that we are doing as an intermediate step towards calculating, let's say, the entanglement entropy. Okay. Now, where does this come into fit with entanglement entropy? So now, remember, the point of Wigner functions was to give you a quantum mechanical average. So now a quantum mechanical average, trace rho times A, can be written as a Grassmann integral of the Wild symbol of A with D, whereas multiplying the chi of E, this is coming from the rho. So you have to basically have one thing with the D and one thing with the E. And then you can convert it into everything with the D by just using this complicated answer, AD of zeta zeta bar, chi D of eta eta bar, and then some complicated expression that you can find quantum mechanical average. Now, why do we care about this when we are trying to do entanglement entropies? And remember, the Renyi entropy, the Renyi entropy S2 was given as some trace rho square. Okay, so it's if I place A equal to rho, I will get the value of Renyi entropy, and in that case, I should be able to replace this guy by the chi D, because A is rho. This would be zeta bar zeta, and good. I am now done with the calculation. Okay, so that's where the Wigner function fits into this whole scheme of things. Okay, so There is still one more step left because you want the Wigner characteristic of the reduced density matrix, not of the full density matrix. And this you can show very easily is that you just take the same trace of rho. In the D, you only use the variable zx and z bar x, where x only goes over the coordinates of A. So that makes life very simple. You can write it as a full trace over everything, which means you can now write it as some sort of a partition function or things like that. Okay. So for bosons, we had done this in this earlier paper. With Sharon, we looked at it for fermions. The answer is slightly different for bosons and fermions, but mostly it goes through similar stuff. Okay, and then you can take e to the power minus s2, which is trace rho square, and then you can write it as this complicated integral as we expected, chi d and a chi d here. And basically A would mean that when I do the D, my x, psi x only goes over the subsystem coordinates x. And if you want to do a more complicated algebra, you can find out the expression for the nth Renyi entropy. So the question that is left to ask is how to calculate chi d. Okay, so if I can give you a prescription for calculating chi d, I'm more or less done, and I can use this to calculate various things. For this, what we do is we use the Schwinger-Keldysh field theory because we want to also look at systems out of equilibrium. And the idea here is you think of an expansion, time evolution of a density matrix in terms of a U and a U dagger, expand each of them in a path integral. So essentially end up with a field theory with doubled fields psi plus and psi minus at each x and time point. Okay, so that's the two fields are because you're looking at both U and U dagger in this case. Turns out that it's simpler for various technical reasons to work with symmetric and antisymmetric combinations of psi plus and psi minus. You can then write a general form of a quadratic action. And what is important out of this whole technical things that you should remember is that there are two kinds of Green's functions. Okay, there are actually four kinds of Green's functions. One is have to be zero, the lowest one. GR and GA are related, so there's essentially one kind of Green's function. And these are objects that propagates the state of the system. So one way to think about GR and GA is that they're conditional amplitude of going to a point, provided you are at an initial point at some time. And then there is a Keldysh component of the Green's function, which is actually related to the distribution functions in the system. Okay, so that's all you need to take out of Schwinger-Keldysh field theory, that there are two fields, but there are, instead of four, there are actually two independent Green's functions. One is used to propagate the system. One is used to look at the distribution function of the system. Okay, unless you are going to work with this amount of information, will work for you. So I have a chi d now that I want to evaluate, that is rho of t times this displacement operator. And what we do is we insert d to the power half on one of the contours, d to the power half on the other contour. And if you look at d to the power half, you will see that it has e to the power ci dagger psi I, zeta I. And then it's not very hard to figure out that this object simply acts like a source term, because that's what it looks like in the position function. But then you come with a source term with very particular set of source term. And this is the pattern that you get. So then some j plus minus and j bar plus minus has some very particular structure. This is a source which is only put on at the time at which you are trying to evaluate the system, and the source which is only put on in the subsystem of A. Okay, and after doing all of this, you can go back to your 1 and 2 symmetric and antisymmetric. Basically, answer is that the chi d is a Keldysh partition function in presence of some delta function source. Now, this is a general formula for arbitrary interacting open quantum systems. So for example, Shumilan probably will talk about it, where they have used this for SYK model, which is an interacting model, but in equilibrium. Mostly maybe a little bit of non-equilibrium also. We had used something similar to look at bosons in both in equilibrium and non-equilibrium with Ahana. And so this is a very general statement that the Wigner function is the partition function in presence of delta function sources. Now,
Raz, you have 5 minutes roughly.
yeah, okay. So now what you have is, we want to look at non-equilibrium dynamics with some arbitrary initial conditions, and for which we had worked out the theory in this paper. You can write down the GK in terms of some complicated matrices, lambda and a sigma, which basically looks at what happens when you have a bath in the system. And when you look at the Wigner characteristic out of this, you find that the same objects, GR and lambda, sit in a very complicated formula here, which you have to evaluate. And then Sharon basically figured out how to do those complicated integrals. And as a result, you end up having an answer where S2 is given in terms of this matrix gamma. So once I know GR, and I know sigma k, I can calculate S2, calculate Sn. I can even take the limit of n going to 1 and then basically calculate the entanglement entropy. This is a statement for non-interacting systems. This is no longer for arbitrary interacting systems, but this is a statement for dynamics starting from arbitrary initial conditions and out of equilibrium. Okay, so what can we use it on? We will use it on two things. One is entanglement entropy of excited states. And here what happens is, let me not go through all the earlier work, but what came out of these earlier works is that there are two kinds of excited states that you can write down. One are critical states where entanglement entropy scales as log of the subsystem. And one is a thermal state, which is entanglement entropy scales as the size of the system. And in this case, in this paper, for example, you can see there are some states which go as log and some states which go as LA. Okay, so that was the general idea for fermions. And for us, this is very easy to compute because we just put T equal to 0. We are starting from Fock states. So we just put T equal to 0. What is known about entanglement energy of entropy of Fock states? So for example, for the Fermi C, it is well known from all sorts of conformal field theory arguments that the answer is a log of KFLA with a coefficient which is related to central charges in conformal field theories. S2 has a similar expression. And in our case, we can just put it on a lattice. We will see that the scaling is with rho into 1 minus rho LA, but we basically recover this answer. What you see here is then you can ask, what about if I have two blocks of states? And the answer turns out, if you look at NB, contiguous blocks of occupied momenta, to be NB into C over 3 log KFA. Let me not go into the details. You can see here that there is a nice scaling, and as I increase the number of blocks, the coefficient increases. However, if you keep increasing the number of blocks very large, the log LA scaling works only when NB, which is the number of contiguous blocks of momenta, is less than LA. We are all doing this in 1D. Log LA scaling fails for this, and in fact, for NB much greater than LA, you end up with a linear LA scaling, and this is basically what is shown here. So the claim is that it's not true that you should call a particular Fock state thermal or critical, but a very particular Fock state can look thermal or can look critical, depending on the subsystem size you are looking at to calculate entanglement. And if you make this criterion that NB greater than LA is thermal, NB less than LA is critical, okay, then you can actually find out the fraction of critical states. So let me not go into the details here, but For example, for different values of density, you can find out the fraction of critical states as a function of LA over L. When LA over L is small, you can see that most states are thermal because, whereas once you reach a particular value above that, most states in the end up being critical in the system. So it all depends on LA over L, and you should be careful about this statements when you look at it in various cases. So
I
can I take
think
1 minute?
okay, yeah, at most 1 minute. Okay.
Yeah, okay. So the other thing that we did was we looked at non-equilibrium evolution of a domain well. So we start with a state which has all occupied on the left, all empty on the right, and it is coupled to some bath. And we want to ask when the system thermalizes, how does the entanglement entropy change? And so the idea is that basically you will see three things here. One is that there is an initial wave front, and as you look at a density at a particular site, you will see that the density rises when the wave front hits it. Then there are some reflected wave fronts coming in here, here and here. And then over a long time, it thermalizes because the bath damps out everything in the system. These are the dynamics, but you see the same thing in entanglement entropy. You see a very sharp rise. I'm looking at entanglement of a subsystem, and I'm looking at it at different points. When the wavefront hits, you see another thing when the wavefront comes back. And then on the large scale, you see it thermalizing to all the values. I will skip all of this and maybe just go to the last slide, where we are looking at entanglement entropy variation during this evolution with subsystem size. What you see is that you see sharp jumps when your size of subsystem is small. When it's large, you see a very smooth behavior. And that's because, the time of passing of wavefront doesn't make sense when you have a very large system. And in the long time limit, if you look at it here, you can ask, okay, what does the entanglement entropy do? It does scale with the size of the system. And so what you can look at is delta S, which is the additional entropy or information loss part side due to tracing compared to the full system. And that goes to zero as you go to the size of the system being very large. So let me just keep the summary here and take questions. I think I've just overshot a little bit. Yeah.
Thank you, Rasdeep, for a very nice talk. I think we have at most 1 minute for some quick questions. Hello? Is there any question?
Yeah, Ravi has a question. Ravi
Yeah, please go ahead, Ravi. Hello?
Yeah. Rajdeep, I am audible.
Yeah.
Yes.
So in the beginning of the talk, when you were talking about trace of rho square being harder than the first power and higher power. Yeah. So you said something about boundary matching there, and I didn't understand. Why do you think the trace of, if you know the spectrum of the reduced density matrix, then the calculation of the trace for higher powers is the numerically, it's not more costly. It is more or less the same.
That statement was.
I should mute.
Yeah, that statement was about analytical calculations. Numerically, once you have the spectrum, you don't care about what function of. Okay. But numerically, of course, you are also basically limited by system sizes. So if you want to take analytic expressions, and the problem there is that trace of something over the full system, whatever you want to do, is easy to write down in terms of path integrals and stuff like that. Okay. Whereas when I say that, okay, trace half of it and then square it and then go, that becomes hard to actually walk through. That's the idea. That's statement for expressions. That's not a statement for numerics.
Okay, fine.
Arti, I have a quick question if there is time. Hello.
Aarti, you are muted.
Let's go ahead. Yeah.
Yeah. So I this is more of a curiosity, Rajdeep. I mean, another way to describe, bipartite system. Let's say I look in terms of Green's functions, and in a non-equilibrium Green's function sense, that I trace out or put the rest your subsystem B as a self energy in the subsystem A. So I was wondering, is there a way to connect what you are saying or to calculate the entanglement entropy in this sort of Green's function way of doing things?
Yeah, I guess I skipped that part. In fact, let me just go to that particular slide. So when you are writing these gammas, okay, I went over it quickly. This is the final formula I wrote. And look at the definition of gamma. They are all written in terms of the Green's functions, okay? And some self-energy coming from the external path. So you are absolutely right. Everything is written in terms of Green's functions. The combinations is what I have written as gamma and lambda here, the particular combinations that occur.
Okay, thank you. I missed it. Sorry. Okay, thanks.
One
Okay.
quick question, if there is time.
Very quick question, okay?
Yes. So can you can write the trace row square as trace swap row tensor row, and this is a trace in the double space, but in the full space.
Yeah.
So can you use that with this Wigner function?
Yeah, sure. That is what people usually do when they basically take two copies of the system, and this is your subsystem, and you basically have to match it here, right? That's what I said. Row ij, row jk. Remember, these j's are only on the subsystem. Okay. Here you have to do some matching on swapping, etc. Okay. What this does is it converts this sort of a thing into by putting sources. So essentially this kind of constraints it's taken care of by using definition of a delta function using a source. As a result, what you get is you first get to do something over here and over here, and then of course you have these additional integrals over the sources. So this is exactly now converted into something on just one copy with sources, but then you have an integral over the sources. So those sources are implementing your swaps, if you wish.
Great.
Okay, so I think we had a wonderful session with a very nice talk from Rasdeep and so many questions. So let's thank Rasdeep again for this very nice talk, and we can move on to Shumilan now.
Yes. Yeah. So can you? Sorry, I think this my.
Screen?
Yeah, I don't have. Yeah, screen sharing. This. Yeah, I think I got disconnected, and probably you have to make me co-host again, Anamitra.
Okay, Anamitra, can you?
Oh, now I'm okay.
I just did.
Yeah, he has made it.
Okay, so second talk is by Shumilan Banerjee from ISC Bangalore, and he's going to tell us about Rayleigh entanglement entropy of Fermi and non-Fermi liquids.
Okay.
So over to you, Shumilan.
Okay, so I'll start. Yeah, so let me start again by thanking the organizers for continuing this wonderful meeting with all these challenges, and hopefully in next time we'll be able to meet rather than having it virtually when you go back to old normal, hopefully. Okay, so I'll be talking about some of the work that I've been doing on entanglement entropy, and my job has been made much easier by Rajdeep's talk. So I'll just go on to the results directly. So one thing is that I have actually a fluctuating internet connection because there is no power and I'm connecting to mobile, so it might get disconnected. So sorry for that. Okay, so let me go on. The first start with acknowledging the people who did all the work. So most of this work of this formalism was done by Orijit, who is now a postdoc at Toronto. And lot of numerical work has been done by Surojit. Okay, and this you can find this work in this publication. Okay, so let me, so Rajdeep has already given the introduction. So I'll just again revise a few things and then go into the results. So we are talking, of course, about entanglement, and so quantum mechanics, as we know, is of course strange. And generally, when we teach elementary quantum mechanics, we talk about superposition measurements, etc., which is the strange aspect of quantum mechanics. But I think the strangest feature of quantum mechanics is probably entanglement, and this comes when you have some tensor product structure, multiple degrees of freedom, multiple particles, etc. And so generally, so this is encoded in this famous example, which is like a popular keyword, this Bell pair of two, let's say, two qubits, which are 0 and 1, and then you form this entanglement pair. So now we know how to measure entanglement, at least for pure state. And so if you are given a pure state, so what you do, you get a density matrix out of it. So you take a whole system subdivided into A and B, and then you trace out the degrees of B with the pure state density matrix. And let's say the A has a size linear dimension L. So, so the measure entanglement, one of the measure is this von Neumann entanglement entropy. So where you have this particular combination, and for example, if you use this combination for this Bell pair example, you will get log 2, the maximum you can get. However, often for calculations, especially analytical calculations or field theory calculations, it is much easier to look into this Renai entropy of the subsystem, which Rajdeep talked about. And this is this particular combination where you have some power of this reduced density matrix, and then you do some tracing and take some log and divide by something. Okay, so this is what I've been going to talk about. And so just one slide, sort of why care about entanglement in condensed matter systems. I mean, these are like a thermodynamic system, not two qubits or all. But the point is that entanglement, among many things, can have, be a very good measure of various states, ground states, like symmetry broken, critical, and topological ground state. And there is this famous area law. So typically, if you look into ground states which are gapped, typically short range models, local models, then you typically get this entanglement which goes as an area of the subsystem L to the power d minus 1, d being the dimensions. However, there are corrections, and these corrections are often very important, and this area law is not universal, but this correction in some cases are universal and tells about some universal aspect of the physics. So I have just copied a table from this review article by Laflorency. But I'll not go into this. But what is important is that you can characterize, for example, topological order using entanglement, so-called topological entanglement entropy, which is probably the simplest and unambiguous way to define a topological order, at least theoretically. And entanglement has also beautiful connections with dynamics, which has emerged in recent years. I will not go into it. So dynamical phases you can also characterize using entanglement scaling, as Rajdeep also talked about to some extent. So now in this talk, I'm going to talk about, as the title suggests, I'm going to talk about Fermi and non-Fermi liquids. So just one slide on that. So Fermi and non-Fermi liquids are of course realities. I mean, they are found in experiments, and I'll not go into all these phase diagrams, but there are several famous compounds. For example, the most famous one is this cuprates, where you see a large regime, a metallic phase, which is anomalous, which has anomalous transport. So I'll not go into this different characterization of transport. However, what I'm going to do is use this diagnostic, which we'll be using in our context, which is the self-energy. So self-energy, so you can distinguish Fermi liquid and non-Fermi liquid using this, how the self-energy behaves as a function of energy at low energies. So for example, if the self-energy is smaller than the energy itself, then it is a Fermi liquid, which essentially means for a metal which goes, the self-energy goes like a power law, is alpha is greater than 1. And non-Fermi liquid, the self-energy will dominate at low energy over omega, which typically means that alpha is less than 1, and it also suggests that there is no well-defined quasi-particles. Now, what is known about entanglement entropy of Fermi and non-Fermi liquids? Again, this to some extent was covered by Rajdeep. So most of the results are for non-interacting systems, and there are of course CFT results. So if you have a conformal field theory, then what you have is this famous area law of violation, where in one dimension you get this log L violation of the area law. and this has been talked by many people, and you have this coefficient, which is the central charge, which is universal. So now what is expected? So this is also expected to be valid for the Fermi liquids, and there is no corrections, lambda Fermi liquid corrections in this formula. But however, non-Fermi liquids, and there is much less known about this as long as I know, as far as I know. And there are some conjectures, scaling arguments of certain type of non-Fermi liquids. I will not go into this. So this is sort of a motivation. I'm not going to really talk about this type of issues in real Fermi and non-Fermi liquids. However, what I'm going to talk about instead a toy model where you can actually solve the non-Fermi liquid phases. So toy model for non-Fermi liquids. And this is a model which is quite celebrated now. It's actually a zero-dimensional model. So some of these questions about this length dependence and all will really directly not work here. So let me just describe this model. So this is a very simple looking model. So all you have is essentially n sides and then the fermions on each side. And all these fermions are connected to each other by a random coupling, a random quartic coupling. So it's an fully interacting model. There is no quadratic term. You have only quartic term, and this random coupling is drawn from a Gaussian distribution with some strength J. And you have some normalization with n because of thermodynamic limit, etc. So this is the Sachdev-Kitaev model, and there are many interesting aspects of that model which I will not go into. But one important thing is this model is solvable in this large n limit, which is also the thermodynamic limit, and it gives a non-Fermi liquid ground state, which you can solve in some sense. Okay, so Kitaev, of course, proposed this model as a solvable model for holography, and I'll of course not go into this aspect, but this model, even though it's a toy model, there is quite realistic realization that has been proposed in graphene flakes and all. So it's not completely imaginary. I mean, you can have this type of models realized even in condensed matter systems, and not only in black holes, if at all. Okay, so this is the thing. So what I'm going to talk about based on this background. So I'll very briefly discuss this new path integral method. So we also found this path integral methods for fermion independently with Rajdeep and Sharonno for the fermions based on, of course, their work on bosonic system earlier. And as Rajdeep discussed, that what it does is essentially the standard path integral methods for calculating entanglement works in a very complicated manifold. So this is a time direction, imaginary time direction. So you write a path integral, and the path integral resides on this complicated looking geometry with a complicated boundary condition on the fermionic field. So what this new method does is essentially simplifies this and put the fermion in a simple geometry with the same kind of anti-periodic boundary condition that you are familiar with. However, it replaces these complicated boundary conditions by some kind of kick in the imaginary time or in real time if you are looking at it real time. And using this, I'm going to mostly discuss the results of our calculations using this method for interacting fermions. So you can also do it with Howard model with some DMFT approximation and all that I will not discuss about. Okay. Okay. So now, so let me just one slide on this new method. So that we also found out in this paper independently with Rajdeep and collaborators based on their earlier work on bosonic system. So Rajdeep already described the model. So it's we just do it superficially, might be slightly different representation, but it's essentially same thing. So the main idea is that you can write the operator, expand the operator in terms of these displacement operators, which Rajdeep talked about. And what you have in this expression is some Grassmann numbers, which appears here. And then you have this displacement operator, which involves these Grassmann numbers and the fermionic fields, the fermionic operators, not the field, sorry, fermionic operators in this displacement operator. And you can write any operator using this expansion. And there is this Gaussian factor which connects these two Grassmann fields which you require for fermions, unlike the case of bosons. And using this, you can write down this entanglement entropy in terms of these fermionic Wigner characteristic functions, which involve some tracing of the density matrix, the total density matrix that you input, and the displacement operator. So now you can obtain similar expressions for higher order Rényi entropies, but I'll be mostly discussing the second Rényi entropy. So what you do is you take a, let's say you take a thermal density matrix and you write a path integral for this characteristic functions, which is fairly easy to do because it is a total trace. And if you write a path integral for this, you actually get the standard boundary conditions for fermion, which is this antiferromagnetic boundary condition. So what it does to this action for this from the standard path integral is that it adds a term, which is like a source field term, which has this Grassmann source fields, and it acts like a kick in your imaginary time, in this imaginary time formalism. So that's basically what happens when you do this formalism. And you can do it also for time dependent density matrices and using a Keldysh contour. So I'll not write it again. So we also did it in our paper, the formalism. And here also it works like an imaginary time kick. You can put the kick, you can split it into two parts, put it two places or one place and things like that. So there are a lot of gauge freedom sort of putting this particular displacement operator. And now using this, you can very easily obtain all the known expressions for non-interacting fermions, which is also found in this paper. And it is written in terms of this correlation matrix, the standard expression, and this correlation matrix only works in the A subsystem. So one thing I should remind you that this Grassmann fields only in the A subsystem when you calculate this Wigner characteristic function. Okay, so now let me go into the results. So this is the model that we first going to look at, and this is this SYK non-Fermi liquid. So this model will be used as a building block to build other models based on this non-Fermi liquids and Fermi liquids. So let me just briefly describe the essential feature of this model. So the first thing is that you can find out the single particle Green's function, which are all on site in this limit, because remember this model is infinite range, everything is connected to every other thing. And as a result, it is sort of a zero-dimensional model. There is no information about space in this model. Okay, so you only get on-site Green's functions, and these on-site Green's functions diverges as 1 over square root of omega. So that is the characteristic of this SYK non-Fermi liquid. And the self energy goes like square root of omega. So this is what I was telling, that the self energy is much stronger than omega itself as omega tends to 0. So that is the characteristic of non-Fermi liquid here. Now, one aspect of this which is important for our purpose is that this model gives a non-zero entropy at 0 temperature if you take the limit in this way. That is, you first take n tending to infinity limit and then you take t tending to 0 limit. In fact, what is shown here is a numerical calculation of this large N theory, where you find that the entropy at t equal to 0 has a finite value. So what is the interpretation of this entropy? So the interpretation of this entropy is that the SYK model near its ground state has an extremely dense many body spectrum and almost like high energies at its conventional model, and the level spacing is exponentially small, and in fact determined by this entropy. This is in contrast to conventional model, which has a gap or 1 over n or some polynomial in n separate gap here in conventional system. So this is the origin of entropy, residual entropy, when you take this limit. And this entropy could be interesting in the context of gravity. So people would like to compare this entropy with Bekenstein-Hawking entropy of certain type of black holes. Anyway, I'm not going to talk about that. I don't know much about it. But what one interested here is that what is the interpretation of this entropy? Can it be connected to some kind of entanglement entropy, some kind of Renyi entropy, etc.? So what is the interpretation? So that's what I'm going to talk about a little bit. Okay. So now so this what I talked about is non-Fermi liquid, but how to get a Fermi liquid? Okay. So that is also very easy. You can take this SYK model. You can just add a quadratic term with again drawn from some disorder ensemble, and that will give you a non-Fermi liquid. So this model, when J goes to 0, is a non-interacting model. It's essentially non-interacting random matrix. And when you take this strength of this new hopping to 0, then it becomes the SYK model. And you can show in this model that as soon as you add any quadratic term, this term TH not equal to 0, the self energy becomes omega square. So it becomes Fermi liquid at arbitrary low energies or low temperature. And you can get a heavy Fermi liquid from this, where you put a very small hopping. So you get a very small coherence temperature. So now this model I'm going to study entanglement entropy, but what I'm going to study entanglement entropy as a function of, right? So what is the subsystem? Because it's a zero-dimensional model. So the subsystem is essentially you choose any number of sites, some fraction of sites, NA, some number of sites Na out of this total n sites. And what we are going to look at is the this Renyi entropy as a function of this subsystem fraction. Okay, so the strategy is that you take a thermal state and then you try to approach the ground state entanglement by taking t tending to 0 and after taking n tending to infinity limit. And what you have to do in this model, you have to do it as a disorder average Renyi entropy, subsystem Renyi entropy, because this model is disordered. These couplings are all disordered. So you have to introduce both disorder and entanglement replicas, these two copies, etc. And what you do, I'll not go into the detail of it. So you can do it in this large N theory, and this large N theory, you get a new saddle point, which is only specific to this Renyi entropy field theory. And what you have specifically, that you get essentially, you can integrate out the source field, this auxiliary source field xi and eta. And what you get is a self energy kick. So that was what I was mentioning. So you get the same boundary conditions, but you get a self energy kick to these fermions, which appears as some delta function kick at some imaginary time, and this time is arbitrary. You can put anywhere because it's a equilibrium state. So there is originally there is an invariance, time translation invariance. So how do you solve this equation? So what you do is you discretize this over imaginary time, and you have to solve it self-consistently, because these are self-consistent equation with full dynamical self energies and dynamical Green's function, okay, with this source field. So let me now go to the result. So first we want to see that these results that we get from the large N theory make sense. So to check that, what we do, we first look into the non-interacting model. So this model that I mentioned, that where you only have the hopping term, okay, not the j equal to 0, that thing. So what is shown here is this, as I said, the second Renyi entropy as a function of this subsystem fraction. And I have different symbols. So one symbol is for this large N calculation. So since this is a non-interacting model, you can get the same result by just doing correlation matrix and diagonalizing this random matrix, a non-interacting random matrix. You can do, it's not necessary, but you can also take the many body Hilbert space and you diagonalize there. So you can see that all these results matches absolutely perfectly, fall on top of each other, the large N result and the other results. And one thing you should note here that, so these results are at some finite temperature. At 0 temperature, this curve should be symmetric around p equal to 0.5, and it has to go to 0 here, okay, at p equal to 1. So this is what is happening as you take lower and lower t. So this point is going down. So what is quite remarkable here is that even as small as a system at n equal to 10, this large N result exactly matches. So which means that the 1 over n corrections are extremely small for this quantity. Okay, so now let's look at this SYK model, what happens, and what happens here is quite drastic. So again, I am drawing this large N results, and now, yeah.
You have 5 minutes including questions.
Sorry, how much minutes I have?
5 minutes including question answer session.
Okay, I'll just finish soon. Yeah. Okay, so what happens this in the SYK model is quite drastic. So again, the same thing that I have plotted. You have the large N results, and now these many body diagonalization results. We of course cannot do the correlation matrix because it's an interacting model. So what you find that these results actually above sort of p equal to 0.4 or something deviates hugely. For instance, this entanglement entropy for the SYK model, the Renyi entropy for the SYK model, even if you take t tending to 0, stays here, it never sort of seems to approach these results, which is the case for exact diagonalization, this clause. Okay, so it seems to be a very large finite n effect in these results, and in fact, you can take these values and you can extrapolate to t equal to 0 for the large N calculation, and what you find that it extrapolates exactly to this 0 temperature entropy of the SYK model. And in fact, you can see the ED result and the large N results deviates at low temperature. In fact, you can show that this Renyi entropy has to be exactly equal to residual entropy when you take t tending to 0 limit for p equal to 1. Okay. So what does it mean? So it means that this quantum entanglement of the NFL ground state cannot be extracted out of this large N limit. So whenever you approach from the large N limit, you somehow this entropy, this residual entropy will always contribute. And it essentially means that these finite end corrections are completely non-perturbative in this limit, which is unlike this non-interacting case. In fact, if you put in some interacting Fermi liquid, not the non-Fermi liquid, you put some pH not equal to 0 term, you find that then this perfectly approaches 0 at this point, okay, unlike this. And in fact, even for a very small system ED, it exactly matches with this large n result. So as soon as you make it a Fermi liquid, then the corrections 1/n corrections are extremely small, and you can show it here that it exactly goes to this 0 limit. And you can look at also the bipartite entanglement entropy as a function of this parameter hopping, which takes it from a non-Fermi liquid to a heavy Fermi liquid, and you see a crossover in this entanglement entropy. So I'll skip this. So maybe I'll just mention one thing. That one can do it for spatially like it. So this was a 0-dimensional model, but one can extend it to finite dimensional model also. So all you do, you think this SOIK as like an atom, okay, like big atoms with big atoms with many levels, and you can put them on a lattice, 1D lattice, 2D lattice, whatever you like. And what it does is that it gives people have found out earlier that you can calculate transport in a non-Fermi liquid metal. You can get diffusion in a non-Fermi liquid metal. You can get heavy Fermi liquid, and you can connect transport and chaos and things like that. So for this system, we can actually calculate the entanglement entropy. So this will be entanglement entropy of a diffusive Fermi liquid. And I'll just end with this result. So what we do here is that we calculate the entanglement entropy as a function of L, this subsystem size, and you take a subsystem. So remember that for a Fermi liquid, standard Fermi liquid, you should get this log L, right? So what happens is for this diffusive Fermi liquid, this disordered Fermi liquid, what you find that initially there is a log L variation, but you can't really say you can fit it in anything probably because it's a small range. But after that, this actually saturates, okay? And it actually follows a modified growth law. In fact, this kind of growth law has been proposed earlier in other contexts of a diffusive Fermi liquid using heuristic arguments. So we actually can sort of calculate this growth law for a diffusive Fermi liquid for a completely interacting system. And it seems that you can have some coefficients which you can't probably interpret as a central charge, but this coefficients also changes with interactions that you can show here. Okay, so I'll just stop with this slide. So essentially, I showed a new method. I just briefly mentioned it, and that I used it for some systems, for Fermi liquid and non-Fermi liquid. And you can use this method for many different contexts, some of which Rajdeep talked about, and we have done some of this also in DMFT and other things. So that's with that I'll end. Thank you for your attention.
Thank you, Shumilan, for a very nice talk. We have 1 minute for a few questions.
Hi, Arti, can I ask a question?
Yeah, sure, go ahead.
Shumilan, so can you just provide a bit more insight as to how I should understand the lack of 1/n scaling or the finite 1/n corrections in the non-Fermi liquid or the SYK fixed point? Is it because of the scaling? Is it because that S0 really comes from a term which depends upon the spectrum exponentially as e to the power -n?
Yeah, right. So basically, it is the problem of taking the limit, right? So in the large n, you always take n tending to infinity limit and then t equal to 0. So you can think that when you are taking n tending to infinity limits, t is some finite value, right? So any finite value, when you are taking n tending to infinity limit, there are infinite number of levels. So you can never get rid of by this way, right? And as a result, I mean, this is sort of an exponential effect. So you can't get it by 1/n correction. So you have to probably get some non-perturbative large number of terms in 1/n. Yeah. So there are some ways to get rid of this using the Schwarzian methods, but that is beyond large n, and we have been working on it. But yeah, I mean, it can be probably done, but yeah, that is the reason. Yes.
Okay, thanks.
Okay, are there any other quick questions? If not, let's thank Shumilan again for a very nice talk. And we can move on to the third speaker of the first session. Saptarishi, can you share your screen?
Yeah, host disabled participant screen sharing. Yeah, host has to enable.
Okay, Anamitra, can you please do it?
What is the problem? Yeah, Ravi here. Anamitra is not around. So Saptarshi, you are.
Or
Probably that co-host or something.
I'll make you a co-host.
Yeah.
Yeah. So yeah. Try now.
Uh-huh. Thank you.
Yeah. Okay.
Okay, so the third speaker is Saptarishi Mandal from IOP Bhubaneswar, and he's going to talk about interacting electrons in the presence of interaction and magnetic field. Over to you, Saptarishi.
Yeah, thank you. Thank you, organizers, for inviting me. This is already the fourth time. My talk is on interacting electrons in the presence of interaction and magnetic field. Basically, we did some work with Sanjay Gupta at Central University of Jharkhand on the Hofstadter spectrum. How does it changes in the simultaneous presence of interaction and a magnetic field? My slides are half ready, but so a lot of details will not be there. Okay, so it is not coming down. Maybe it is taking time. Let's see.
Yeah, Saptarshi, just try to slide down, change your slide.
Yeah, I am doing page down, right?
It's changing on your machine, right?
No, it is not changing.
Oh. No, but it's a PDF file, right? So you should be.
Okay, now it is changed.
Yeah, now it's working.
Yeah. So the brief outline is a brief introduction to Hofstadter problem. It is a one-page introduction. And I thought to give some quick review on important work, but due to the time constraint and also some busyness from my side, I could not. So I will directly go to motivation and formalism. And we investigated this for both the square lattice and honeycomb lattice. We investigated both the spectrum and some kind of entanglement study, and previous two talks has given excellent overview of the entanglement entropy, its importance in condensed matter systems, and also yesterday a lot of talks are on the interaction. So I think I will not miss anything. And then some conclusion or discussions. So in 1978, Douglas Hofstadter has investigated this problem. The problem is very simple. Take a square lattice and apply a magnetic field and find its spectrum. So he worked in so-called Landau gauge, where the y component in the vector field is proportional to the x. So this problem then becomes a one-dimensional coupled chain into y directions. For every x directions, you can do Fourier transforms, and he solved it analytically for rational values of magnetic field. And then he extended it to the irrational values. The nature of the result remains same. So how does the spectrum depend? That is the central idea or the central theme of this talk, how this spectrum changes with interactions and disorders and corresponding entanglement spectrum. So the main result which we need is the following. So as you see, this picture is the Hofstadter spectrum. Along y-axis, we plot the magnetic field B, scale to 0 to 1. And along x direction, we have the spectrum, the eigenvalues. And as we see that for a given magnetic field, the eigenvalues are accommodated, or they are clustered together, and there is a gap, and then there is a clustered together again, and there is a gap again, something like that. And from a large scale, it looks like a butterfly kind of pattern. It has also a close connection to the fractal dimension, fractal structure. As you see that these fractals are repeating, there is a repetitive pattern. So few properties are is that if I calculate the spectrum for a given magnetic field B, so B plus N, or here N is 1, N could be any integer, they are identical. Sorry, there is some spelling mistake, I could not this. And spectrum of some alpha with minus alpha, they are also identical. If a given energy belongs to spectrum alpha, then minus E also belongs to the spectrum. So this is a particular symmetric. And the upper limit and the lower limit is given by this -4 epsilon to 4. And all these four results has been extensively proved in that paper. It is a very beautiful paper. Now I go to quickly to what is our motivation. So there has been a lot of work on this observer problem, various aspects. And there has been also work on how this observer spectrum can be killed in the presence of interactions. Once we put a on-site interactions, that will show also. So what we thought is that whether this, once you put interactions and observer spectrum is lost, that its fractal character or butterfly character is lost, can it be revived by disordered? So we wanted to investigate a competition between correlation driven insulator and disorder driven insulator. Because we know that disorder also induces a localizations due to the decoherence properties, and also interactions. Due to the interactions, we also have a localization properties. So whether they can help each other and whether it can be manifested in some way in the observer spectrum. And we have taken two kinds of lattices to see whether the lattice connectivity or dimensionality has any role, and also how the entanglement properties get manifested in this process. Okay. So this is the brief model Hamiltonian and formalism. So we took a tight binding Hamiltonian. The first part, as you see, the simple hopping, where this Ti alpha will be due to the magnetic field, we will have a PL substitutions by this way. And the second term is the on-site interactions, chemical potentials, and disorders. Epsilon I will be disordered potential, mu is the chemical potential, and U is our interactions. So as usual, we took the Landau gauge, and during for our work, we have done a simple mean field analysis, very simple. So we decouple into each densities. Okay. So for the interactions, for the disorder, generally we need to take many realizations and take an average over that. And it is really a time consuming problems, because for each realization, self-consistence, and then do this disorder averaging for many such configurations will be very long time job. So what we did, we took a particular disordered sequence, which is called Rudin-Shapiro sequence. There are other work also which has taken Fibonacci sequence, etc. in one dimension. So the significance of the Rudin-Shapiro, or why did we take it, is that in 1988, by this paper PRL that we have written, that by calculating the DC conductivity and other average other order parameters, it has been shown that this routine, this particular disordered sequence is shown to mimic the disorder average very well. So we hope that this does not bring any shortcomings to our problem. So we take that as a granted by that result, and we took that routine Sakura sequence. So what is the sequence? So you take any 4 letter A, B, C, D, and the generating scheme is that I replace A by AB, B by AC, C by DB, and D going to DC. And we take particular values of A, B, C, D as given here. We have taken 2 disordered strength. One is 0 to 13 and other is by half. Taking that possibilities, and then the sequence therefore grows like this. One can check it very easily. So this is wrapped in a 2-dimensional lattice, because a 2-dimensional lattice we have to consider a 1-dimensional lines wrapped over 2-dimensional path. So about that 1-dimensional path over 2-dimensional lattice, we wrap this particular sequence. Okay, and regarding the entanglement entropy, what we studied is the following. So for the square lattice, we took a small square, which is a subsystem, and we grow the area of the subsystem and plot the entanglement entropy for each subsystem. And for the largest subsystem, when it is exactly half of the system, we also calculate the spectrum, entanglement spectrum, the eigenvalue of the reduced density matrix, and try to plot it. So similarly, same thing for the honeycomb lattice. And this honeycomb lattice has this kind of geometry we have taken, the armchair in the right and left, and a zigzag edge in the top and bottom. So we will also see how this interaction and disorder is manifested there. And now we'll go to the, I will go to the result of for the square lattice. Yes, so as we see, the figure A is the Hofstadter spectrum for square lattice without interactions and without disorder. Here U is the interactions and delta is the disorder. So yeah, and figure B, as we see, is the entanglement entropy for every magnetic field. And for a given magnetic field, if I go along y-axis, these values are basically the entanglement entropy for each subsystem. And as we see that for very low magnetic field, the entanglement entropy is equidistant almost. So that means they are following the area law. Okay. But as we increase the magnetic field for larger magnetic field, sorry, for larger subsystems, the area law seems to be a little bit violated. And when the subsystem is very large, it is more violated. Yeah, more departure from the area law. But one thing is noticeable is that they are symmetric around the values 3. Actually, it should be pi 3.14. So the Hofstadter spectrum is, as you see, there is a symmetry, 4-fold symmetry. So it is reflected, there is a particular symmetry, and also it is reflecting symmetry, parity symmetry around b by 2, which is 3.14. So entanglement entropy is also symmetric. And the figure C is our entanglement spectra for the half subsystem, where the subsystem is exactly half of the area of the full system. And we suspect that very interestingly, it has also the symmetry, the 4-fold symmetry of the Hofstadter spectrum. And we think it has also a fractal character. There are some repeating patterns. For example, exactly b equal to pi, there is a sparse structure. So lot of void regions. And as you see, these void regions are repeated. So this is the entanglement spectra, and let's see what happens when we put the disorder. So in the absence of interaction, which is given by D, and once we put the disorder, so for a given this strength we took, the first choice, we see this Hofstadter spectrum is going to vanish. It has almost vanished. The entanglement entropy retains is area law for small magnetic field and also the large magnetic field, but the fluctuations of entanglement entropy for large subsystem for intermediate values of B is reduced compared to when there is no disorder, as you see, if you compare the figure B and figure E. For figure F, we see the symmetry has been lost. The four-fold symmetry has been lost, but still the reflection symmetry around B equal to pi is still exists, at least to the bare eyes, but we'll see whether we can quantify it better. So this is what happens when the disorder is switched on. And now we'll go to when interactions is switched on and disorder is 0, and then when both are switched on. Okay, so this figure A is what happens when interaction is switched on. For square lattice, it is U equal to 2.7, and there the a gap opens as it should. Entanglement entropy becomes more smoother, but for B equal to pi, there is a huge departure for the largest subsystem. Entanglement spectra has completely different character. It is grouped together into a upper band and the lower band. In many literature, this opening up of the gap in the Hofstadter spectrum is termed as the absence of Hofstadter spectrum. So now, if I put on the interactions, as you see, this gap is closed, and the Hofstadter spectrum somehow has a better feature compared to where there is no interactions and no disorder. So figure E shows the corresponding entanglement entropy. And if we remember the earlier plot, it does not show much difference, but only one difference between figure B and figure E is that for B equal to pi, the entanglement entropy is minimum here at B equal to pi, but here the entanglement entropy is maximum, that we notice. And for the disorder also, the entanglement entropy becomes disordered looking, but still we find that the reflection symmetry around B equal to pi still retains. So yeah, so these are, I will summarize into next. What the so-called result is that entanglement spectra has some fractal characteristics. It seems entanglement entropy obeys area law, though there are departures for some magnetic field or in the medium range, not very high, not very low. Entanglement spectra and entropy are symmetric as Hofstadter spectrum. Entropy is minimum at half magnetic field. With interactions, entanglement entropy becomes homogeneous, no ups and downs. Disorder still seems to preserve the reflection symmetry of entanglement. Interaction causes a gap in the Hofstadter spectrum as well as in entanglement spectra. And disorder closes the gap caused by interaction. So now I will quickly go to the honeycomb lattice result, and we will see some differences. So the same result.
Krishi, you have 6 minutes including questions.
Okay, good. Yeah, so in A, as we see that the spectrum is there, and in B, the entanglement entropy, and we see it shows better power law for all magnetic field. There are no oscillations as found in the square lattice, but entanglement spectra is completely homogeneous. There is no reflection symmetry or no fractal kind of character. The moment we put disorder, the Hofstadter spectrum is absent. Entanglement entropy still retains so or so as before. The spectra becomes a little bit different with a minimum at B equal to 2, where the magnetic field is half the periodic values. And so once we put the interactions, the Hubbard gap opens up, and once we put the disorder, it actually there is very faint. I think we need to take more B values, and then the Hofstadter spectrum will be visible that we are running it the code. Entanglement entropy does not so much character, it changes, and similar behavior for the spectrum also. It does not. So it seems very robust for the honeycomb lattice. The entanglement property does not change much whether interactions is present or disorder is present. So then we have also investigated for taking the disorder strength half. So I will just quickly, I'll just skip the result. Only take a point from that is that the interaction needed is reduced. So yeah. So entanglement entropy seems to have a area law and it is structureless. Entanglement in spectrum does not have any structure as well. While for square lattice, revival happens at u equal to 2.7, the corresponding value of u for honeycomb lattice is 3.5. So it was wrongly written 3 in the picture previously. So as you see that lattice connectivity has some significance. In the presence of interactions but zero disorder, the entanglement entropy is minimum at b by 2. This is also for the seen for the square lattice. When we reduce the disordered strength by half, we get the interaction needed for Hofstadter revival as u equal to 1.8 and u equal to 2 for square lattice and the honeycomb lattice. So things to do. Actually, we think that the proper way to characterize whether Hofstadter butterfly is revived or not is to calculate the fractal dimension, which is 1.52 for pure Hofstadter spectrum. And we have trying to calculate it, but by some box counting method. And method I will not go detail. It can be seen. The reference is there in the next page. Let me go to that. So this paper is Sosa et al. They have calculated these fractal dimensions for Hofstadter spectrum in the presence of spin-orbit coupling. And as you see, is that this beta is the spin-orbit couple. And DC, the correlation dimension or whatever the fractal dimension is 1.52 for beta equal to 0. As we increase the value of beta, it increases gradually. So
Saptarishi, can you wind up, please?
Yeah. So this is discussion. So interaction and disorder are able to nullify each other. The entanglement spectra has some symmetry which is absent for honeycomb lattice, and there are some things to do that we are planning, like study of gap and fractal dimension, and if we scale the interaction lambda, what are the scaling needed for the disorder? Thanks. If there is time left, I can answer few questions.
Okay, thank you, Saptarishi. We can have 1 or 2 quick questions because we are running very late. Well, if there are no questions, go ahead, please.
No, Aarti, you can go ahead. I can ask later if there is time.
Now, I just wanted to ask Saptarishi, in the way you are including disorder in your problem, how do you control the strength of disorder?
Actually, the value of disorder we took, now we think that it is not the correct value of, we have taken 0 to 1, 3, right? The value of ABC.
No, I mean, I'm talking about the way you showed that sequence, right? Some Shapiro sequence. So I couldn't get in that way of doing disorder averaging. Where is the disorder strength coming?
the sequence I have shown,
Hmm.
each letter is like the site index.
Okay.
And that one-dimensional line is wrapped over the 2D path.
Mm-hmm.
And wherever A is there, I put 0. Wherever B is there, I put 2. Yeah.
Okay. Okay.
Yeah, that way.
Okay. Thanks. Anamika, please go ahead.
A quick question. I noticed when you put the interaction there, your entire Hofstadter spectrum shifts up. Is this a Hartree shift?
Yes, yes. Yeah, the gap. Yeah.
Okay, and at some point, I think for the square lattice, did you say something about a general question about magnetism in the problem? I understand you're doing a sort of mean field, but you can get some sort of mean field magnetism there. So does that, or
No,
is the field so high that
you are
it sort of
right. We
makes
have
everything
not
ferromagnetic?
calculated that.
No, no, is it as I understand, your magnetic field typically for Hofstadter has to be very large if it's a because it's you have to have enough flux through threading your lattice sort of
Yes.
this thing. So is it that everything becomes ferromagnetic, spin polarized by the time you are at sufficient high magnetic field for seeing the Hofstadter spectrum?
Uh, no, we have not calculated that. We have that data. I understand that enough minus n down, whether what is the at the half filling, what is the magnetization, that we have not calculated.
Anamitra, he has basically done the spin symmetric Hartree-Fock calculation.
Okay, okay. It's so we should think in a paramagnetic regime in that sense.
Yeah,
Yeah,
yeah.
yeah. Basically, there is no, yeah, the spins are here not coupled to the
Okay,
magnet.
okay, sure. Thank you.
Okay, thanks, Saptrishi. And we should quickly move to the next speaker. Saptrishi, please stop
Yeah,
sharing your
all
screen.
is, I'm trying to all is right.
And Tanay, are you around?
Yes, yes,
Yeah, please share your screen.
yes. So I just shared my screen. Can you see it?
Yes, yes, yes. So the last talk in this session is by Tanay Nag from CISA, and he is going to talk about dynamical analog of topological lattice defects. So Tanay, you have 10 plus 2 minutes, and
Yes.
I will let you know after 9 minutes, okay?
Okay, okay. Thank you, Arti, for the nice introduction, and thank you, organizers, for giving me the opportunity to present my work here. So this talk is based on dynamical Floquet dislocation mode. So the title suggests that dynamical analog of topological lattice defect. This work is based on this archive version, and we have done this. I have done this work with Bitan. And I am now in RWTH Aachen. So my collaborations is like from CISA and Aachen. Okay, so now the main question we pose here, like how do we probe a topological phase in the bulk without having known its boundary modes? So we know that in topology there exist boundary modes, but can we get some information from the bulk itself? So in order to get that information, we introduce some dislocation or lattice defect, and if the topological phase is captured by the lattice defect, we call it translationally active topological insulator. Now the next question is that once we drive the model Hamiltonian of the topological system, how do this bulk probe get modified? So we eventually get some non-trivial time dimension, which essentially allows us to have anomalous dislocation mode, which are not there in the static system. So in this way, we can get some translationally active Floquet topological insulator. So these are the basic two aspects of our talk today. So now some basic things about topology. So as we all know, it can be observed in quantum Hall and quantum spin Hall effect. If we do not break the time reversal symmetry, we get quantum spin Hall phase. So I just directly go to the basic example of quantum Hall, where if we take a two-dimensional sheet and we apply piercing magnetic field, we get some skipping orbital at the edges, which essentially leads to the topological H state at zero energy. And we can understand this feature from the filling of the Landau level as shown here. So this is the basic notion of topology, that we get some H state at zero energy at the boundary. So now the next question that we pose here is that how do we include this dislocation, or what is dislocation, and how do we geometrically interpret it? So here I have shown basically a 2D square lattice and the atoms are sitting at the intersection of these vertical and horizontal lines. Now, if the way we implement this dislocation is called Volterra cut and glue procedure. So we somehow remove a line of atoms. So the removed line of atoms is depicted by this hollow bubble, and then we reconnect it via the adjacent sides. So the adjacent sides is depicted by this uh, the solid bubble red and blue. So in this way, basically we cut a line of atom and then we reconnect the adjacent sites. And when we end this dislocation, we call it a dislocation core or dislocation center. So that is depicted by this orange bubble. So in this way, once we construct a dislocation, we basically restore the translation symmetry away from this dislocation core, but basically we are breaking the translation symmetry near the dislocation core. So now if we go to the basic example of topology, then here I have depicted 4 figures. So just consider the left top. So it's basically a 2-dimensional square lattice and H state are flowing along the boundary. And now we deform the sample, we somehow remove one line of atom, and it's basically a deformed square now, as you can see here. So we get some additional edges here, so through which the current is flowing, and we get some H state across the boundary. And now if we connect this line of atoms, like if we just connect the atoms across the edges, then if eventually we get back to the square geometry here, which is the figure left bottom. We get back to the square geometry, but due to this hybridization of this atom across the boundary, we essentially generate a spatial profile of mass. So we eventually generate a mass profile, and that will allows us to have some dislocation mode or like the localized core at the dislocation center, which is depicted by this red dot. And now if we go to the periodic boundary condition, and in presence of dislocation and anti-dislocation core, we can go back to the localized mode, which are at zero energy and like and there is this mass profile associated with them. So having said that, now this is our model basically. So we take the 2D Chan insulator. So these sigmas are the orbital indices. Now here we have this mass term, which is given by m minus summation over cos, and there are these other hopping terms which is given by sine k. So this model is having is having particle hole symmetry. The particle hole operator is provided here, sigma 1 complex conjugation, but this model breaks the time reversal symmetry. Now, if we just want to explore the phase diagram associated with this model, so we have a mass inversion, we have an on-site mass term m here. So we'll just focus on the values of m and the topological phase associated with it. So for here, if you just follow the middle panel here, which has the energy momentum dispersion, if we have the mass value between 0 to -2, we get the band inversion at kx is equal to plus minus pi. On the other hand, if we go to the other values of mass, which is between 0 to 2, we get the band inversion at kx is equal to 0. So these two are different topological phases. In the top middle panel top figure, we get the Chern number is equal to +1. So Chern number is basically giving you the number of right movers minus the number of left movers. So for a given edge, for example, red edge, which is localized at the left edge, let's say, so we get the number of right movers, which is 1, and left movers, there is no left movers, so this is basically 0. So the whole number turns out to be 1. And similarly, we can go to the other phase between 0 to 2, and there the Chern number turns out to be -1. So it's basically when you get the band inversion at the zone bound or below a zone boundary, you get Chern number 1, and when it occurs at zone center, we get Chern number -1. But if we go back to the real space, the real space energy level diagram is depicted at the left panel. Here you can see both of these phases have shown actually showing same identically same feature. There is no distinction between these two phases. And if we get back to the real space with open boundary condition, the right panel which is shown, we again get back to the same structure of the LDOS. So there is no way that you can distinguish these two phases from the real space structure. Now we introduce dislocation. So upon introducing dislocation, we see that the phases between m -2 to 0, we refer it as m phase, where band inversion happens at plus kx is equal to plus minus pi. We see a very prominent dislocation mode which is appearing at the mid gap, and which is exactly at 0 energy, and the state is localized exactly at the dislocation core. So basically, in this way, upon introducing the dislocation, we can identify this M phase. On the other hand, when we have band inversion at 0, where the mass value is between 0 to 2, we cannot get any dislocation core at the 0 energy. We get some dislocation mode, but which are like diffused in the bulk. So that means that upon introducing the dislocation in the bulk, we can identify two different phases, which is topologically, translationally active or translationally inert. The left phase at the M phase, where the band inversion happens as plus minus pi, we consider this phase as translationally active. Okay, now why this is happening? So the main reason is that when an electron moves around the dislocation core, it basically picks up a phase which is given by k dot b. Now what is k and what is b? So b is basically Barger's vector, because we know around the dislocation we are missing by a translation vector, because we break the we just remove one line of atom. So this b is given by the Barger's vector perpendicular to the missing line of atom, and k is the band inversion momentum. So now when k becomes finite, when k becomes plus minus pi, this k dot b turns out to be pi. And as a result, we get a masked formation, masked domain wall formation in the sample, and eventually which will lead to the zero energy state, followed by the Zaki-Rabi mechanism. So this is the underlying reason why we should get a dislocation mode at when band inversion happening at finite momentum. Now, having said that, now the main topic is that this periodically driven system, that is the main aspect of this talk. So now we know that upon driving a system, you can get many non-trivial phases. So for example, you get Kapitza pendulum. So when you basically oscillate the point of suspension, you get a new stable position at theta is equal to 0 here. So it's basically the vertically upward position, it gets fixed. And on the other hand, for a quantum system, if you drive a single level, then you can eventually see you cannot get any tunneling from one level to the other level here. So it basically your tunneling amplitude gets modified by delta effective. So due to the driving of the single level. So these two examples are very basic examples that like periodically driven system can give you a whole lot of non-trivial state. Now in the context of topology, what we can get, so upon driving light or upon by changing some values of by changing some parameters in your Hamiltonian periodically, you can transform a gap non-topological phase to a topological phase here, as I have shown. So it's basically you get some zero energy state when you drive the system, and when you are in the static limit, there is no zero energy state. It is trivially capped. So this whole field of this driving is called Floquet topological phases. Floquet topological insulators, and these phases are called Floquet topological phases. Now,
Sunny, you have 2 minutes left.
Yeah. So now, like when you drive the system, it basically get some anomalous mode which are happening at finite energy. So these are the anomalous mode which are away from zero energy. So basically, this red and blue lines which are away from zero energy, this will basically the implication of your dynamics. Now we will probe this anomalous mode in our system. So that the driving we have imposed here is just a staggered on-site potential, which is given in this form. Now we have a Floquet operator, and we then diagonalize the Floquet operator to get the eigenvalue and its eigen energies. So this is the basically phase diagram we are getting. So this phase diagram is based on the Chern number. So this color bar on the right hand side is basically Chern number, and it is plotted as a function of frequency of driving and the amplitude of driving. We see a lot of phases here, basically depicted by different colors, but we have to consider the translationally active Floquet topological phases, which is depicted by the symbols. So what are the symbol means? So it's basically when we get the normal dislocation mode at mu is equal to 0, mu is the quasi energy, we refer it as the cross and the circle. When we get the anomalous mode, we refer it as the, so it's wrong, we refer it as the plus and the circle. And when we get simultaneously both dislocation mode happening at 0 energy and at omega by 2, which is at the zone boundary, we refer it at circle and the dot. So in this way, we can basically explore our whole phase diagram, and then basically we have to translate our static system to the Floquet topological insulator, and then we identify the translationally active modes. So these are few examples. If I go to the high frequency limit, we can get various phases which I depicted here around omega is equal to omega above 8. You can see various phases here. So there are kx is equal to plus minus pi will give us the dislocation mode. Here the dislocation mode at the left panel, you can see here the dislocation mode happening as kx equal to pi plus minus pi, and at zone center, so we get we go to the real picture and we get the at mid gap we get at mu is equal to 0, we get a dislocation code. Similarly, for the right picture here, right panel, you can see the dislocation mode happening at the zone boundary. And if we go to the real space picture, we similarly we diagonalize the Floquet Hamiltonian, we get here the dislocation mode is happening around omega by 2, which is the Floquet zone boundary, and the associated LDOS is plotted below. So in this way, we can identify different topological phases. So this is another example. So the last example I will talk about. So we will get some.
Tanay, we should wind up. Your time is up almost.
Okay, so this is the last example where is basically the trivial insulator when you get both dislocation modes happening at zone center and zone boundary. So it's a new phase that we are getting here. So so this is like a new non-topological phase where you can have dislocation modes, but the phase remains non-topological. And so there are some other examples. So we can also do it in experiments by so this one experiment from the how do you introduce dislocation, and you get some normalized resistivity difference. And there is one experiment from the Floquet part. So you can basically introduce some Floquet sidebands. So that basically gives us the opportunity to explore our work from in lab. So then we conclude that with the realization of Floquet topological insulator, we can have dislocations, we can add dislocations to it, and eventually we can get normal and anomalous dislocation modes. So this anomalous dislocation mode is basically new in the Floquet business that we approach here, and our whole procedure can be extended to 3D or like Floquet topological insulator, light driven Floquet topological insulator, and some other phases. Yeah, that's all.
Okay, thank you, Tanya. I think we are already at 11 o'clock, so we can have at most one question, if there is any question. Okay, I see there is no question, so let's thank Tanya for a nice talk. And let's also thank all the speakers of this session. We had very interesting talks, and to the organizers if they have any announcement.
Okay, thanks Aarti for chairing the session. So I should thank you on behalf of everyone, and also the speakers of this session for very interesting talks. So we are running slightly late. So the next session, instead of 11, let's start at 11:10. It gives a little bit of time for people to get connected, etc. Is that okay with everyone? So I think the next session chair is Mukul. Yeah. Hi Mukul, if you're around. Hello. We cannot hear you, Mukul. Okay, so I'll just. Navnita and Avdesh. Let's just Avdesh. I mean, Navnita I saw.
Hi,
no,
Namitra. This is Avdesh here.
Okay.
Hi, this is Navneet. I'm also okay.
Yeah, I'll just make you the session co-host as well. So, please to but Mukul, let me just get to Mukul. I'll come to you guys. Just give me 1 minute. The session chair, I cannot hear his audio. Just let me just sort this out. Mukul,
Sure.
thank you. Mukul, can you? I mean, we cannot hear you. Can you hear us?
There?
Yeah, he's there. I can see his video, but I think there is a net problem.
Can you hear me now? Can you hear me now?
Mukul, yes,
Yeah.
yes. Yeah, okay, good. Okay, so fine. So Mukul, I've made a co-host. So Avdesh, you want to try your screen?
Yeah, sure, I can try. I think Navneeta is first, but yeah, anyway, I can try to.
Okay, just try. I mean, it's fine. I mean, okay, I can see
Can
your
you
screen.
see my screen?
Yeah, yes.
Is it full screen now?
Yes, it's full screen. I can see your cursor. Yes.
Yeah. Okay, great. So should I stop sharing?
Yeah, sure. Thank you. So Navneeta, maybe you can try yours.
Yeah, I'll just share my screen.
Yes. Yeah, I can see your screen. Yeah.
You're able to see the full screen, right?
Yes, I can see the full screen. Maybe you can try your pointer. I can see
This is
your cursor.
actually a PDF, so I don't need a pointer. It's fine.
Okay, okay, that's good. Okay, thank you.
Okay.
Can I just quickly? Okay, thank you. So can you unshare? I'll just check with the 3 student contributed speakers.
Yeah, sure.
Yeah, thanks. So who's this person? Deepak. Deepak, you're around? Yeah, let me make him host. Deepak, Suman Mandal. Suman Mandal. Okay, all the 3 are made ghosts. So maybe Jagannath, you can hear us?
Yes, yes.
You have already tried, I remember. If you want to, you can go have a go once more.
Yeah. Yeah. Can you see my screen?
Yeah, it's visible.
Full screen.
Go ahead. Yes,
Fine,
it's
right?
visible. Yeah.
Okay.
Okay, thank you. So Suman Mandal, maybe you can give it a try.
I need to unshare it, right?
Yes, you have to unshare it.
Okay.
Okay.
Okay, let me share my screen.
It is the last
one. Can you see mine?
Yes, I can see its full screen. Maybe, yeah, I can see your cursor as well. Yeah.
Okay. And my talk is scheduled at 12, right? 12 on.
You just follow. I mean, there is a little bit of delay. Will start at 10. So you just your co-host, so your name will come up after Jagannath Sutradhar. You have the schedule with you, right?
Yes, yes.
Yeah. So just follow the schedule. I mean, the session chair will call out your name once the talks prior to your done. Okay. The only person left is Deep. So you can unshare your screen, please.
Yeah, sure.
Okay, thanks. Deepak, Deepak Singh Katiyat, you can hear us?
Hello. Am I audible now?
Yes, Mukul, you are audible. You are audible. I think only one person. The last speaker in your session, I made him. This person named is a contributor talk, Deepak Singh Katiyat.
Yeah.
So I cannot hear his audio. I made him a co-host. Other people have checked their screens, etc. Things are okay. So let's wait for a minute. We have 4 more minutes before we start.
Yeah.
So I think Deepak, let me just write to this guy. Where is this? ABC. This is, I presume, Deepak, but we cannot hear your audio, Deepak. Hello. I'm just writing to the speaker that you cannot hear him.
Sure. I think he is around, but like he probably.
Yeah, he is a co-host. He shared. Oi. Oh, sorry, I'm writing to you for some reason. Sorry about that. Chat with everyone in public doesn't allow me to do that. Hey, Ashish, এটা কি করে করবো? আটকে গেছে। No, I want to just write to this Deepak or write to everyone, but when I'm writing, it is going to Mukul for some reason. Ah, there. Okay, good.
क्या क्यों मसाला था पूरा था दे दो पक दे दो
देखो तुम वैसा नहीं रहे
No, he is around. We made him co-host. I mean, I think he shared his screen also, but his audio is not.
Are you waiting for me? I just went out and came back. Sorry.
Yeah, we'll start in a minute. This one speaker is having a little bit of audio issues. If it cannot be sorted, we'll anyway start in a minute. So Mukul, what do you think we should do? I mean, should we? I mean, the speaker is the last one. Maybe he will have a little more time towards the end.
I think he might sort it back on time. Maybe I would request him to log out and re-log in. Maybe that might help.
Yeah, let me just write it.
Maybe. Yeah. So I think if you can hear us, can you please also write if you can hear us or anything, what is your problem in the chat box to any one of us? So Deepak, we cannot hear you. Can you please log out and log in, and also can communicate through chat box if you are around?
Yeah, Mukul, I wrote to him the same things you mentioned. He hasn't responded yet.
So maybe he's not in front of his computer or something.
Possibly. So maybe we should start, and he's the last speaker. He'll have some time. We can probably sort it out then. How about that?
Yes.
Okay.
That is what I also think.
Okay, so everybody, let's welcome back to this pre-lunch session. So Mukul Kabir has kindly agreed to chair this session, and I turn it over to Mukul. So Mukul, it's yours.
Yeah. So thanks, Anamitra, for organizing this conference online. So in this second session, we'll have 5 talks, including 3 student talks. And the first talk will be given by Navneet Krishnan from IISc, and he will talk about phonons under extreme environmental conditions. So over to Navneet, you can share your
slide. I'll just share my screen.
Yeah. So maybe I will give you, I mean, once you are done with 20 minutes, okay?
Yeah, so you're able to see my screen, right?
Yes.
Okay, so thanks everyone for attending this talk, and thanks to the organizers for giving me the opportunity to present in this Young Investigator meet. So I'm Navneet Ravichandran. I joined as an assistant professor in Mechanical Engineering Department at IISc earlier this year. So today I will talk about a story of how we managed to go beyond the conventional first principles techniques to really identify very unique characteristics of phonons in strongly anharmonic materials under extreme conditions. So before IISc, I was a postdoctoral fellow in Boston College Physics Department, and before that I was a graduate student at Caltech. So a lot of this work that I will show today were funded by various fellowships and funding organizations in those places. Okay, so overall, I just want to start with an overview of what I and my group do for research. So we develop experimental tools, new experimental tools to probe the microscopic quasi-particle interactions in materials using non-contact optical experiments. So for example, here I'm showing a picture of the experimental setup that I had built at Caltech during my graduate study. So one of the main features of my lab is we do experiments that are theory driven. So we have in-house capability of predicting material phenomena ab initio without any adjustable parameters using density functional theory, and which includes some many-body effects. So we have developed in-house computational framework which can predict very interesting material physics, and we use that guidance to design experiments and look for novel material phenomena. So today I will talk about some of the findings in the theme of this workshop. I will talk about some of the findings from this first principles framework, which I primarily developed during my postdoctoral work. So this first principles framework, as I mentioned earlier, takes the conventional approach one step further. It goes beyond the conventional first principles approach. And using this advance, we were able to identify very interesting material properties, particularly phonon and thermal properties in the past few years. So for example, the work that I'm showing here is a prediction of a new material called boron arsenide, whose thermal conductivity was comparable to that of diamond. So diamond is known to be one of the highest thermal conductivity materials that occurs in nature. And we were able to show that this boron arsenide under certain conditions can actually have thermal conductivity above 1000 watt per meter Kelvin at room temperature, which is actually starting to compete with the levels of diamond. So one of the main features of this work is that by developing this unconventional first principles technique, we were able to accurately and quantitatively predict the properties of this material. Because this material was not available in nature, this helped as a theoretical guidance to the experimental colleagues who were able to grow this material and confirm our theoretical predictions. So I've also dug into more physics of this thermal properties of boron arsenide, and we found out or we predicted very unusual pressure dependence of thermal conductivity. So typically in materials that occur in nature, if you compress this material, thermal conductivity will monotonically increase with pressure. But in boron arsenide, because of this unusual behavior, the thermal conductivity is actually decreasing and doing various weird things with pressure. There is some experimental work ongoing to prove this behavior. And also we found that this unvented where higher order interactions among 4 phonons were explicitly included. This was found to be actually ubiquitous among a broad range of 3,5 compounds, as I have shown here. So we found that in several of these 3,5 compounds, we have to go beyond the conventional first principles framework to get agreement with the measured experimental data. And also we using this advanced technique, we were able to quantitatively again predict the effect of isotopic enrichment on the thermal conductivity of boron nitride. As you can see here, if you enrich boron nitride isotopically, you can actually achieve thermal conductivity exceeding 1500 watt per meter Kelvin, which is again puts it in an ultra high thermal conductivity regime. And finally, we have also worked on using this framework to look at the other end of the spectrum, where we look at low thermal conductivity materials, which are also strongly anharmonic, and try to predict the microscopic phonon properties as well as the microscopic thermal and thermodynamic properties as well. So this is a broad overview of what I have done using this first principles technique. So today in this talk, I will just focus on this last topic, looking at how phonons behave in a strongly anharmonic material like sodium chloride. So till now I have talked about going beyond conventional approach, right? So what is this conventional first principles approach? I'll just give you a quick primer on this approach. So in this framework, that is the conventional framework, we start with just the definition of the crystal geometry and also the potential or the pseudo potentials that the atoms in this crystal geometry interact with each other. That's it. With just that information, you can crank it through the density functional theory machinery and very accurately predict properties such as phonon dispersions and other phonon properties without any adjustable parameters. So you can also do things like you can predict the free energy of this crystal at different temperatures, and with that identify what is the stable crystal configuration by just minimizing the free energy. So for example, in the conventional approach, typically what is done is you calculate the electronic free energy using this density functional theory and add the harmonic phonon contribution to the free energy, and you get this quasi-harmonic free energy curve. And if you minimize this quasi-harmonic free energy curve at different temperatures, you get the ideal lattice constants or the lattice thermal expansion as a function of temperature. So you can get these thermodynamic properties. You can also look at phonon-phonon interactions driven by the anharmonicity in the crystal potential. For example, here I'm showing the scattering rates among three phonons driven by this cubic anharmonicity of the crystal structure. That is again within this conventional framework. And with all this information, phonon dispersions, scattering rates, and the ideal lattice constants, you can put them all together into a kinetic theory kind of expression shown here to get the thermal conductivity of any material. So the figure that is highlighted within the red box is one of the first works by my postdoctoral advisor, where he was able to quantitatively predict the thermal conductivity of silicon and germanium and achieve excellent agreement with the experiments. And all of these calculations did not have any adjustable parameters. You only have to start with the crystal geometry and the pseudo potentials with which these atoms interact. So it's actually a very predictive theory which has been used beyond just silicon and germanium. So here is a small list of materials where this conventional first principles approach, including quasi-harmonic approximation for the free energy and only three phonon scattering, we were able to obtain good agreement with the experiments on this large list of materials. But I guess the question at this point is this conventional recipe sufficient for all materials? Like, are there materials where this conventional theory is not enough and you have to advance this theory to predict properties of other materials? So I will show you one example, that is the example of sodium chloride, where this conventional recipe that I just explained does not work. And I'll talk about how we included these higher order effects to fix this issue of this conventional approach. So if you do a calculation that I just described, right, within the conventional approach, quasi-harmonic theory and three phonon scattering, you find that for the material sodium chloride, the thermal conductivity versus temperature that is measured is actually lying on top of this conventional prediction of thermal conductivity. But if I include this higher order 4 phonon scattering that I just briefly described, that is interactions among 4 phonons at a time driven by the quartic anharmonicity of the crystal potential, you see that there is a large discrepancy with the experimental data. So I just wanted to remind you that inclusion of this 4 phonon scattering was very important for the case of boron arsenide that I briefly described. But here, including 4 phonon scattering within this conventional theory is actually making the agreement with experiments worse. So this is one observation. But a more serious discrepancy is if you look at the phonon dispersion curves. So the figure on your right, I'm plotting the experimental measurements of neutron scattering, phonon dispersions through neutron scattering by this paper at the bottom. And you see that at 80 Kelvin, which is a relatively low temperature where anharmonicity is expected to be weak, you find that there is some discrepancy with the data. But as the temperature increases, the discrepancy becomes worse. So at 300 Kelvin, there's almost 0.5, more than 0.5 terahertz change, difference between the experiment and the theoretical prediction with this conventional approach. The same story also repeats it when you calculate the lattice constants. So this tells you that the free energy is also incorrectly predicted by the quasi-harmonic, conventional quasi-harmonic framework. So clearly from these three plots, it seems that the conventional theory is inadequate to describe both thermal transport and thermodynamics of this material, sodium chloride. In fact, this failure of this conventional approach for sodium chloride is tied to a more fundamental problem where we find that the assumption of this quasi-particle picture for phonons itself is breaking down. So typically, you say the quasi-particle is well defined if the total scattering rates divided by the phonon frequencies on the order of 1. So when scattering rates are much smaller than 1. So when scattering rates are roughly or much smaller than the frequency, the quasi-particles are said to be well defined. But you can see here that these scattering rates divided by omega are approaching 1 around 500 Kelvin. Right, so the melting temperature is much higher, like more than 1000 Kelvin for sodium chloride. But even at below half the melting temperature, the quasi-particle picture is breaking down within this conventional approach. So typically, if you see this kinds of failures of the quasi-particle picture, the approach we take is to look for renormalization. So here, as the temperature increases, the breakdown of quasi-particle is getting worse. Quasi-particle picture is getting worse. So it is somehow linked to the anharmonicity of the crystal structure. And typically, when you have these kinds of effects which breaks down quasi-particles, we look for some recipes for renormalization so that we can identify new well-defined quasi-particles with weakened interactions by including certain higher order diagrams. And that's what we did. So we developed a self-consistent phonon renormalization technique, which builds in higher order anharmonicity into the definition of the quasi-particles to achieve well-defined phonons. So I'll very briefly describe how this self-consistent renormalization works in somewhat qualitative fashion. So in the conventional approach, that is the quasi-harmonic approach, what we do to calculate the phonon properties is to take a supercell of atoms in the crystal, freeze them at their equilibrium position, and displace the atoms one by one from that fixed equilibrium position to calculate the force constants. So, for example, second order force constants are calculated by displacing 1 or 2 atoms at a time from this periodically arranged frozen structure. And in the quasi-harmonic case, because we are minimizing the free energy at different temperatures, we calculate the force constants by freezing the structure at lattice constants corresponding to different temperatures, right? But in reality, if you look at, if you zoom into a real crystal, right, all of these atoms are not going to be sitting at their equilibrium positions. There's going to be thermal displacements of atoms. And what the self-consistent renormalization says is that the actual harmonic force constants that the atoms face has to take into account the thermally displaced environment that the atom sees. So in effect, we have to look at, instead of having just the single derivative, we have to take a thermal average of the derivatives across several thermally displaced snapshots. So the average basically is an average across different thermally displaced snapshots of atoms. And that should be the effective second order force constants that these atoms face. So if you do a Taylor series expansion, you can see that the renormalized force constants are actually just the quasi-harmonic and the bare force constants, plus a correction term, which depends on higher order force constants, in this case, the fourth order force constants, and the thermal displacement correlations, which takes into account the thermally displaced environment that the atom faces. So more details can be found in these two papers. If you want to have a mathematical description, so this renormalized force constants are created by renormalizing the free particle phonon propagator with loop diagram in a self-consistent manner. Okay, so we have developed this renormalization scheme. Now let's see if it helps with the agreement of the experiment. And as you can see in these plots, both at 80 Kelvin and 300 Kelvin, the agreement is now much improved with the experiment using these renormalized phonons. So the solid lines are the new renormalized phonons and the dashed lines are this conventional quasi-harmonic phonons. We can also, since we have all the phonon properties, we can actually now go ahead and calculate the lattice constants also as a function of temperature. So here in this work, we have included the contributions to free energy from the electronic part, which is phi naught, the harmonic part, which goes into the quasi-harmonic picture, and also these higher order terms from the fourth order potential and the third order potential. And with these inclusions, for example, you can see that there is a large variation in the curves. The red curve is this current fourth order free energy, and the dashed curves are the original conventional bare quasi-harmonic free energies. And you can see as the temperature increases, the curves move far apart. But more importantly, with this new renormalized and fourth order accurate free energies, we are able to get excellent quantitative agreement with the lattice constants as well. So the dashed lines are the original quasi-harmonic thermal expansion curves that I showed, and the solid lines are now with this renormalized phonons. And you can see with experiments, these phonons are capturing the thermodynamics very accurately. So before we go into looking at results for thermal conductivity, so thermal conductivity is calculated using the Boltzmann transport equation. So the definition of quasi-particle, that is the well-behaved nature of quasi-particles, becomes important. So let's see if that issue is also fixed, whether we are now getting well-defined quasi-particles using this renormalized picture. So just to refresh your memory, these were the scattering rates divided by phonon frequency plots for the bare conventional phonon picture. And when I compare it with the renormalized phonons, you can see that gamma or omega is now significantly below 1 for most of the phonons in the problem. So now this plot shows that the renormalization creates nicely defined, very sharply peaked quasi-particles, which can be used in a Boltzmann equation kind of framework. So in this work, we have calculated the thermal conductivity by iteratively solving the full Boltzmann transport equation. By full, I mean both, including both 3-phonon and 4-phonon scattering processes. So this is a familiar relaxation time approximation, which gives you the scattering rates for these two processes. And since we are doing an iterative solution, the equation is far more complicated. But I guess the key takeaway point is, by solving this equation, we get the total transport lifetime, including both 3-phonon, 4-phonon processes for each calculation. And from that transport lifetime, you can calculate the thermal conductivity. So just a minute, I wanted to just emphasize how computationally challenging these higher order scattering rates are. So typically, as I showed earlier, to get the scattering rate calculation complete, we have to do two things. The first thing is to count the number of scattering channels that satisfy conservation. So these are the constraints that are coming in both from the translational invariance of the crystal and also the Fermi's golden rule. And after we have a list of allowed scattering channels, we have to calculate the strength of these scattering channels. So these are the two tasks that we need to do effectively to calculate the scattering rates. In the conventional picture, where 3-phonon scattering is only considered, typically for a reasonably converged calculation, we have to do about 100 million or 200 million events which satisfy these constraints. So we have to calculate the strength of these many events and store them so that we can use in the Boltzmann transport equation. So if you have 200 million events, it roughly comes out about 150 gigabytes of storage, which you can typically nowadays do on your desktop computer or even a single node on the cluster. But by just pure combinatorics, you can see that the number of allowed scattering channels goes up by 4 orders of magnitude. And similarly, the corresponding storage also goes up by a large amount.
Navneet, you have 5 more minutes, including questions.
Sure, yeah. So this says that this calculations are really challenging. But if you look at the details in the papers that I showed earlier, we have included a lot of symmetries in the matrix elements and also implemented some hardware acceleration to bring down the calculation time significantly. And with that calculation, with that improvement in the calculation time, let's see if we are able to get agreement with the experiment in this new renormalized framework. So here I'm showing, just refreshing your memory of what I showed earlier. The conventional picture predictions of thermal conductivity. The dashed line is the 3 phonon calculation and the solid line is 3 plus 4 phonon calculation. Now, if I plot the renormalized values, you see that the solid line, which is having both anharmonic renormalization and the 4 phonon higher order scattering processes involved, is getting very close to the experimental data. So the first conclusion is that 4 phonon scattering rates included with the calculation of the renormalized transport matches well with the experimental data. And the 3 phonon scattering, that is the dashed line, is actually having higher thermal conductivity, which means the scattering is getting weaker in the renormalized picture. So that makes sense, right? So when you do the renormalization, the intent was to create new quasi-particles with weakened interactions. And with the 3 phonon picture, you can see actually both with 3 phonon and 3 plus 4 phonon, you see thermal conductivity has gone up. So the interactions has become weaker. But the elephant in the room is somehow the solid red curve is actually lying on top of the dashed black curve. So the renormalized 3 plus 4 phonon calculation is actually lying on top of the original quasi-harmonic calculation, excluding 4 phonon. So why is that? And it turns out it's actually due to a very beautiful cancellation of errors that happens, particularly in sodium chloride. So it's actually related to the fact that in the bare phonons, that is the conventional picture, TO phonons actually coming out to be softer. When you have the optic phonons softer, their phase space of scattering with the acoustic phonons will go up under the 3 phonon picture. So the fact that these optic phonons are softer additionally creates more 3 phonon scattering, and that kind of tries to mimic the higher order 4 phonon scattering in a very fortuitous manner. So this nice cancellation of error, we have searched through a large catalog of materials and doesn't happen in other cases. So it's actually very unique to sodium chloride. And in fact, what we found is that in the case of sodium chloride, in the bare phonon picture, that is the unrenormalized conventional picture, all phonons undergo very strong softening with temperature. When I take a temperature from 100 to 600 Kelvin, the frequencies soften a lot in the first plot. But in the renormalized quasi-particle picture, there's almost no softening. This is also something very unusual. Usually materials undergo a very strong softening with temperature, but in the case of sodium chloride, we are predicting there's almost no softening. And in fact, this is actually in a quite good agreement with the experiments as well. So in the third figure, I have plotted the measured phonon frequencies at the gamma point as a function of temperature. And you see that our predictions are actually lying on top of data for both acoustic and optic phonons. And we have also done some dummy checks in the sense that if you take a weakly anharmonic material like diamond, the effect of renormalization should be minimal and on both thermal and thermodynamic properties, and that's what we find. In all of these 4 plots, you cannot tell the difference between the renormalized and the conventional phonon calculations. So to summarize, I hope I have shown that in the case of sodium chloride, the effect of higher order corrections to both free energy and also the definition of phonons themselves is important to get agreement with experimental data for both thermal and thermodynamic properties. And we have shown that this kind of unified self-consistent phonon theory works well for both weakly anharmonic and strongly anharmonic materials. So it's a single recipe for the entire spectrum of materials for phonon properties. So thanks for your attention. I will be happy to take any questions.
So the floor is open for maybe one very quick questions. If there is no question, then I will ask one question. So, so Navneet, it's a very nice talk. And is there a way to also incorporate phonon impurity scattering in your?
Yeah. So actually, when I showed this, I skipped out the phonon impurity part. There's also a phonon impurity term here. For the thermal conductivity, we can definitely include it either using the Born approximation, which is the lowest order, or we could also include some kind of a T matrix approximation, which includes higher order corrections. That is for the phonon scattering rates. If you do the T matrix and take the real part, it also gives you some kind of renormalization of phonon frequencies themselves due to impurities. That can also be done.
I see. Thank you. Okay, so let us thank Navneet for very nice talk on phonon. Okay, and we can move to the next talk.
Yeah, thank you.
So Avdesh, so next talk is by Avdesh Narayanan from IISc again, and he will be talking about controlling exceptional points using lights. So Avdesh, are you around?
Yeah. Hi. Mukul,
yeah,
thanks.
please. Yes.
So I'm just trying to share my screen now.
Yeah, sure.
Yeah. Okay, can you see my screen?
Yes. Yes.
Is it full screen?
I think so. Yes.
Yeah, and can you also see my cursor? Thanks.
Yeah, I can see your cursor, but there is this green squarish thing on your screen. I mean, I don't know.
Now?
Yeah, no, not now.
Okay.
But it is probably not full screen again.
Aha, I see. Okay, maybe yeah. I think I can proceed this way maybe.
Yeah, sure. So I'll knock you at 20 minutes.
Okay, thanks.
Yeah, sure.
All right. Thank you, Mukul. So let me also start by thanking the organizers for organizing this really nice meeting and for giving me the opportunity to present our recent work. As you can see, I'll talk about controlling exceptional points using light. And so let me start by acknowledging people. So the work that I'm going to present is mainly driven by Ayan Banerjee, who is a PhD student in my group. And we have an active collaboration with Debashri Chaudhary, who is at IIT Roorkee. And we are also working with Rimika Jaiswal, who is an exceptionally talented undergraduate student at IISc. And I'm supported by a startup grant at IISc and DST SERB. So here are the references that the talk is based on. So you can find many more details there. So the first question that I'll try to address is that why do we want to study non-Hermitian systems, which is where these exceptional points occur. So of course, as we all know, that quantum mechanics postulates self-adjoint operators, which are represented by Hermitian matrices. So why would or how would non-Hermiticity occur? So one kind of useful way to think about non-Hermiticity or non-Hermitian Hamiltonians is to consider them as effective Hamiltonians of a smaller system, which is embedded in a larger one. So what then can happen is that such some smaller subsystem, due to its interaction and gain and loss of particles with the rest of the system, the Hamiltonian for this subsystem can become non-Hermitian. So and if you think about it, these non-Hermitian Hamiltonians are actually pretty common. For example, they can occur in photonic systems where there might be injection or loss of photons in these systems, and you can get effective non-Hermitian Hamiltonians. Also in a more conventional transport setting, where you have, for example, a scattering region of interest and you attach it to two semi-infinite electrodes, then typically one describes these electrodes by self energies, which are in general complex. So again, the effective Hamiltonian for this system becomes non-Hermitian. And also in interacting systems, as we nicely saw in the last talk, if you have electron-phonon interactions or electron-electron interactions, then there are quasi-particles, and these have an effective lifetime. And these lifetimes can then be described by Hamiltonians, which are non-Hermitian in general. So so these in the recent few years, last let's say 3 or 4 years, there's been growing interest in trying to combine these non-Hermitian or open systems with the notions of topology. And this combination of topology and non-Hermiticity, in fact, gives you several unique features. So let me just quickly remind you about what are called symmetry protected or topological systems. So one of the cornerstones there is what is called the bulk boundary correspondence. So what this essentially dictates is that if you know about the bulk topological invariant of a topological system, then you can essentially predict everything that is going on at the boundary. So just an example, if you consider a time reversal invariant topological insulator, the band diagram is shown here, taken from this really nice review. Then if you calculate the Z2 topological invariant of this system from the bulk, then you can exactly tell someone that, okay, at the surface, these are how many topologically protected surface states that you're going to get. But in contrast, in non-Hermitian systems, what you might get is, in addition to a state, edge state localized or surface state localized the surface, it might happen that a majority of the bulk states can also localize in the same way. So in the inset here, you see there are a number of states that are localized at one of the edges of the system. So this conventional bulk boundary correspondent in fact breaks down. And how to describe this or how to extend this notion to non-Hermitian system is a very active topic of current research. So going forward, another very intriguing aspect of non-Hermitian topological systems is the presence of what are called exceptional points. So what happens at these points is that the Hamiltonian becomes what is called defective. So not only the eigenenergies, they become identical, but also the eigenvectors at these points become identical. So let's look at this simple example to understand what are these exceptional points, because that's what the talk will focus on. So if you consider this very simple 2x2 Hamiltonian, you can see if alpha is not equal to 1, then clearly the Hamiltonian is non-Hermitian. So one can just diagonalize this very simply and find out the energy eigenvalues, which are given by plus and minus square root of alpha. And in general, for a non-Hermitian system, your left and right eigenvectors need not be the same. So one can also calculate the right eigenvectors, which I denote by psi r here. So you can calculate very simply, and you will find that this is this column vector plus minus square root of alpha and 1. Now, as you can see, if you approach alpha equals 0, you'll see that the energies are, of course, becoming equal to 0, both of them. But at the same time, your right eigenvector also becomes the same. So both the eigenvectors are now 0 and 1, 0, 1, right, the column vector. So that means that they don't now span the full Hilbert space. And in that sense, the Hamiltonian has become defective. And this notion of if exceptional points was first pointed out by Cato in this very, very influential treatise back in the 60s. And then subsequently, there have been a number of nice reviews and papers discussing the properties of these points, some of which I list here. So at the same time, while these features are being explored, there has been a tremendous advance, especially in experiments, in using light to manipulate quantum matter. And this field is called Floquet engineering. So there are a number of very, very interesting experiments that have been done in the field. I'll just focus on two of these. So on the left, I show you this really nice work from the group of Nu Gedik at MIT, where they showed they were able to experimentally measure Floquet block states, which are basically analogs of block states when you are driving the system with light. So what they did was they took bismuth selenide, which is the canonical time reversal invariant topological insulator, and they applied a light pulse. And by doing time resolved and angle resolved photoemission spectroscopy, they were able to get these really nice images of these. So this is the single Dirac cone that one begins with. And then you can see all these copies of the Dirac cone that arise, which are the Floquet states. And when the pulse ends, then you get back your single Dirac cone. So that is a really nice example of how you can actually use Floquet engineering to manipulate these topological states. And another more recent example, this is from the group of Andrea Cavalieri at Hamburg, where they took graphene and applied circularly polarized light, and they were able to measure the anomalous Hall effect arising because of light. Not quite quantized yet, but still anomalous Hall effect. So then the question that we ask is, we are looking at these very interesting properties in non-Hermitian systems. And then there is this exciting idea of using light to manipulate quantum matter. Can we combine these two and use light to somehow manipulate these non-Hermitian systems? So how do we do that? So the way to theoretically tackle this problem is well established by now. This is something called Floquet theory. So this is a very general formalism to treat time periodic systems. So let's take our system, which is described by this Hamiltonian h t plus capital T, where t capital T is a time period, and it goes back to the original Hamiltonian h of t. So it's periodic with the time period capital T. So the central idea is to expand the wave function of such a system in the Fourier components in the multiples of the driving frequency, omega, which is given by 2 pi over t. And as you can see this expression, this looks very familiar to that of the Bloch expansion, right? The Bloch theorem that one typically uses in when you have a periodic lattice in space, right? And when you plug this in and do some algebra, you actually end up with a time-independent eigenvalue problem, where the eigenvalue equation is of this form. These epsilons are called Floquet eigenenergies, and the matrix elements of this Hamiltonian HMN are given by integrals of this form. And you can go one step more and simplify even further in case you are dealing with large frequencies and you are not in the resonant limit. So you're not tackling resonant excitations. In that case, you can actually do what is called a Floquet-Magnus expansion, where your effective time-independent Hamiltonian is given by your H0, which is your bare Hamiltonian without the presence of light, and then commutators of this form, where these H minus 1 and H plus 1 are Fourier components of your full time dependent problem. They're given here. And omega is a frequency, and then you can do up to as many orders as you like. So I've truncated the series here at the first order in 1 over omega. You get higher order 1 over omega square and so on. And the results that I'm going to show you next are all based on this. Although we have already also checked with the full this time independent full eigenvalue equation as well, and we get very similar results. Now this as I presented was for Hermitian systems. Does this work also for non-Hermitian systems? It turns out that it does, and it was shown in this really nice and insightful paper that earlier appeared this year. That this same formalism, in fact, also the rest of the linear response formalism also follows through in an identical way with non-Hermitian systems. So, so the plan for the remaining part of the talk would be the following. I'll show you 3 different examples of non-Hermitian topological systems and show you how one can engineer and control exceptional points using light. So the first example that I want to show you is that of a non-Hermitian nodal line semimetal. Many of us are familiar with Hermitian counterparts of nodal line semimetals. These are just kind of a topological semimetal where the bands touch or intersect at in a line instead of a point. Right. So this first part of this Hamiltonian describes a typical Hermitian nodal line semimetal where this M and B control the band inversion, which denotes the presence or absence of the line nodal degeneracy. Sigma or the orbital other pseudo-spin Pauli matrices. V is the group velocity, Q's are the momenta. And in addition, to make this non-Hermitian, we have added a term I gamma sigma z proportional to the z component of the Pauli matrix. As you can see, this term makes the Hamiltonian non-Hermitian. And physically, one way to think about it is just like adding or subtracting particles from the 2 orbitals. So if you look at the band structure of such a Hamiltonian, of course, now you have both real and imaginary parts of the energy. So the real part looks like this. You have, instead of a degeneracy along a ring, you actually get a degeneracy along the annulus of a disk, right? So the bands are stuck together in this region. And within the same region, the imaginary part is finite and it's 0 outside everywhere else. And it turns out that the exceptional points lie along these 2 circles, which bound the region of band coalescing. So we go ahead and apply Floquet theory under high frequency approximation. I won't show you the details, but effective Hamiltonian at the end turns out is of this form. And this last term here is what is contributed by light. So here E is the electronic charge, eta is the polarization plus or minus 1. AY and AZ are the amplitudes of light along the Y and Z direction. Sin phi controls the polarization, so phi equals 0 or pi for linearly polarized light, and pi over 2 for circularly or elliptically polarized, and omega is the frequency. So you can see that this term is 0 if you have linearly polarized light, On the other hand, it is maximal for elliptically polarized light. So now what we are going to do is we are going to take a cut along the QX direction and start to look at the position of the exception points. We'll come back to what happens for the full 3D case a bit later. So for this problem, we can analytically calculate the position of the exception points, which is given by this expression here. And now zeta we define in this way, which is the term that controls the light intensity. And we have set AY equal to AZ equal to some A. Now we're going to characterize these exceptional points by a topological invariant that is specially designed for non-Hermitian systems. It's called the vorticity. It is defined in this way, nu mn of gamma, where that we have two bands, EM and EN, which are in general complex. So they have this representation, and theta L is the angle involved. And you take the argument of these complex numbers, take the gradient, and then integrate over a contour labeled by gamma. And the theory is that if you have your exception point within the contour, or if you have an odd number of exception points, then this vorticity is finite and characterizes the topology. So let me show you what happens for this particular system as you increase the light intensity. So the top panels here denote the position of the exceptional points in the momentum space, and the bottom panels are the vorticities. And from left to right, you are increasing the light intensity. So the leftmost plot is without any light, and the rightmost plot is the highest intensity. So you see here, there are two pairs of exceptional points as you're looking along a cut in the QX direction. And you have the bands, as you look at the vorticity as a function of theta, you see that the two bands cross each other, and then they exchange as you go along. And we are choosing our gamma to lie such that we are integrating over this particular exception point. And now we start to increase the light intensity. You see that the exception points start to come closer together, and eventually they meet. And since they have this opposite vorticity, they annihilate. And you see that the bands, the vorticity plots, they don't cross each other, and we see that the topological transition has occurred, and we have lost the exception points. And you see that the positions actually move off the real Q, which means that they don't exist anymore. This is just a representation of that fact. So we have found a platform where we can actually destroy and move the exceptional points using light. So what happens under open boundary conditions? We have also examined that. So here I show you the absolute value of the energy without light and with light as a function of momentum. So we have opened the boundaries along QX. And there are two features to notice. One is this zero energy edge mode lying between pi over 2 and pi. And there is this higher order exceptional point where all the bands actually coalesce at finite energy. So with light at sufficient values of intensity, we find that we can actually destroy both these features. So now here, for example, the bands are actually not degenerate, and this zero energy edge mode has also moved off the zero energy and is no longer localized strictly at the edge. Okay, so that was destroying exceptional points. The next question that one might ask is, can one also create these? So the answer turns out to be yes. For that, I show you the next example that I have here, which is a non-Hermitian Dirac semi-metal. Again, many of us are, or most of us are familiar with Hermitian Dirac semi-metals, which graphene is a very common example. You can also get these in 3 dimensions. Cadmium arsenide and sodium bismuth are very famous examples of these. So the typical Hamiltonian that one uses to describe these 3-dimensional Dirac semi-metals is written down here. So here, this term is not that important. Again, taus are pseudo-spin Pauli matrices. M of k is the crucial term which dictates whether you get Dirac points or not. It controls the band inversion. Then this is a term linear in the momentum. And we have added, to make this non-Hermitian, we have added a term proportional to tau z of the form I gamma. Again, gamma is a real number, and I gamma together makes it a non-Hermitian. So as before, we apply Floquet theory under high frequency approximation. And this is the term that we end up with for the effective Hamiltonian. So this last term written in the lower line is the one that is coming from light. And we have here taken a circularly polarized light to begin with. So what is happening here? So we start off, again, I show you the band structure here. Top panels are the real part of the energy. Bottom panels are the imaginary part. And from left to right, we are increasing the light intensity. So back in this Hamiltonian again, I mentioned that this M of k is actually what controls whether we get a Dirac point or not. So we start off with by a choice of M of k such that we don't have Dirac points. So if you look at the real part of the energy, you don't actually have any Dirac points. It's just a normal, usual gapped semiconductor, if you like. And the imaginary part is gapped as well. And now we fix our M of k and also the non-Hermitian term, gain and loss term gamma. And the only thing we change is the light intensity. So you see what happens as we move with increasing light intensity, the band gap starts to close both in the real part and in the imaginary part. And eventually at large enough light intensities, there have band degeneracies have been introduced. And you see that they lie along this part and this portion of the band structure. And the endpoints of these band degeneracies here and here and here and here are actually the exceptional points. So we have managed to create exceptional points using light where there were none. And the imaginary part shows this typical exchange behavior whenever you get these exceptional points. So we have another example where we have actually managed to create exceptional points using light. So this last example here, which shows what one can do in a higher dimensional case, where one has, instead of exceptional points, one has exceptional contours, which are like a surface of exceptional points or a line of exceptional points. So for this,
Avdesh, you have 4 more minutes.
Okay, yeah. So let me basically skip the details. But what I want to tell you is that we have an example of what is called a multi-wile semi-metal, which is which is a system which has band crossings which may be linear, quadratic, or even higher order. So if you have such a system and you introduce a non-Hermitian gain and loss term of this form here, and as usual, we apply our standard flow K theory under high frequency approximation. So what happens to the Fermi surface or the exceptional contours? So that's what I show you here in the QX, QY, QZ plane. Left to right again is no light, then increasing light intensity. The blues contours are the real part, and the red contours or the pink contours are the imaginary part. Their intersection actually defines what are the exceptional contours of the system. So you start off with something that is elliptical, and as you increase light, you see that there's a pinch off that develops, and eventually these two split off. So this is for a double wile semi-metal, which has a big has a topological charge to start off with of 2, and we have managed to use light to actually split these two contours and split off also the topological charge into +1 and +1. And we have characterized this by a non-Hermitian version of Berry curvature. Okay, let me skip over this and just briefly tell you about possible experimental realizations that where our proposal might be tested. So there are a number of platforms that might support this. I highlight just 2 here. The first is this helical waveguides, where you have these waveguides fashioned in a helical manner, and this helicity actually provides an analog of the Floquet driving. And the way to introduce non-hermeticity is actually introduce breaks in the waveguide, which leads to loss. And very recently, this setup has been used to generate non-Hermitian wile points or wile semi-metals in this reported in this very nice paper. Another platform is a more conventional one, where according to this theoretical proposal, if one takes a ferromagnet and a topological insulator, at the interface, one is able to generate non-Hermitian exception points. And our proposal is that if you irradiate this with light, one might be able to test our ideas. So with that, let me end and just show you the summary. So the main takeaway message from the talk is that using light or driving, one can have quite good control over exceptional physics in non-Hermitian systems. And I showed you 2 or 3 examples where we have shown that one can control, create, move, and destroy exceptional points. And you can find many more details in these 2 references that I list here. So with that, let me end, and thank you very much for your attention.
So Avdesh, very nice talk. So the floor is open for few questions.
Yeah, I think Sumilan has.
Avdesh. So Sumilan here. So I just to add one technical question. So generally in this non-Hermitian, when you write the time evolution, you get this non-Hermitian term like anti-commutator or something, right?
Right.
So you include that when you do Magnus expansion?
Yes, we include that. Yes.
Okay. Okay.
Yeah.
I see. Yeah, that's yeah.
Any other questions? Yeah, sure. Please go ahead.
Yeah, so I just had one question from your intro part about the non-Hermitian skin effect.
Right.
So is that true in all kinds of systems or only photonic systems?
No, in principle, so you mean this one, right? The one where you get a lot of states localizing at this one, do you mean?
Yeah, yeah.
Yeah, so in principle, I mean, this is just a model study. So this is just takes a particular model and then it's a theoretical study.
Right.
So it should be possible to observe it in any platform where you can actually generate non-Hermitian physics. So not necessarily photonics.
I see. I see.
Yeah.
And what's the reason behind this effect?
Oh, so the reason, okay, one very simple way to think about it is that let's imagine just a chain of atoms, right? 1D chain.
Mhm.
Okay. So if you have a Hermitian system, then your left hopping and the right hopping are equal.
Mhm.
Right?
Right.
Now, what you can do is if you just shut off one side of the hopping, right? Let's say you hop only to the right and not to the left.
I see.
Then you have turned into a non-Hermitian system.
Okay.
But you can imagine that if you have only a one-sided hopping, all the particles are going to end up at, let's say, the right edge.
I see.
No matter what is their energy dispersion, right?
But they are still time independent not states.
Yes, yes.
I see. Okay, okay. Thank you.
Yeah.
Mhm.
Okay. Is there any other question? If not, I can quickly ask one.
Yeah, sure.
So I was wondering, Avdesh, I mean, what will happen if you, I mean, do the similar light interaction with the Hermitian systems?
Yes, that's a very good question. And actually, this has been, sorry, I did not mention that there have been a number of theoretical studies doing that. So essentially, if you look at this picture here on the left, where I showed you this experiment from the Geddick group at MIT. So people have been able to model this, both using model calculations as well as some kind of extension of DFT, what they call Floquet DFT. And they have been able to model these kind of Floquet block bands and actually calculate conductivities and so on.
I see. Very nice. Okay, so if there is no other question, please let us thank Avdesh again for the very nice talk.
Thank you very much.
So
I'll stop sharing now.
Yeah, sure. We can move to the student presentation. And the first one is by Jagannath Sutradhar, is from IISc. And we'll talk about localization length in Fock space. So yeah, here you are.
Can you see my screen?
Yes. So please go ahead. Yeah.
So
I'll remind you when you are 10 minutes down.
Yeah. Okay. So a little bit change in the title because the project is in progress and we are continuously evolving our understanding. So instead of localization length, we are calling it a length scale in the Fock space, which is able to detect the MBL phase and the universal classes of random and quasi-periodic system we have found. So the work has been done with these people. So let's begin with the, let's begin with the clean lattice system where we have only this tight binding term. So here the states will be delocalized with some system size L throughout the system. Now, if we include disorder in the system, the same lattice with disorder, then the states can be localized with some localization length psi. So this is called the Anderson localization, and the disorder mainly studied in this area are two types. This random disorder with some the on-site potential you take from some random uniform distribution randomly, and the other type is this quasi-periodic potential where you have some periodic potential with some irrational number in the argument such that the potential is deterministic but not repeating. So, and this, remember this parameter W, which is the potential strength controlling the here the on-site potential. So the non-interacting picture is this: from delocalization to localization, you get a transition with the disorder strength. Now, if we include interaction, so the interesting part is this phase. What happens to this localization, whether it survives or not? So there has been many studies, theoretical and numerical, which shows the localization still survives, and that is called the many body localization, or MBL. So I have shown some of the literature diagrams. So the picture is here with the disorder strength, the delocalization to many body localization transition occurs. But there are many questions to answer. So the one of them is the stability. So the two types of potential that has been studied are the random and quasi-periodic. And in the random case, in the thermodynamic limit, there is a probability of getting what is called rare thermal region. That means few of the on-site potential will be close to each other, that they can resonance and make this region locally thermal, and which can destabilize this many body localized phase. But in the quasi-periodic case, that cannot be the case because the potential is completely deterministic. So this also says that there can be two different mechanisms for this transition in this random and quasi-periodic cases. So the nature of the transition is also not settled. So some says it to be continuous, some says it to be a KT type transition, and the universality class between this random and quasi-periodic model also are different, and there are different types of flow possible from this random to quasi-periodic model, and there are debates about it, which one is true. And the MBL phase mainly to the transition happens in the Fock space, but the real space parameters to the Fock space transition is not very clear. And the main problem of this numerical studies is the numerical calculation, if you want to do by exact diagonalization, is limited by small system size, which I will briefly tell why. So let's consider this Hamiltonian. I will represent this Hamiltonian in the number basis. So the number basis is like, let's say there are 6 sites where we have 3 particles. The red one are the particles, and these are empty sites. Now you can interchange the empty sites and the particle, and you can construct the full basis to describe the system. So this is one example of the full basis states. So here, this basis is the number occupation basis, and these two terms is also number operator. So they will give a diagonal term in this basis, and this term will generate the hopping between different basis states. So this term will give a hopping where I and j are the basis in this this Fock space. So this is a simple tight binding model, looks like a simple tight binding model, but here you can see the connection statistically goes extensively with system size. So that is a problem. And the other thing is the dimension of this Fock space grows exponentially. So for the half filling case, the dimension grows for 22 lattice sites, it's around 700,000. So that is very difficult to handle numerically. So, but our focus is here, the Green's function. So that is the propagator in this space, which connects the propagator connects between different sites in time. And we are looking at the frequency space of the frequency Fourier transformation of this propagator, which is defined this given some small imaginary number. So this contains the information of localization because it relates to the time evolution of some states to other. But because of this matrix is very large, it not easy to invert. So, but our interest is here various diagonal and off diagonal term, which will also capture the essence of this full Green's function. So instead of doing the full Green's function, full Hamiltonian inverting, we'll use the iterative method, which also provokers discussed yesterday. So the method is given some part of the space, let's say I'm calling it each layer to be some slice, and given some Green's function of the slice, we can include another slice to this space, and we can calculate the Green's function given the earlier Green's function. So this is the iterative method, and we can update the previous Green's function as well. And we can keep on iterating the same thing, and we'll get all the Green's function. I'm showing it for the diagonal terms. So in this process, the maximum dimension we need to invert is the dimension of the middle slice. So you can see here the dimension of the middle slice, here it is around 18,000, where it was for the full inversion, it was 700,000. So all our results I will show for these parameters. And coming to the results. So given this Hamiltonian, we can define the diagonal element with respect to the self energy, where this term coming from the diagonal part of the Hamiltonian, let's say for some sites I, and all the self energy is coming due to the presence of all other sites. So from the self energy, we can extract the imaginary part of the self energy, which is the inverse lifetime. So because this is compared to the inverse lifetime, it is important because in the delocalized phase, this lifetime is finite, but in the localized phase, this lifetime goes to infinity. So this has been shown that this distribution of this inverse lifetime will be log normal on the delocalized phase, and some particular distribution called Debye distribution with some distinct tail. So that we have seen considering this diagonal term only within this middle slice, to be matching quite well with the tail and the log normal distribution, both the delocalized and the localized side, both for quantum and quasi-periodic and random case. Now, if we look at the typical values of this distribution, so the typical values here I have shown, the typical values shows a crossing here and able to distinct between the phases of this localized and this extended phase. So both for the quasi-periodic and random case, here I have shown the crossing points, which is shifting with the system size. That is like the level spacing ratio, which has been started to detect the MBL transition. So this is one thing. Now, if we consider the off-diagonal element from this Green's function, so the off-diagonal elements contains the non-local spatial information, unlike all the studies which has been done for the spatially locally in the Fock space. So deep in the MBL phase or in the infinite disorder, we know this has to be true. Green's function between I and J, when these two sides will be different, will go to 0. And our numerical studies inspires us to take a scaling of this Green's function like this, exponentially suppressing with some distance called distance Rij, which is called the Hamming distance between two sides I and J. And
you have 2 more minutes.
Okay, thanks. And this Ji is defined, given this scaling form, we can define this Ji to be like this with respect to the system size. Two things you can clearly see in the delocalized phase, since the Hamiltonian will mimic a random matrix, so this Gij will be independent of the system size. So this length scale will be almost proportional to system size. And in the deep in the MBL side or in the disorder limit, so this Ji should go to 0. So these two property we can be certain. Near the critical point, what happens, that is we will see. So if we look at the typical values of this length scale with respect to disorder for the random case and the quasi-periodic case, and we are taking these first sides, the I sides, the topmost side, and the J from all the sides in the middle, and we are taking disorder average. So the typical value with disorder shows a crossing, and on the delocalized side, we see the localization length increases with system size, but on the other side, it decreases with system size. We have gone up to system size here, L equals to 20. And similar for the quasi-periodic case, where there is little bit fluctuations, but similar the story you may say. So we can do the finite size scaling with this functional form, where this is a critical point and this is critical exponents, and this is the results we got here. So I'll show you the scaling collapse. So let's first look at the insets. So both for the quasi-periodic and random case, here the scaling collapse has been shown, and you can, if we look at the variance of this Ji, which is the most striking fact here, so the variance shows completely different behavior in the two cases, which led us to conclude that there are two universality class, because this new the scaling collapse gives this random exponent to be greater than the quasi-periodic exponent, and the difference in the variance, which is clearly shown here. You can see this difference more clearly if you go to the distribution of this quantity. So in the distribution, you will see many non-monotonic behavior in the quasi-periodic case, whereas in the random case, it will be smooth. So the same features appear if we look at other off-diagonal terms as well. So here my conclusion: we have implemented the iterative method in the Fock space to calculate Green's function system size up to 22. From this thing, we have calculated this part, and from the non-diagonal element, we have defined a length scale between two sides I and J, which is able to detect the phase transition. And one thing we have noticed that the diagonal part, which is the special locally, the critical point we extracted from it always smaller than the off diagonal part, where the critical point we have extracted. That means it contains some more information, non-local information, which we have to look more carefully. And finite size Calling collapse produces new random greater than new quasi-periodic, which led us to believe that they belong to two different university classes. Thank you.
Very good. Thanks, Jagannath, for the nice talk. The floor is open for maybe one very quick question.
May I ask just very small point? I just wanted to ask how you are taking the quasi-periodic potentials. Like, how are you placing them in the system?
Oh, that is in the real space.
Real space, but how are you implementing the periodicity? Like there are.
Oh, no, I am not. I am using free boundary condition.
Okay. Thank you.
Can I ask a quick question, if there is time? Jagannath, thanks for a very nice talk. So I just wanted to ask, in this quasi-periodic potential case, so the critical disorder actually also depends upon the irrational number that you use in the quasi-periodic potential, right?
Yes.
So have you seen whether this exponent nu you have calculated, how it depends on that irrational number?
No, actually we have fixed that to be a golden ratio.
That I saw, but I'm just asking, like, in case there is more data which you have not discussed here, or if you have some.
No. We have till now we have not changed that. We have kept it constant.
Okay. Thank you.
With the interest of time, let us thank Jagannath again, and maybe we can proceed to the next talk by Shuman Mondal from IIT Guwahati. We'll be talking about topological inheritance in half SSH Harvard model. So it's over to Shuman.
Yeah, sure. I think you have not enabled my sharing capabilities. I can't share. It's saying a host disable the participant screen sharing.
So, Anamitra, are you there? Yes.
Okay,
yes,
okay. Yeah, now I can. Yes.
Can you just try now?
Yeah, it's working. Thanks. Yeah. Is it visible now?
Yes. Please go ahead.
Okay. First of all, I'd like to thank the organizers to give me the opportunity to present my work here. So today I'm going to talk about topological inheritance in half-SSH Hubbard model. So other than me, there are three more people involved in this work. Dr. Tapan Mishra, my PhD guide, Professor Luis Santos, Dr. Sebastian Gesna, our collaborators. So topological phases of matter can show exotic behaviors. As we know, for quantum Hall effect, they can exhibit phase states which can conduct even though the bulk is insulator. So these properties are robust against disorder and perturbation because they are protected by the topology, and these are related to some non-trivial topological invariants, which are called Chern number in this case. These are given by the integral of Berry curvature over the Brillouin zone, and these are further responsible for the quantized Hall conductivity in the system. So after the discovery of the quantum Hall effect, there are 1, 2, and 3-dimensional quantum Hall topological insulators have been observed. So today I will be only restricted to the 1-dimensional systems. For that, I will first introduce the Suschreiber-Heger model, which is also called SSH model. Which is a very simple model that exhibits topological phase transitions. So this model was first introduced to describe the polyacetylene chain, where the electrons are staggered hopping along the chain. And so this kind of model became very popular to study the topological phase transitions because they are very easy to simulate in quantum simulators, such as in optical lattices, ultra-cold atoms in optical lattices, then photonic systems, superconducting circuits, and so on. The Hamiltonian is given by this, where T1 and T2 are the staggered hopping along the chain. So the symmetry that protects the topology in these systems are called chiral symmetry, and the system has two bands, which is given by this, and the topological invariant in this case is called winding number, which is given by this. And for the case, there are two cases when T1 is less than T2 and T1 is greater than T2. For both the cases, the system is gapped. And for T1 is greater than T2, the winding number becomes 0. And for T1 is less than T2, the winding numbers becomes non-trivial 1. So if we look at the open system, open boundary condition system, then I have plotted the energy spectrum in this figure. Where we can see that when T1 is less than T2, there is a zero energy state and in between the gap, and for T1 greater than T2, there is no zero energy states. When we plot the A point, when we plot the wave function at A point, we can see that these states are localized at the edges. Now, if we look at the many body systems, when the chemical potential is at 0, which is at half filling, we can see that when T1 equal T1 greater than T2 for open system, the system is each particle is localized at each double wells, and this is called bond dimer phase. And for T1 less than T2, the bulk is same bond dimer phase, but there is a state sitting at the edge. And when T1 equal to T2, the gap closes at that point, and the coherence length becomes large. So the question we ask is, if we have two systems, one is topologically non-trivial and one is topological trivial, then how with the interaction one can induce the topological property to the other system, which is topologically trivial. For that, we have introduced a model which we call Hubbard model. Then in this model, we will first talk about the bulk properties, then we'll talk about the edge properties, then we'll talk about some dynamical observables, which are mean curl displacement and Thouless charge pumping. Then I will conclude my talk. So let me first introduce the model. In this model, there are two components. One is up and one is down. And only the up component possesses the SSH kind of dimerization in the hopping. And for the down component, this has a homogeneous hopping along the chain. And this is the Hubbard kind of interaction. And this is Hubbard kind of interaction. So, okay. So now this kind of system can be simulated in optical lattices with the state-dependent optical lattice, or we can also simulate with the two neighboring chain which interact with the long-range interaction, where along the chain there will not be any interaction. That can be realized with the dipolar bosons, where two dipoles are parallel to each other or polarized to one direction. Then the interaction strength is given by this. As you can see, by varying theta, we can tune the interaction along this direction and along this direction. So let me first talk about the bulk properties in this system. So to quantify the bond dimer phases in this system, we calculate the dimer structure factor, and also to look at the gap of the system, we calculate the single particle gap in up and down components. So these blue curves, these two blue curves are for the up component, and these red curves are for down component. So as you can see, for any interaction, the bond dimer phase is present and the system is gapped. But for u equal to 0 in down component, the gap and bond dimer phase is both the gap is 0 and there is no bond dimer order in the system. When we introduce the interaction in this system, then we can see that this gap is opening up, and the system is in the down component, the bond dimer phase is getting induced. So as you can see in both the direction, when U is positive and negative, they are almost symmetric. They are actually symmetric, and we only look at the attractive cases, and all the results will be translated to the repulsive cases when U is positive. So then we have looked at the pairing, how the two components is getting paired in the system. To do that, to quantify that, we have looked at this quantity, which is eta. And as you can see, when U is very large, then the quantity is going to 1. That means both the component is getting paired. And at that strong pairing limit, we can actually map the Hamiltonian to a one-dimensional one-component system, which is SSH, which has SSH like dimerization, because because T1 is not equal to T2. Okay, so now the question we ask is what happens to the lower values of U, and how the system is getting induced, all the orders are getting induced in the down component, which is trivial. So then we have looked at the edge state of the system. As you can see that for interactions, when we introduce the interaction, both the component possesses the localized edge state, and this edge state can be quantized with the real space polarization, which is given by this formula, and we have just plotted this value. So the value minus 0.5 means the system has a state at the boundary, and as you can see, for very moderate values of U, maybe 1 or so, the a state is present in the non-trivial, in the trivial component. So now we have looked at some dynamical observables to just characterize the topological properties of these phases. So one of them is mean chiral displacement. What happens in this is just observing the quantum walker in a topological system, one can quantify the the winding number in the system, which is topological invariant. So to do that, we first just calculate the ground state of the system. Then we create a quantum walker, which is by annihilating a pair in the middle of the system, which behaves as a quantum walker. And by evolving this wave function, we calculate the mean chiral displacement by this formula, and look at the behavior of this quantity with the at large time. So as you can see that when U equal to 0, in this figure, the open circle, the empty symbols are for down component, which is topologically trivial, and this the solid symbols are for up component. Okay. So as you can see, when U equal to 0, the up component is already oscillating around -1, which is non-trivial value, and the down component is oscillating around 0. So when we introduce the interaction in the system, we can see that both the component up and down component are oscillating around -1, which tells us that the system has become topologically non-trivial. So to check that, we have calculated the winding number in the system by using the twisted boundary condition, which in that case, we just use the periodic boundary condition and transform this A operators with this formula. And if we calculate the vary phase in this by varying this theta, we can calculate the winding number of the system. So when we calculate the winding number of the system, we have seen that for these cases, the winding number becomes 1. Okay, there is a 1 over pi missing here. Okay, so the winding number becomes 1 for these cases and becomes 0 for these cases. Okay. Then we have looked at another dynamical property of the topological non-trivial system, which is called Thouless charge pumping in the system, which has a close analogy with the Archimedes screw pump, which is a classical system. And in this pump, as you can see, by rotating the steering, we can just pump a liquid from a reservoir. So similar to that, in the quantum system, by just periodically varying some parameters, we can pump quantized number of particles in the system. And for this SSH kind of model, this kind of protocol is given by the Rice-Milling model, which is given by this, by introducing a new term in the Hamiltonian, which is on-site potential. Okay. Now, if you look at any cross section of the lattice, you can see after one cycle of the pumping, a quantized number of particles should be pumped from one side to other. So now, if we look at the open boundary condition, then we can just track the edge states to just monitor the pumping in this kind of system. So here, what we have done is only the up component. Yeah, thanks. Okay, so with the so in this kind of in our system, what we have done is only the up component is subjected to the Rice-Milling kind of pumping protocol, and down component is as it is, which is a topologically trivial kind of system. And then with the introduction of interaction, we see how the topological charge pumping is getting affected in the down component, which is not being derived. Okay, so by looking at this polarization, we can calculate the number of charge pumped in this kind of system per unit, per one cycle of the pumping. So as you can see that for up component, which is topological non-trivial system, the polarization is varying from plus 0.5 to 0.5 for every values of u, because in this case the edge state, when tau equal to 0, the edge state is sitting on one edge, and then when the full pumping cycle is happening, then the edge state is going to the other edge of the system. So when the similar thing we have when we have looked at the down component, we see that when with the increasing interaction, a robust pumping is happening after certain values of u. Okay, so as you can see, this green curve is around 1, and after that value, maybe we can say that there is a complete pumping is happening. So, to quantify, we can look at this initial slope to quantify where the pumping actually robust pumping is happening. So we have just looked at this initial slope. As we can see that around u equal to the actual behavior of this curve is changing. So to actually quantify the actual point where the actual the full inheritance or full pumping or full state is arising in the system, we have looked at the fidelity susceptibility, which is the differentiated form of the inner product of two wave functions at two different parameters. As you can see from this formula that if two wave functions are very different, then this should diverge at some point. So we have looked at for different values of L, the system size, we can see that there is a clear peak at certain values of U. Then when we extrapolated that point to the thermodynamic limit, we can see that the critical point maybe is around 1.06 or so. So in this slide itself, I want to conclude the talk. The remarkable thing happened in this case is the complete inheritance is happening at very small or moderate value of u, where the pairing is very weak, is around 0.2. Otherwise, if for large values of u, this kind of inheritance is expected. But at very moderate or low value, we can see that complete inheritance is happening. So with that, I would like to thank all the participants. Yeah.
Thanks, Sohan. So maybe we have time for very quick question. One very quick question. So if you have a question, please straight go ahead and ask. So if there is no question, then for the interest of time, we'll move to the last talk of the session, which is by Deepak Singh. We'll talk about magnetic Hamiltonian and structures in metals. So Deepak, the floor is yours. I will let you know when you are 10 minutes down. Please share your. Shuman, you have to unshare.
Yeah, I've done that.
Hello.
Yes, Deepak, please go ahead.
Yeah. So good afternoon, and I thank organizers for allowing me to present my work. And the title of my talk is Microscopic Magnetic Hamiltonian for Exotic Spin Textures in Metals. So I will give introduction to about Rashba spin orbit coupling. Then I Yeah, hello.
Deepak, we can hear you.
Then I will talk about so microscopic electronic Hamiltonian, and then I will discuss about double exchange model. combine these two concepts and have a partial model and show some simulation results after the effective spin Hamiltonian, and then I will conclude. So this the work I am presenting is published in Physical Review B. Yeah. So when a particle with spin moves in an electric field, that it experiences a magnetic field in its rest frame. So in this way, the spin and orbital degree of freedom of that particle gets coupled. This is called spin orbit coupling. So in a two-dimensional electron gas, there is a lack of inversion symmetry that leads to the some electric field in a perpendicular direction to the surface, and this asymmetric potential gradient happens in this inversion symmetry. So because of that, the Rashba spin orbit coupling appears in thin films or in interfaces between transition metal oxides. So this gives rise to the Rashba spin orbit coupling, which has this form, and so we will talk about this. So Rashba spin orbit coupling can be tuned by external gate voltage because it by gate voltage we can tune this dV by dz.
Sorry to interrupt
The
you. Can you
potential.
make your slides, I mean, full screen?
Isn't it full screen?
If it is possible. Otherwise, you can just go ahead.
Yeah. Go to the view and then click the full screen.
I think you have to share your screen again.
Share screen. So is it fine now? Hello?
So the view, so if you go to view again and see what other options are there. It's sharing and unsharing. So it's your presentation.pdf is the one.
I'm trying something.
So maybe you just open your PDF and like we will go ahead as it is. No problem. Yeah, please go ahead as it is, like, no need for. Yeah.
Is it okay now?
Yeah, you go ahead. Yeah, no problem.
Okay. So we start with this Hamiltonian, which is a Kondo lattice model in which there are localized magnetic moments are interacting with the itinerant electrons, which can hop in a lattice. So we consider these these localized moments as classical spins with magnitude 1 and its Hamiltonian is this, which is tight binding part, and these classical spins are local interactive with alternate electrons. So now we can from global quantization axis to we can transform this Hamiltonian to local quantization basis of the localized moments by this unitary transformation. In this way, like here in this picture, so these localized spins are these, and which electrons are hopping with hopping t. But when we transform this Hamiltonian, we get hoppings from so parallel electrons can align parallel or anti-parallel to the localized spins, and we can have a hoppings. So these are projected hoppings. Now, so in when this there is a large Kondo coupling or Horn's coupling, which is we say it as a double exchange limit, and in that limit we can the electrons can align in completely parallel to the localized spin moments. And so in that way, the hoppings gets modified to this expression where the hopping is dependent on the theta and phi's of the localized movements. So now, so we combine these two. We have this tight binding term, Kondo coupling term, and we add this Rashba spin orbit coupling Hamiltonian here. And so important point here is here the electron flips when it hops to the nearest neighbors, and we parameterize with T naught equals to 1 such that lambda is alpha T naught and T is equals to this. So where lambda is the Rashba parameter, or which is equals to alpha. So similarly, what we do for double exchange model, we transform this using unitary transformation. This makes Rashba double exchange model gets this form where D, so basically Hamiltonian transformed into another form in parallel basis, where Gij gamma is Tij gamma plus lambda Ij gamma, where expressions are like this. So we get these expressions. So now this Gij, which is a sum of these two, is a complex number which we can write in polar form as this, where Fij is its magnitude and this is its azimuthal point. So now, because we can write this Hamiltonian as a Dij gamma, Fij gamma. So where this Dij gamma is ground state expectation value of this term, and Fij gamma, since it is a magnitude of this complex number, we do calculation and finally reach to this expression for Fij x and Fij y, which has basically three components. This is like Heisenberg term. There is a DM interaction like term here also, and there is a this is a dipolar pseudo dipolar term it has. So finally we can combine we can write this expression as this, and so here important point here, Dij gamma is can be non-uniform. It actually is non-uniform, but we find that if we Dij gamma probability distribution, if we plot it, and find that we can approximate Dij gammas to be uniform. And so for our simulations we use dij gamma equals to d naught, which we take as 1. So now we combine spin fermion model and the spin only model. So in spin fermion model, we reach from spin fermion model to spin only model, and we compare these two models by comparing the energies in the low temperature regime, which we find that the two models almost give similar energy dependence on temperature. And so ground states and in effective spin Hamiltonian, we find that we get the accurate ground states, which we get by in spin fermion model by doing hybrid Monte Carlo simulations. So in this way, we so by using effective spin model, we can perform calculation on larger lattices. So here are some simulation results. We start at high temperature with the paramagnetic state or alpha 0, and at lower temperatures, we get the ground states, something like this, which we call classical spin liquids. And for alpha 0.6 parameter, we get something like this, which is if we see, so these are like a crystal of small Neil skyrmions. So I will show in next slide also. So from our calculations, we in our calculation there is a we plot phase diagram. Here we temperature and we increase alpha. As we increase alpha, alpha 0 case is ferromagnetic state, because that is simply the double exchange model. But we increase alpha, the ferromagnetic state goes to the classical spin liquid state, which if we see the evolution of this phase diagram through spin structure factor, we see starting from ferromagnet, it goes to a diffuse ring pattern in a spin structure factor, which is a signature of classical spin liquid. And as we increase alpha, this arc-like feature comes. And so after that,
okay, you have 2 more minutes.
So filamentary domain wall get narrower, and as we increase alpha more again, so we get single Q states, and further increasing alpha gives us this skyrmion crystal lattice, and then other states are like diagonal flux states. So so important states are here are this spin liquids and this skyrmion crystal. So to understand this classical spin liquid behavior, we do this variational. We consider variational line charts to understand these classical spin liquid behavior. So in this spin liquid comes for small alpha. In small alpha limit, we can ignore lambda square terms from our Hamiltonian, and so that basically this is the dominating part in the Hamiltonian. And so these two this term prefers two spiral states, competing spiral states orientations, and so like in along x direction, it prefers to xz spiral plane, but in y direction, it prefers yz spiral states. And we consider all different spiral states and found that as long as so here q vector phi p is the spiral plane angle and Q vector is Q is this cos beta sin beta. So as long as beta and phi p has this relation, we get the all different spirals with different planar angles have the have degenerate ground states. So basically, this
Deepak, you should quickly
classical spin liquid.
end.
Yeah, okay. So finally, I conclude this with some experimental comparison with some experimental results done by this LTM studies. So in experimentally, they found this classical spin liquid in different materials, these in these different papers. And when we apply magnetic field in these, we get skyrmionic crystals, skyrmiones. So similarly, in our theoretical simulations, these all results I showed was with zero magnetic field. As we apply magnetic field in this, we also get skyrmiones here. So thanks.
Yeah. So thank you very much, Deepak, for a very nice talk. So the floor is open for maybe one very quick question.
I have a quick one. If I
sure, right.
So I was
Yeah.
just wondering for the spin fermion model. Have you guys looked
Yeah.
at the dynamical susceptibility within some RPA scheme? So particularly to understand your classical spin liquid, I understand that you towards the end use the classical model to sort of discuss this. But if you calculate the dynamical susceptibility for the spin fermion model, there do you get some signatures of because you still have the classical spin sitting there, do you get a dominant washed out feature?
Dynamical susceptibility, no, we have not done that.
Okay, another slightly related thing. So at some point you mentioned that you have looked at that the spin fermion and the classical model agree well at low temperatures. What happens? So one would expect it to deviate as the spin sort of cant more and more. The deviation in the structure of the model will show up at high temperature. Is there a similar study that you have?
So at high temperatures, the results will not match that much. So we are only say about at low temperature regime, these two models are.
I see the axis is temperature. Is it the x-axis here?
Yeah, the
okay,
x-axis is temperature.
Okay, thank you.
Okay, very nice. So let us thank Deepak again for a very nice talk, and let us also take this opportunity and thank all the speakers of this session, and mostly keeping the time. So yeah, so let us end this session here. Anamita, do you have any announcements?
Yes. So let me thank you, Mukul, for chairing the session and all the speakers for very interesting talks. So we'll start the post-lunch session at 2:25 with 3 talks chaired by Manoranjan. Okay, that's the announcement. So we will meet at 14:25. Speakers and the chair can log in around 2:15. We'll be there to sort out any issues if they have.
Yeah, I'll be there, Anna.
So, okay, thank you, Manoranjan. And thank you, Mukul.
Yeah.
We'll okay, thanks. Bye.
Okay.
स्लाइड ही नहीं दिख रहा था स्लाइड ही नहीं दिख रहा था पता था अभी भी समझ नहीं आ रहा कहां तक क्रॉस हो रहा है साले मैं करने जा रहा हूं इतना क्यों पहले करता है मैंने ऐसे लिया अभी म्यूट है ना हां मैंने ऐसे लिया बस मुझे इसको हटाना था या फिर ये साला पता नहीं जहां पे दिख रहा है क्लिक कर दे रहा है अबे वो कुछ बोल रहे थे
Hello. Manoranjan, you're around? Maybe I'll ask Shayan. No, Tanmay, are you? Can you hear me?
I'm around.
So you want to check your slide? I have made you a co-host. If you want to check your slide, maybe you can share your screen.
So should I try now?
Yeah. Go ahead. I can see your screen.
You can see. So actually I'm in some 2 monitor mode, but do you see my full screen?
No, I see one screen, and I think next slide has a small thing on the right.
Okay, now I see. So what I need to do is that I need to get out of this 2 screen mode. So give me 1 second.
Sure.
Tanmay, just set the mirror display, then also it will work.
I
think you don't have to change the.
But anyway, I think I know one simple way. Let me stick to it. I don't want to do any experiment now.
Okay.
Especially my computer is telling me to update both Zoom and my computer. I've sort of postponed both my thing. So I don't want my computer to do the restarting. Anyway, can you see it?
Yes, I can see this full screen.
It's all fine, right? Okay.
Yeah.
Great.
Yes,
Okay.
I can see their pointer as well.
Yeah. Okay.
Okay, thank you.
Good, then so I'll stop sharing.
Okay, thanks. Shayan, you are a co-host now. You can share your screen if you. Hello.
Where is Sorinda?
Sorinda is still not here. Probably deciding on his title. He said he'll change.
Give him a call, man.
I'll try to call him.
Background sound it is?
I think Shayan's. Shayan, try it once more.
Yeah, just on.
Hey, Sharinda. আসছো তো?
Yeah, is it visible?
হ্যাঁ, এখন লগইন করে একবার চেক করে নি স্লাইড গুলো, মানে দেখা যাচ্ছে কিনা। ঠিক আছে। Sure. Okay. Sure. Thanks. Okay. Bye. Shaurin is coming in 2 minutes. He just got back from someplace. Shan, I can see your screen.
Is it visible?
Yes, your voice is slightly low. Maybe you can up your volume or something.
Oh, just 1 second. Yeah, now is it fine?
Yes, I can see your screen, etc. The only thing is your voice is not very loud. Maybe you come closer to the laptop or the computer.
Yeah, now it's fine?
Yeah, it's fine. So make sure when you speak, just be close to the machine because your voice is generally a bit less audible. Otherwise, things are fine. Okay.
So now it is audible,
you
right?
can.
Okay, thanks.
Yeah, sure.
No, actually, you are not audible at all. I mean, very.
So Shayan, so others are saying you're vaguely audible. So
can you try to rectify in some way? Maybe just come close to the microphone or something.
Yeah.
Yeah, I just try. Now is it fine?
No.
Still very low.
Better than previous one, but still low.
Yeah.
Yes, Saswata, are you there?
Yeah, I'm here.
Yes, sorry, I wanted to listen to your talk and Amrita's talk, but today we have this faculty meeting. And in fact, I will miss the faculty meeting little bit.
No problem at all.
My
It's
talk, then I
absolutely
have
fine. But more important that I will attend your talk. So that is
that is the least important.
no, that is very important because I'm slowly switching to quantum materials and these things. So I really need to attend your talk. So that's absolutely
In fact, I will disappoint you already that my talk has nothing to do with any real world. It's non-Hermitian system.
Okay, no problem. But still, it is always nice to hear you. So I'm really waiting for your talk. I have in fact even told today all my vendors that please do not call, do not come this time.
Yeah. Your students' talk was yesterday. I was the chair of that session.
Yeah, I know. Manish, he gave yesterday.
Hello. Now is it audible, no, sir?
It's still quite low, so just speak when you speak. If you cannot rectify it, shout a bit when you're giving the talk, okay? Speak a bit more loudly than usual. If we cannot hear you, we'll let you know, then you can speak even more loudly during your talk. Okay?
Okay, I think there's a problem in my lap. Yeah, I will actually...
Just speak a bit loudly, that should be fine.
Okay. Yeah, thanks.
All right, so Shaurin just got back. He requested that he'll come in a couple of minutes. So we're just waiting on him.
He wants to be a second speaker or what?
We did not say. If you want to take the session, you can take the risk and pick up the issue with him. I have no problem.
I mean, actually, from my side, if he wants to go second, I'll be absolutely fine. Just to let you know. I'm fine with anyway.
No, I'm just joking.
Hey, Shaurin is calling. Just listen. Hello, हाँ Shaurin बोलो. ना Google Meet ना Zoom link. আমি কি ফোনে থাকবো যতক্ষণ তুমি জয়েন করছো মানে if you need any you don't need any password etc. You should be able to just click and get in. So I see. Okay, I can see you. What I will do is, I'll make you a co-host. Okay, so now you should be able to share your screen. Yes, I can see 2D platform is desirable. And I see more than one slides this time. Sorry for the joke. Okay. Full screen. Yes, I can see your screen and your cursor. Okay, so it's fine. You can stay because all other speakers have checked their things. So since you are the first speaker, keep it on. We'll start in a minute or so. Okay, I'll cut off the phone then. Sure. So Manoranjan, it's over to you now.
Yeah, okay. Thank you, Anamitra. So shall I start now or we'll wait for a minute?
Maybe let's wait for a minute. It's just 25.
Okay.
Few people might show.
Sarinda, I can't hear you.
Sorry, I was muted. Sorry.
Okay. So good.
You can hear me now?
Yeah, now we can hear you.
Okay, great.
Yeah, so we'll wait for a minute and then we'll start.
Yeah, sounds good.
It's almost time, actually.
Okay.
So. Okay, I think we should start.
We can start.
Yeah, so good afternoon, everyone, and welcome to the post-lunch session. Our first speaker is Professor Sarin Das from IISER Kolkata, and he'll be talking about topological superconductivity and Majorana fermion helical edge state.
Okay.
And now, Professor Sarin Das.
Thanks, Professor Manoranjan, for handing me over. So, and thanks to the organizer for giving me this opportunity to speak about our recent results on topological superconductivity in helical edge state. So, our collaborators on this work is Vivekananda Adak and Abir Mukhopadhyay from IISER Kolkata, Shumanjali Dey, and Sumati Rao from HRI, and Udit Khanna from jointly from Weizmann Institute and Tel Aviv University. So the idea of this talks, the overview will be something like this, that our main focus, I think maybe it's not so exciting for theorists, but maybe more exciting for experimentalists. What we are trying to do is look for signatures of Majorana fermions in helical edge states, which is really a 1D system, and then try to simulate those results through 2D simulations, where you really take up a lattice model which is more realistic and realize the edge states in the topological regime, and try to see if you put appropriate contacts and make appropriate arrangements, do you really recover all the 1D nice results which you see from a simple-minded calculation coming out of your 2D non-equilibrium transport calculation. So that's the idea. So I'll try to convince you that it is really possible, and we really almost see 90% overlap between the two results. The predictions coming out of 1D model, which is reasonably simple-minded, and something coming out of a reasonably complicated non-equilibrium transport code. Okay, so let's start. Oh, I'm not able to change my slides. Oh, come on. Manu, you have any idea how? So this is. Oh, sorry, it started working. Something went wrong. Okay. So it's a quick introduction to Majorana fermions. So Dirac versus Majorana. So really from a cheap, I'll say rather cheap introduction to Majorana fermion would be the following: that if you think of fermions, so these are really creation. We think of what comes to our mind is creation and annihilation operator, which follow an anti-commutation relation, which tells you that you cannot create two fermions at the same site. So they square up to 0, and these operators are not self-conjugate as expected. So now if you can mathematically, you can always write the C's or the C daggers in terms of two other objects which are Hermitian, which are self-conjugate, each of which you see that here I write C as eta plus I eta dagger. If you look at eta and eta dagger, they are even and odd under some kind of a anti-unitary operation, which you can think as some simple-minded time reversal symmetry. So that's the distinction between them, and you can write the C operator as a combination of the two. So now the question is, of course, we can do that, and you see that they also follow some anti-commutation relations. This is just a mathematical exercise, and you can write any model which you wrote in terms of fermion could be written down again in terms of these etas and eta bars. Nothing stops you from doing that. Question is it physical? And the idea of what is physical is what we can address experimentally, or we can see as an isolated excitation of a theory. So if we can see them as an isolated excitation of a theory, we will say they are physical. If there's not, it's just a mathematical fancy exercise and it doesn't mean much. So that is exactly what was the genius of Kitaev. So he came up with this idea that if you take really spinless fermions in one dimension, truly spinless, and which only has no other quantum number other than just they are left movers and right movers, and you induce superconductivity into the system if you can, and then such a superconductivity naturally is a p-wave superconductor, because you cannot really create two fermions at the same site, so it has to be non-local in nature as far as the pairing is concerned. And if you go to the Fourier space, it will have momentum dependent pairing, and this gives rise to the p-wave nature of the superconductivity. And if you have in 1D, if you have p-wave superconductivity, it will give rise to the Majorana fermion, and it is a topological phase of superconductivity. So that's the simple idea, and there are different platforms to realize it. So experimentally, it has been explored in various possibilities. For example, the 1D for a 1D system, as you can see that the indium antimonide nanowires, which are strong spin orbit material, has been explored quite extensively. Which recently, I think Leo Covenhagen and Charlie Marcus are very aggressively working on it. On the other side, you have the 2D platform in which you have the quantum spin Hall phase, which has a nice helical edge, which is practically spinless. which is like a 1D spinless system where if you could induce superconductivity, you are again supposed to see these Majorana fermions. And Lawrence Monenkamp has been an initial player and a big player in the game. All the samples come from him, and recently Ami Jacobi from Harvard has also joined hands with him, and they're doing some wonderful work there. And then there was some work also by Princeton group. This isn't just an isolated piece of work where they essentially took ferromagnetic atoms and kind of deposited them, organized them rather, on top of a lead so a superconducting surface. They organized 1D atoms, and then they tried to look through an STM probe if they could see Majorana fermions. I mean, there's a lot of controversy about if it's really Majorana fermion or not, but they definitely saw a zero mode at the end of the chain. So all these three experiments have seen reasonably encouraging results. But the 2D platform is particularly encouraging because all our IC technologies is really based on 2D platform. We know how to make devices out of them. So if you are thinking of doing topological quantum computation using Majorana fermions and Majorana fermion qubits, then you better think of 2D because that's the best place where you can really make use of it. So it's I think there is lot more results on the 1D side, but I would say that the 2D side is really a very important platform which has been pursued recently, and I think this can, if we can realize it here, this will be much more useful than the 1D platform, because you need to do braiding operations and so on to really do encode some quantum information on it, read out quantum information from these qubits, and that is much easily doable in 2D. Okay, so the 1D platform has been, as I said, it has been extensively, kind of worked upon, and I think that the leading groups which initially came up with this idea was from the Leo Covenhaven's group from Netherlands, and then there was the Weizmann group, and there was one more group. So three groups. I think Anindya is there. Anindya was one of the lead authors on this first paper which came out from Weizmann. So there were three groups initially there, but I think Leo has been pursuing it very recently quite aggressively, and also Charlie Marcus. So, okay, so I won't tell much about that except for the fact that the essential picture is this, that you have a 1D topological superconductor drawn here, and then you have a normal lead and you are trying to inject electron into it, and what you're looking for, because this is a subgap state which is really sitting at zero energy, what you're looking for is a resonant transmission or resonant and wave reflection, which should give rise to a conductance of 2 squared over h at zero energy. And initially the peaks were pretty bad, they were really not 2 squared over h, but if you look at this recent experiment from 2018, they have been perfected to a great extent, and they almost see something like 2 squared over h. So it's very encouraging from that point of view. Okay, so now this is the STM experiment. I won't get into the details. You can see that at zero energy, they see this is the STM scan, and you see this red spot here, which is telling you that zero energy, there's really an end state. And this is coming out of some STM scan from these arrangements here. Okay, so now the 2D platform. So this is what I'm going to talk about. So the quantum spin Hall at state is what we are after. So if you can think of it, and as a quick introduction, you can think of it as two copies of quantum Hall effect, each nu equals to 1, which has a single edge with up magnetic field and down magnetic field put together, so that when you put them together on an average, there is no magnetic field, but you're left behind with a double edge which is propagating opposite to each other with spin polarization opposite to each other. So that's the picture. That's the helical edge state. The bulk is gapped. It's a topological state of matter. The edge is gapless. It's helical in nature. So the dispersion is given here. So you have a right moving branch, you have a left moving branch, and the right moving branch has a locked spin to it, which is up, and the left moving branch has a locked spin, which is down. So the spin is really here spinless because this is practically spinless because spin is locked to the momentum. It's not an independent degree of freedom. So now, so as far as the 2D topological insulating phase is concerned, which is the Z2 phase, this really does not require SZ to be conserved on the boundary, but there is enough experimental evidence on like this 2012 experiment, which is again from the Molenkamp's group, which gave very clear indication that there is very strong spin polarization on the edge, which is along the Z direction. So it's a good starting point that we assume that the edge is really spin polarized in this sense, and it has a SZ polarization. Okay, there is strong evidence for that. Okay, so if we start with that, so I'm not going to get into this. So we start with a simple-minded 1D model where you see that it's extended from -infinity to +infinity. So the initial Hamiltonian is just a linear spectrum, a Dirac spectrum in one dimension with some chemical potential term here. So the sigma z are the spins, real physical spins. Tau z are essentially the particle hole degrees of freedom. And now we have two other perturbations which are switched on the superconductor. So essentially this is an helical edge. This region here, which we call delta here, that is where on the helical edge we have imposed some proximatized superconductivity, and also we have induced what we call the mass term and the boost term. So the mass term essentially is a magnetic field on the edge acting along the x direction, which opens up a gap in the spectrum. On the other hand, the boost term is something which doesn't open up a gap, it just shifts the Dirac cone. So if you think of a filled Fermi sea on the edge, then if you apply the z sigma z term, it essentially shifts your Fermi sea and gives it a finite momentum. So initially the Fermi sea is sitting at 0 momentum, and finally the Fermi sea after you apply your boost is really having a finite momentum. And you can imagine that if you try to switch on superconductivity while your Fermi sea is carrying a finite momentum, this is going to compete with each other, and finally you're going to hit, at some point you're going to hit a gapless superconductivity, and that's exactly the phase transition which one is looking for. So the mass term essentially will drive you through a transition which is starting from a superconducting gap to an insulating gap. So it's a gap closing, gap opening transition from a topologically non-trivial regime where you have a Majorana in the BDG gap regime to a gapless regime where you have no Majorana, where you have an insulating gap. On the other hand, the boost term is more interesting because what it is going to do as you increase the boost, initially you have the Majorana, and at some point the boost is going to close the gap and not reopen it. It's going to keep the gap closed, and you're going to get a superconductivity which is gapless superconductivity, and there will be a nice transition between the two. So when the BDG gap is of the order of the boost, then essentially you lose the Majorana, and that is the transition. So what we are looking for is a phase diagram in the space of G1 and G2. These are the two important perturbations which you can switch on, and trying to see what kind of transpose signatures you get, which will tell you what is going on. Manu, can you give me a prompting when I'm left with, let's say, 10 minutes?
Sure.
Thank you. So, and we also have a barrier term. The idea of putting the barrier is that if you do not put the barrier in front of the superconductor, then the Majorana is going to delocalize all over the place. It's just going to delocalize into the edge. So if you want it localized and stay sharp as a resonant level, then you have to you put another gap in front of it, which is the mass gap. And then you have an incident electron, and then this incident electron really sees a sharp resonance due to this Majorana sitting in the middle, okay, exactly between this this barrier region and the superconducting region. So that's the idea. So you can just go to the Fourier space and rewrite this Hamiltonian. If you do that, at least in the G equals to 0 case, when you have no boost, you will essentially get an effective P wave delta and an effective S wave delta, and your topological regime is where the P wave dominates, and the non-topological regime is where the S wave dominates, and that's the phase. So there's a phase transition here between a topological and non-topological regime where you lose the Majorana as the mass gap starts dominating. On the other hand, when G2 is 0, you have a phase where it's essentially at some point your gap closes due to this shift of the Fermi sea, and you lose the Majorana, and that's the topological to non-topological transition. Let me not get in the spectrum. So what you can do is you can just look at the BDG gap and try to understand what is happening. That will give you a sense of the phase diagram. So as you see that when I'm 0 chemical potential, essentially the dark circles which you see here and this line, these are the points where the gap closes. All the green region which you see inside is essentially where you have topological superconductivity. With the green region outside is essentially the mass gap dominated regime where it's an insulating phase. So as you see that as I switch on chemical potential and keep increasing the chemical potential, chemical potential, the gapless regime keeps on widening, and you have a large gapless regime where you have in between there's a capsule kind of region which is representing topological superconductivity, and outside you have a trivial superconductor, right? That's the phase diagram. So now we'd like to have a transport signature coming out of it, and that's you can just calculate the zero energy conductance which you expect to be 2e squared over h whenever you are in the topological regime. So you exactly see that. You see, as a function of chemical potential, you see that this ball here is essentially representing the place where the gap is completely closed. The gap is the BDG gap is dominant, and you have a topological superconductor, so you have a conductance of 2e squared over h. If you go outside it, is your Andreev reflection is exponentially suppressed here, and you see no conductance. And there's a nice line here. This is the line where you have gapless superconductivity, where the mass gap is practically 0 on this axis. So it is not topological, but you still have superconductivity. So you can think that your superconductor is like a cavity where you still have particle hole conversion, and particle hole sloshing back and forth, giving rise to some kind of interference pattern, but it's not gapped. So it's not quantized to 2e squared over h. You have no Majorana there. So, and you see that this gapless phase keeps on increasing and gives on this oscillating pattern as you keep on increasing the boost. So that's the phase diagram, and you can check for yourself that essentially on this line here, which is this white line, you have a direct backclose. So if you look at the BDG gap, there are two kinds of gap here. Actually, if it is mass dominated, it's a direct gap. The gap really closes and opens at the same momentum point. But if you have a boost field acting, which is here, then you have an indirect gap closing. Essentially, it's not a direct gap. The gap is closing, but essentially the upper band and the lower band are hitting 0 at different points in the momentum. And that is an indirect gap. So as you go to larger chemical potential, you really get these two different kinds of gap closing. One a direct gap, one is an indirect gap dominated by different physics, and there's a competition between the two. So that is what we get from 1D physics. And as you see that here, this bright line you are seeing here, if we switch on, this is in absence of the ferromagnetic barrier. So look at the first figure here. This absence of the ferromagnetic barrier, you see this nice interference. If you put the ferromagnetic barrier, you see it just disappears. So if we put barrier, we can get rid of these resonances, and it starts looking quite different. Okay, so with that, so this is again a expanded version of the.
7 minutes.
I have 7 minutes. Okay, very good. So this is an expanded version of the same picture. So I think I told you whatever is there, and I think I'll go ahead. So now the 2D model, which we are going to simulate, we're going to discretize it, and then kind of really do a real space simulation, transport simulation with this. And the idea is that if you look at the BHZ model, which reasonably faithfully represents this Mercury telluride quantum wells, you have a spin-up block and a spin-down block. Each of these blocks you can think in terms of a Chern insulator, where the Chern, Chern number for them is equal and opposite. If one is +1, the other one is -1, and then each of these blocks essentially induce one edge states, and that is how you get two edge states. So the up block give rise to an on the boundary up edge, and the down block give rise to a down edge. That's the idea. So that is your helical edge state, right? So what you can do is you can switch on an exchange field, and essentially you can switch it on in such a way that you can actually kill one of these topological blocks, leaving behind the other, which makes it an anomalous spin Hall insulator, right? So you can be in the topological regime where both of these blocks are topological, but you can also switch on an exchange field. I think the details of this is given in this paper, which we exploit in our device construction, where you destroy one of the gap, such that let's say the spin-up block is no more topological, so the spin-up edge is gone, but the spin-down edge continues to be there, which is pretty much like an Hall effect. So the device we come up with is the following. So you have a spin Hall sample. We put the source lead, we put the drain lead, and the upper edge we destroy in the sense that we disconnect it by putting a ferromagnetic gap. On the lower edge, we put BDG, essentially put some BDG Hamiltonian exactly on the edge. So we essentially do some simulations to get an estimate of the edge state and precisely put, superconducting correlations on those edge, and then put some ferromagnetic gap and check if we have the Majorana mode. And then from the source we inject electron and get back a reflected hole. But this is, as a device, this is a bad device, because you have the injection and the reflected electron coming out on the same channel. What you want essentially is to have a situation where the injected electron and the reflected hole are completely separated out, and that's exactly what you get using this anomalous spin Hall configuration. So in between you put the anomalous spin Hall, so that you have an incident electron which comes in as an up electron, then it reflects back as a down electron incident on the Majorana, and goes back as a hole again as an up electron, and then being collected at drain D1, And remember that we also have a phase space where the gap is closed. So if your gap is closed, when there is an electron incident from here, it can actually go to the drain electrode because the BDG gap closes and the electron indeed can go through the superconductor. So then the leaked current will be collected at drain 2. So essentially what we presently the kind of dimensions which you're looking at on this device is like 1000 cross 200 lattice sites. And you can think the caricature of the pathway of electron is something like comes out of the source and then suffers a spin flip, goes to the superconductor and comes out exactly as a perfect hole as long as it's at zero energy, and finite energy is going to become something else, of course. It will be like a partially whole an electron, but what we are focusing on right now is really zero energy, and we see the resonance or not. So with this device, if we perform, no, it's not moving. Come on. Yeah. So if you look at the result of a simulation, this is the result of a simulation, and this is really, I mean, these are heavy simulations which run for a few weeks on a parallel platform on the size which I told you, and you see that the match between this 1D calculation and the 2D device which I showed you here in the previous slide is almost perfect. So you exactly get what you expect, provided you have put your contacts and leads and in the ferromagnetic correlations on the edge very, very carefully. And this was done by Vivek really very intensively. I mean, he really has developed a very good expertise on this, on running this device simulations. And after a lot of hard work, I think we can see that, you know, there's a perfect consistency between what is obtained as a theoretical calculation and what is obtained from the simulation. So now you see below, this is a simulation where we are presenting the current density plot, right? So you see that the injected current densities on the color plot, color code, you see that the positive numbers, the red numbers here are essentially the spin up side, the down numbers, the blues are the spin down side, and we see that the injected current density is initially blue, then it reflects, so it becomes red, and then from the ferromagnet and the superconductor via the Majorana, it reflects back as a blue and being collected in the lead 1. So essentially we are in the 2 lead configuration right now, and we are trying to extend this to 3 lead configuration so that we can, you know, collect the signals of the reflect and the transmitted beam separately. So that is the kind of consistency we have. These are calculations which was done by Abir, which got reproduced very nicely by Vivek. And now lastly, we have some beautiful results also from come on, it's just really stuck. Hello?
Yeah.
My screen is stuck. I don't know.
Maybe try to go off full screen and try back. Just try to not go off full screen.
Yeah. Okay. Can you see my screen now?
Yes. If you want to continue,
yeah,
you can continue.
I think, yeah, okay, fine. So I'll just continue. So these are simulations done at finite energy, and again, the upper block is really coming from our transport simulations, non-equilibrium transport simulation. The lower one is simple 1D calculation, and they show almost a perfect match between each other, even at finite energy. So this one was at zero energy scan. This is at finite energy. We are looking at different slices of this plot. And lastly, there's a very nice self-consistent simulation done by Shuman and Udit, which we are looking at very carefully. And what we are trying to see is that when you have the gapless phase, if you really run your BDG equation self-consistently in presence of some interactions, what you see is a nice FFLO phase appearing there. And you can see that these edge states really get decorated in terms of their BDG gap. So there are some oscillations, as you can see, they are emerging as a function of this. G1 was the parameter, which is the boost parameter. So initially we have 0 G1, no boost, and as you start, imparting momentum to your Fermi C, then it competes with the auto parameter, and then finally, once you have a gapless phase, you start getting these kind of oscillatory pattern in delta. So to complete the phase diagram, you can imagine that the phase diagram looks something like this.
Sarinda, you have to wind up.
I'm pretty much done. So if you think of the phase diagram, where is it? Yeah, if you think of the phase diagram, you can think that, this is a trivial insulator. This is a topological insulator, and this is an FFLO phase. So that's roughly the phase diagram which we get, which we can very nicely scan out of some 2D simulations, giving a reasonable indication that this should be possible in probably some experiment. Okay, with that I would like to conclude, and I'll just flash the conclusion, and thank you very much for listening to me.
Okay, thank you. Thank you very much for interesting talk. Now we'll take one question.
Can I ask a question? I'm Ganesh.
Yeah.
Shorinda, so you have shown this conductance for 1D case.
Yes.
Here, in that, I mean the diagram that we have shown. So there is a black line in the middle. Does that mean anything, or just?
No, I think it is a numerical. Yeah, I know there is a small glitch there, but I think it's mostly numerical. I don't think there's any physics there.
Oh, I see. Okay.
Yeah.
Hi, can I ask a question, Manoranjan?
Yeah, I think we'll take this one as a last question. Please go ahead.
Okay. Hi, Shorin. Just a question. Is this gapless BCS state, does it have finite single particle density of state at zero energy? And if yes, is it stable to fluctuations?
It is.
In 1D?
So that's exactly what we are exploring right now. So as you see that we did some self-consistency, and new patterns seem to emerge.
Okay, I think that it's unstable because you can just write single particle terms. Okay.
Yes, but
finite density of state.
Yeah, I think it's a question of if. So I think if you think from a device perspective, it's being induced from outside. So if you think of a situation where the superconductivity is emerging due to the material property itself, then it's unstable. But if it is really induced from outside, I think it's pretty much stable, and the stability depends on what is inducing it. So if you have aluminum or something which is inducing it, that will hold the BDG gap pretty stably into the material, and it won't be taken over by something else. You see the point? I mean, if it is something which is coming from the inside of the material, some instability, then it's a different story. But this is really proximatized superconductivity. So I think we can pretty much hold it there, and instabilities won't matter in some regime. Shubhra, did I answer your question?
Yeah, I think we need to discuss this later. Thanks.
Yeah, okay.
Okay, so thank you, Shorinda, for nice, interesting talk.
Okay, thanks, Manu.
And we'll move to next speaker. Our next speaker is Professor Tanmay Das from IC Bangalore. And he is going to talk about the hidden gauge symmetry in the non-Hermitian quantum world. Professor Tanmay Das, please go ahead. Please share your slide first.
Yeah, I shared it. Can you?
Yeah.
Can you see it?
Wow.
Manoranjan, can you confirm whether you can see the screen?
Oh.
Hello.
Yeah.
Maybe anybody else? Like.
We can't see your slides.
Okay, maybe now it should work.
Yeah, it is there now.
How about now?
Yeah. Oh, yeah, it is there.
Okay. Okay, guys. Thanks a lot to the organizer for inviting me. So this is my first participation in your ongoing sort of series of conferences. So I'm very happy to be here. And yeah, so I will talk about something. I thought I was just talking to Sastata saying that these are all unrealistic world, but it's not completely true. It's there are part of it which are true, which are real, called a PT symmetric system, which we can realize. But anyway, let me build on it. And so I'll start with I'll start with giving a short introduction to the non-Hermitian system, or rather like non-Hermitian way of, or sort of a parallel quantum theory that one can, or people are trying to build for a non-Hermitian systems. And there would be many applications of it, many realizations, which I will not talk about it. But then I will switch to a very specific type of system, which are parity time reversal invariant system, which is kind of a now mainstream research because there's a huge number of realizations of parity time reversal invariant systems, which are non-Hermitian, but yet it has unitarity, real eigenvalues, and so on. But it does have some roadblocks, and which I will address first. And then I will, so like when I was trying to look at those roadblocks, and I realized there might be an emergent gauge symmetry in these sort of systems for its stability of the inner products and all. And that's what the realizations, and I worked out few of the methodology, and an emergent charge, topological charge conservation, which is required to stabilize this system that I will talk about. And I will show one experimental result, recent result, which we can explain if we include this topological charge conservation or emergent gauge theory. And a while ago, we wrote a review on non-Hermitian topological systems, and I think we sort of went all aspects of non-Hermitian systems, their quantum theory, and all the latest developments of topology in the non-Hermitian setup. So this is the first one, and second one is partly what I'm going to talk about, and yes, and something we are writing. So I'll start with some sort of a semantic questions that people have been asking for century, is like why quantizations, why topology, and how sort of topology field entered into physics, if you like it entered through QCD, and slowly it went to vortex and scarmions, and then it landed in band theory. So I will eventually get to band theory, but let me just start with how it entered. So it was sort of enter with this sort of a questions people used to be wondering, like why charges are always quantized, despite that if you have many charges, things can screen and charge can change, but other charges remain same and everything else gets screened, if you like. So it was sort of a trivia. It's not exactly what is relevant to us, is that Lord Kelvin once proposed that atoms are nothing but topological objects and not kind of vortex in the ether, and also there are a lot of experiments and discussion in Scotland in those years. People are looking for vortex in ether and all. So he proposed that, and it was then again turned down. But now we know that vortex are actually topological objects. So there is a particle duality to it, in which there is a quantization. But more realistically, it is the Dirac who sort of proposed this idea of monopole as a result of charge quantization, or one can also think in the vice versa way. For example, now we know that what he talked about monopole topological configurations. The monopole configuration is nothing but a Aharonov-Bohm effect. So, and then it was the Scarmi who really implemented this idea and introduced the idea, and at the same time many people probably did, is how these elementary excitations like quark and all has quantized charge. They are nothing but a relation of related to topology, variant number and all, and also has a like this. So with that maybe I'll just skip it and just skim through it very quickly, saying that studies of non-Hermitian systems dates back to the early days of quantum mechanics, and there are many approaches to it. But even nowadays, also we take it as a mathematical tool. For example, in bosonic systems and many other cases, and even now we have real materials. So with that, I'll start with to give a flavor of what is the PT-symmetric quantum mechanics and what are the roadblocks. So let me do it by a direct comparison with what it would look like for a Hermitian case. So Carl Bender was the mathematician who sort of started working on it. He also did the first experiment apparently, to realize PT symmetric system. So here it is. So we had these two postulates of quantum mechanics in which you have this probability and you have the energy which are measurable, and you write in terms of the some inner product of some wave function, and your energies are there is an operator or Hermitian, and you take the expectation value of it. And if you define your inner product this way, psi dagger psi, and you can, let me see what is my next. Yeah. So you can actually start with it, and you can demand that the total probability is 1 and conserved. And with that, you can derive the condition for H, which will turn out to be Hermitian. It has the same Dirac conjugation. And also time evolution of the state will turn out to be governed entirely by the Hamiltonian itself. Yeah. So it was a consistent thing. But then you would find that there are many Hamiltonians in which these two facts are realized, that your probability or the number of particles remain conserved, energies are conserved, but it is not defined by a Hermitian system. And then there is a subclass of those non-Hermitian systems which are PT symmetric. So that means there is a parity time reversal symmetry with which it commutes, and you can show that this is good enough to give you real eigenvalue. So one problem is solved. But the second one, when you try to do that, it turns out to be a sort of a problem. It says the probability of the inner product is not positive definite. Okay, in this description. So then Bender proposed an operator, or he realized later that it's a symmetry called C symmetry. And once you sort of put this non-local operator, I'll show that it's non-local, right? Yeah. And then this C operator with psi PT, I just put this row from here, and then it becomes 1. Okay. So one can work it out what should be C. So for example, the dual space of psi in PT symmetric is not just a PT conjugate, rather we can call it CPT conjugate. So that's the dual space, and it's a non-local propagator sort of thing. So the other one can call it a CPT invariant system. Okay, and then we figure out that C operator commutes with the Hamiltonian, and it has the same eigenfunction as the Hamiltonian, so it's a symmetry. So that's what he said, and there is no, so we do not know what does this symmetry mean. What sort of symmetry it is? Is it a physical symmetry and all? So that's why a lot of people had a raised eyebrow about this PT symmetric system and so on. Okay, so this is what the roadblock is in a nutshell. So let me then try to introduce the reason for finding it to be a gauge symmetry is this. So if I just try to look for the gauge symmetry in the Hermitian system, we know that the inner product or the probability density is gauge invariant. Even for a local gauge, it's invariant. If you just use the arbitrariness of the gauge for each wave function, this one is gauge invariant. It doesn't change. Inner product is gauge invariant. And the Hamiltonian, the kinetic energy part usually changes because of the non-local property. So it's gauge covariant. If you have a magnetic field, a vector potential that can absorb it and everything is fine. But without magnetic field, you have only two possibilities. One is omega, which is the omega, the scalar field is a constant. So that means there is no, fine. So then, so this is a global gauge symmetry. And there is another solution, which is topology, in which if there is an emergent gauge field, which is defined by the gradient of a scalar function, then obviously the curl of this is 0. So it's a conservative field. So it doesn't change your energy or anything. So this is a perfectly valid way to define gauge symmetry. And you see that I will show you in a bit more details that if the omega has two values plus minus 1 as x goes to plus minus infinity, so it's like a step function, then this sort of local gauge freedom is allowed. And what you will find out that that omega is also sort of a step function, so A is singular wherever the step function is going steep, and we can choose it to be anywhere like x equal to 0. And if a particle is going not wrapping that singularity, you have a trivial one, so it doesn't acquire any field, any phase, so it's a trivial. So you can contract this contour to 0, no problem. But if a particle's trajectory is wrapping this one, it has to have only the phase can only change by 2 pi because of the single valuedness. So that's the Aharonov-Bohm effect, or yeah. So that gives the proposal of a singular gauge, which is the monopole, or the Berry phase if you define it in the momentum space. So if you try to do that for the PT symmetric case, even at the inner product case, we have a problem. The reason being, here the dual space is not a local thing. It's actually the dual space live on the other side of the space, which is the parity conjugate, and you can have this freedom of choosing the local field different, and this is itself is not gauge invariant, and obviously Hamiltonian is not. So this is sort of our starting point. Okay, and so how do we approach it? The way we approach it is that there must be so we need to gauge fix. We need to fix the gauge. So you have this state, you have to bring it to here to take this inner product, and there has to be a parallel transporter, or additivity transporter. There are many names of the same thing, like a Wilson operator and all. Mathematicians probably use even many more names. Yeah, so whose job would be to fix the gauge, and more specifically, its job would be to keep the quantum number of this state that it is carrying, like charge and spin, has to be invariant, so that it has to, yeah. And also, this non-local operator, propagator, must be path independent, right? It depends, it shouldn't matter in which path you have integrated, you have taken to come to here. So based on these two facts, we can sort of think of Cx prime x as like some infinitesimal change from one space to another one. So the first, and we can do a Taylor series. Really, the first one is the identity. It doesn't do anything. We'll realize that this is a continuous symmetry slowly. And then you can take the first order term. So this one we can write just a notation, delta x times some gauge field. Yeah. So this is the vector potential and some charge, which is undefined for the time being, but it will turn out to be the topological charge. And it's a symmetry, because if you want to get to a larger propagator, you can build on it by taking a product of these things that all the small cores can fill, and you can exponentiate this one. So it's a continuous symmetry. It's a gauge symmetry. Because you can go from x to x prime by taking a line integral along any path. And it is a it will be a topological, I'll show in a bit, that will say that it will not be path dependent. Okay, so it's called a connection or gauge field. Let me do this for an example of a U1 gauge. So that means it's just a scalar field, and it is exactly the same thing I showed earlier for the Hermitian case. That this has to then depend on a gradient of some potential, scalar potential. Okay, and that potential has to have a plus minus 1. So it has to have a step function around it. So this line will be an obstruction to the gauge fixing. So it has to have a change as x goes to +1 to -1. And this is also called pure gauge. So you can use any other gauge, which are called small gauge and all, but there is only one singular gauge that you cannot remove. Everything else you can remove. So that's why it's called a pure gauge in the literature. Anyway, so omega will have this sort of a form, and this shape doesn't matter. It only depends on the boundary at x2 minus x. Okay, and wherever it has a sort of a step function, you can choose whichever way you want to model the step function. A will be singular there, like a delta function. So it will be like a monopole. But this is all emergent. There is no external magnetic field here. Okay. And then you find the C operator will only depends on these two boundary values. And by the fact that the quantum number and everything has to be same, and by the fact that it has to be single value, so the omega has to change by this value of 2 pi n. N will be the winding number. So you can actually figure out where this omega come from the wave function. It will find that as this psi has gone from here to here, it actually has wind in its complex span, and n will be an integer winding. Okay. And then if you substitute this one here, you will find that it will turn out to be minus 1 to the power n. And this is exactly the eigenvalue that Carl Bender proposed to get a PT symmetric system, to define a unitary inner product. This is and that's what we now prove it from here. So this has to be a topological one. So what this means, all the
Tanmay, just a clarification. So this this operation is like a reflection about x equal to 0 line?
Yeah, we call it parity, but you know that in parity is it's a reflection, because
okay, I'll ask a question.
Yeah,
okay, I'll ask a question
minus
at the end of your talk. Thanks.
So yeah. Yes. Okay. Fine. Okay. So then all the eigenstates of your Hamiltonian are defined by the different winding number. So winding number becomes a good quantum number for this Hamiltonian, right? Because this n, which I actually didn't show, maybe I should have shown it, or maybe it is here. So all the eigenstates are defined by n, and they are all nothing but the winding number of those states. Okay. Fine. And you can also go ahead and do this for a degenerate case. Oh yeah, one more thing I didn't talk about, which I will talk about in a bit. Although I said U1, but then I put a U1 PT. So what I am going to show in a bit is that this is not a unitary. Okay, it's actually a PT invariant gauge, PT invariant symmetry. Okay, so that's why we call it PT. I'll show how that comes. And the same thing here. Instead of SUN, we can just call it, just give it a name, SUPT.
Tanmay, you have 6 minutes.
Oh, I am almost done. Anyway, so if we have a n-fold degeneracy, your gauge field can now live on that manifold of that UN or that SUN group. And so here the earlier gauge field will now become like this, and you can show that this will also be Carl free, and it has all the property that we had earlier. And so again, it will have a topological structure as we had it for U1, but the criteria it had to be is that at r equal to 0 and r equal to infinity, this has to go back to unit matrix. In between, it can take any other value. So what this looks like, and then you can write it in terms of the generator of your SUN generators, and then these are the coefficients, and these are some unimodular coefficients, and you can sort of look for a so I did it for SU2. So there are 3 generators for sigma matrices, sigma X, sigma Y, sigma Z. So in all this manifold, this criteria will be satisfied if you have this sort of an onion ring sort of thing. So if you have this omega r, which takes a functional value of r, which goes like everywhere it hits a point where omega n is 2 pi times n. I don't know if I have it. Yeah. Anyway, so everywhere it will have these things, and this is where the wave functions will be living. It's very similar to the instanton sort of solutions that people wrote. So anyway, so once you put that, so everywhere you get this 2 pi n, 4 pi n and all before it gets to some n at the infinity. And in all these cases, this is identity. So you'll get minus 1 to the power n. I just put it 2 pi n here. Okay. And then it gives exactly the same symmetry that Carl Bender talked about. Okay. So then coming back to what we mean by this PT and how do we realize it. So let's say we have this state, then we give a rotations with respect to some matrix. And for the typical Hermitian case, we know that the inner product has to be same, and we figure out that these are unitary. But here we know that the CPT inner product has to be invariant, not just the psi dagger psi. So to have this inner product to be conjugate under this rotation, we figure out that this matrices has to follow this property. So instead of dagger, you will have a CPT conjugate, and transpose comes because exactly the same way the transpose came for a Dirac conjugations. Okay, and PT is time reversal is usually a antilinear that always gives you the complex conjugation. So if there is no P or C, you can just think of it. T does the job of a complex conjugation, and then you have the transpose. But this is the replacement of unitary group. So it will be PT group. And another interesting thing we find is that, so the Hamiltonian will have the PT symmetric Hamiltonian will have all these eigenvalues, and the eigenvalues all will be enumerated by the different winding number. But the time evolution will not be determined by this Hamiltonian only. And if you work it out, you will find that the time evolution will be determined for the same state, which are the eigenvalues of H, determined by a connection, gauge connection, which will be the gauge connection here, which will obtain to be C dagger. Okay. So then it will be a CPT covariant derivative, which is very kind of the analog of unitary covariant derivative is this one, where it will be again the same way. The gauge field or all the derivatives will change like this. Okay, so this is the theory, and I will show that this works very nicely to explain one of these recent experiments. So in the experiment, the way they realize this non-Hermitian system is that you take a two-level system, and only one of them is connected to some bath, to some excited state where you can pump the particle out from one of them. And these two states are connected by some hopping J. To define this Hamiltonian, you have, to define the system, you have this Hamiltonian. So these two labels are connected by J, and there is a loss term, which is defined by I gamma. Gamma can be related to how the particles, the rate of change of the particle number. Okay. So this one is a non-Hermitian. So obviously, if you, and for this case, they observed that the number of particles are conjugate and the eigenvalues are real. But if you try to model this in terms of the typical Hermitian quantum mechanics, it will fail because this is not Hermitian. But it will, so you will have a success with the PT invariant quantum mechanics. Okay. But this is not also PT invariant. So what we do is that you extract out a PT invariant Hamiltonian from here, and you will have a left out term which will be PT anti-PT symmetric one. And that is what is going to come out to be here. Whereas all the states, eigenstates, or the basis that you can choose, much like what you have done here for the PT invariant one. And you can build your Hilbert space for that. And this will turn out to give you the dynamics. Okay. So the PT operator will be this, and time reversal symmetry is just the complex conjugation, and it's a PT symmetric one. You can show energy eigenvalues are real as long as this quantity is positive, and there is a region of parameter space that these guys can tune to achieve this PT symmetric region. This is called PT symmetric, PT unbroken region. Okay.
Then may I please bind up?
10 seconds. Okay.
Okay.
So the PT invariant inner product is again has this problem. Then C operator you can figure out CPT will work, and then you will find that the probability density can be split into a PT1 which is conservative, and then extra one which will turn out to be exactly what we proposed. So this will be the decaying part and this will be the oscillatory part. So with that, I'll conclude that we showed that PT symmetric quantum mechanics makes sense, and we are able to resolve one of the puzzle is this extra symmetry that Carl Bender invoked. It turned out to be a gauge symmetry. And yeah, so static solutions are denoted by one Hamiltonian, whereas the dynamics is denoted by Hamiltonian plus this emergent gauge potential. With that, I conclude. Thank you.
Okay, thank you very much, Tanmay, for nice talk. We'll take one question, quick question. Please.
Manu, can I ask?
Please.
Tanmay.
Yeah.
So I think what you're saying is that, see, the space.
So who is asking, by the way?
This is Sorin here.
Yes, okay.
Hi. So this is so when you are essentially identifying the dual space, you are saying initially when you have Hermitian Hamiltonian, the dual space is simply given by the Hermitian conjugation.
Yeah.
Now, once you have a non-Hermitian object, you have left eigenstates and right eigenstates. And now you can say that what is the map which takes me from left to right eigenstate, and that map will automatically give you this construction of the operator which you're proposing, right? Whatever you call it.
I'm not using left and right. Right.
I mean,
yeah, so I'm defining everything in terms of Hamiltonian only.
Right. So you have to define dual space, right? The moment you define the bras, you have to define the kets in some sense.
This is
and
the
once you have right. So once you define the bras and the ket carefully, then everything is fixed. This is just that the bras and kets are not connected by a dagger. It's a different operation. Is that correct? I mean, this is the essence of the story.
Because the dual space lives in a different space-time coordinate than your original space. So you need to have a parallel transporter. You need to have a propagator to bring that state to here, whose job would be to fix the gauge.
Yeah, because this non-locality, of course, comes in when you're looking at continuum. Imagine you're looking at a 2-level or a 3-level system, then the interpretations. I mean, this is nothing to do with non-locality. It is an intrinsic property of the math you are doing, right? The structure is just there.
Yeah.
And
so if you are, go on. So if you are sort of thinking of a 2-level system, so that means you are sort of the parity conjugate would be going to the another basis, right?
Yeah.
You have one basis, state is defined in one sublattice, let's say, and the dual space is defined in another sublattice.
And other thing which is very important, which I probably don't understand here, is you see the gauge part is a part of one. So Berry phase part is one part of the problem. When you define these objects, you have this, you can define on your Hilbert space, you can define this symmetric and antisymmetric, fully antisymmetric and fully symmetric matrix, one of which defines the gauge field, and other one defines the metric tensor on the space, right? And they are dual. In a sense, they are independent information. One defines the distance of notion of distance between states. The other one defines the phase aspect of it. Right. So you are looking at a part of it probably when you are looking at this phase aspect of it, the geometric phase aspect of it.
Many things, so we have to break it out. Maybe. So at some point you're talking about metrics. I didn't introduce metric. In principle, if you want to define in terms of metrics, C operator will turn out to be a metric.
No, that's not what I'm saying. I'm the space of state has a underlying metric space.
Oh, metric.
Right? There's metric space in it, right? And this phase, the notion of how the phases operate and the notion of how the metric space, they are dual to each other. So one is antisymmetric, fully antisymmetric one gives you the notion of magnetic field, monopoles and all this stuff. The other one gives you really this notion of distance and so on the space of states. And they are connected with each other. One is
Are you saying things which are related to
May I request both of you to continue this discussion?
Oh, sorry.
Right? Yeah. Okay. So let's thank Professor Tanmay Das for nice and interesting talk. So our next speaker is Sayanjana, and he's going to talk about the metal insulator transition and band topology in driven strongly correlated systems. Sayanjana, can you please share your talk?
Yeah.
Okay.
So am I audible, sir?
Yeah. You have to be louder.
So Yeah, because there is a problem in my microphone. Now it is fine, right? Yeah. So I would like to thank the organizers for giving me the chance for present my recent work here. So I will be talking about this interplay of periodic drive and correlation effect in this triangular lattice. So this work has been done in collaboration with my guide Orit Saha and Anamitra from Niger and Priyanka from KR from Delhi. And this is a journal reference of our work. Yeah. So these are the basic outline of my work. So first I will discuss about this band topology of this driven triangular lattice in the non-interacting theory. Then I will discuss about the interaction within this Leviton midfield, and then I will give some possible experimental realization of our work. And I will.
Ryan, can you please bring your microphone near your mouth? I mean, because it seems it's very far.
Oh, now it is fine.
Yeah, it is better, but it seems that in between it moves away or something.
Okay, so I will talk a bit louder. Yeah, thank you, sir. Yeah, so this is the basic diagram for our triangular lattice. So we can see that there is this triangular lattice has three sides pyramid cell, and these are denoted by A, B, and C. And this TAB and TSA and TBC is the nearest neighbor hopping terms. And this is the free Hamiltonian for this triangular lattice. Now we drive this lattice by some external periodic field, and this AT is the vector potential for this field. And as we are considering here the circular polarized light, so we consider this phase difference between these two as pi by 2, and this omega is the frequency of the light. Now to incorporate this vector potential, so we use Piaget substitution, and rather we use the high frequency Bilow-Agnot theory in the high frequency regime to have this effective time independent Hamiltonian. So I did not go to these details of this derivation. So this whole derivation is in our paper. So if you are interested, you can look into it. So I just say that this effect of this drive not only denormalizes the next nearest neighbor terms in this hopping, also it generates some next nearest neighbor terms which are chiral in nature between this A, B, and C sublattices. So this is the picture of this next nearest neighbor terms. So this figure is for this A terms. So one can see there is 6 terms which are appearing due to this drive, and the amplitude of this next nearest neighbor term is proportional to the square of this AB and AC. So one can see that if we take all the nearest neighbor terms to be equal, like TAB and TAC is equal to TBC, then we just switch off all this next nearest neighbor interaction. So we have to choose particular values for this next nearest neighbor term. Now we just see the band structure of this driven system in the non-interacting limit. So for this, we consider this omega to be 10, and TAB and TAC is equal to 0.5, and TBC equal to T. So that shows that this AA hopping has to be switched off, and this TBB and TCC hopping will be same. So in the undriven case, one can see that the three bands touches with each other, and this is the cartoon of these three bands. And in the half filling, one can see that the chemical potential is always in the middle band. As this middle band is already dispersive, so one can see that this is a metallic state. And also, if we switch on the interaction a little bit, like A equal to 1.5, so we can see that though there is a gap opening between these three bands, but again the chemical potential lies in the middle band, and also this middle band is dispersive. So again we have the metallic phase. And again, if A equal to 3, then the gap always closes, and also there is a metallic state. So we can see that half-filled triangular lattice always have a metallic ground state in the driven case. Now, before going to the interaction case, I just want to spend some time on this Leviton mean field that I have used to solve this interaction problem. So in Leviton mean field theory, this electron degrees of freedom has been decoupled in some spin-on and this rotor part. And similarly, one can rewrite this electronic creation and annihilation operator as a product of this spin-on and this rotor term. And this rotor creation and annihilation operator are defined like this. And to exclude some of the unphysical states in the extended Hilbert space of this spin-on and rotor, so we constrain the system by this constant term in the half-field case. Now, the last task we have is that to solve this spin-on and rotor Hamiltonian term in a self-consistent manner by considering this constant in the mean field level, also by employing some of the chemical potential, some suitable chemical potential. So for detailed calculation, on you can see this paper by Chao and Paramkanti. Yeah. So before going to our results, I just show some of this experimental work which are done by this group, and this is some PRL paper, and here they considered some various different phases. So one can see that if this frequency is much large than the interaction term, so one can see that this off-resonant Hamiltonian can be written in some effective form, and here one can see that this interaction term is unaffected by the frequency. But if in the reverse case, when this frequency is much equal to this interaction term, so one can see that this interaction term is reduced by some h card omega. Also there induces a density tunneling term here. So also this paper also describes some time time calculations, so that I did not show here. Yeah. So now we can come to our result. So here we consider the large U limit, and in the undriven case, so it is on the purely interacting system. Now the important part is that we only consider the interaction only on the one sublattice. This is on the A sublattice, and these BC sublattice are non-interacting. So the observables we are considered here, our first observables is the rotor order parameter. So this rotor order parameter is defined like this, and this rotor order parameter we can take same as for all A sublattice throughout our system. Now, when this rotor order parameter is 0, that shows us that this charge fluctuation on the A sublattice is negligible. But so it just gives us some hint about the local mode transition. But it does not say that the ground state is insulating, because as we consider the interaction only on the A sublattice, so for metal insulator transition we rely on the sublattice resolved density of states. So now at A equal to 0 in the undriven case and U equal to 7, we can see that there is a charge gap that are coming from this A sublattice, and so we can see there is a peak at omega minus mu equal to plus minus U by 2. So these are the charge gaps, and these BC sublattice are hybridized by this TBC term. So one can see that at large U limit, the virtual charge, the connectivity between this A and BC sublattice are negligible, as the for large U, the virtual charge fluctuation is really suppressed. But this BC sublattice for the low energy limit around this Fermi energy can be connected by this TBC term. So if we see the lattice connectivity here, so we can see there is a hexagon type of here. So we can say that half filled undriven triangularities in the presence of interaction have a same metallic ground state. Now we consider this drive case. So for this, we consider like U equal to 2 and A equal to 1.5, and one can see that around this Fermi level, we have all the contribution from this A, B, and C sublattice. So we can see this ground state is a metallic one. Now, if we increase the Hubbard term from 0.2 to 4, we can see there is an insulating phase. So there is a gap around this Fermi level. So we can say so this phase is a insulating one. Now, similarly, for small u equal to 1.0 and A equal to 3.t, one can again say there is a all contribution from this A, B, and C sublattice, and this phase we are considering as a metallic one. But one can see that for A equal to 3, if we slightly increase the U from 1 to 3t, we can see there is a charge gap here from the A sublattice, but this BC also, constitute a semi-metallic phase, much like the earlier case in the A equal to 0 case. So this phase diagram, we have made this phase diagram based on this density of states, and this blue line, blue region, we consider is a metal. This regions, this metallic, and this yellow region we are considered as insulating, where there is a gap, but this dashed line considered as a same metallic one. And this diagram basically shows the AB, AC, BC, and the next generation number AA and BB hopping term as a function of the amplitude of the vector potential. Yeah, now we consider this case, why this is becoming semi-metallic one. So now we can see that at large U limit.
Sayan, you have 2 minutes.
Oh, thank you, sir. So at large U limit, this next nearest neighbor hopping terms like AA, BB, and CC terms are unaffected by this U, and also around this Fermi level, the contribution from the A sides is far, and only the low energy bands that are constituted by this BC sublattice. Now, in the large U limit, if we vary the amplitude as a function of A, one can see there is a band gap close and reopening as a function of this amplitude. And also this also accompanies with the band churn number swapping. And when there is a band gap closes, the churn number changes. And one can see that at large U limit, so this lattice connectivity between this A and BC is negligible. So this BC only constitute this lattice, and also this constitute the next nearest neighbor chiral term. So it slightly resembles like the non-interacting Knellman model. And also, as at the large U limit, the A sublattice has the occupancy of 1. So this model has stabilized in the half-field case. Now, previously we considered this spin-on term as 0 because we considered this TAA has to be 0. Now, if we just by hand we just made this term to be non-zero, so we can see there is a rotor kinetic energy term that is generating. So this physics I did not discuss here because of this time constant, but this phase diagram that we get previously are likely same. Yeah. And these are the some experimental realization based on these papers. And so for our model, we consider omega is kind of 20 to 30 kilohertz, and this next noise current can be taken as 1 kilohertz, and A can be taken as 1 to 5 kilohertz, and U can be taken as 20 to 30 kilohertz. Yeah, this is the conclusions. So we got repeated metal insulator transition, that is the phase diagram. We have non-interacting Knellman model stabilized by the strong interaction. We also has this repeated insulating and symmetric bonds, and also we calculate the band churn numbers. Yeah, thanks. Oh, thank you.
Okay, Shayan, thank you very much for interesting talk. Now we'll have one or two questions. Questions?
Can I just make a quick comment if there are no other questions?
Artidi, please go ahead.
So Shayan, somehow I find that your phase diagram looks very similar to the phase diagram of Bose-Hubbard model. It's just that wherever you see metals, there is an insulator there, and in place of insulator, there is the superfluid there. And as if there is an effective chemical potential here rather than A by 2. So is there a mapping one can do between the two models?
Yeah, Bose-Hubbard model, yes. I mean, what we have considered is a like slave rotor, and Bose, but yeah, but we are in the fermionic case.
No, I know you are starting with the fermionic Hubbard model, but I'm just by looking at the phase diagram, because it looks exactly like if you just replace metal with insulator and insulator with superfluid, it looks exactly like the phase diagram of the Bose-Hubbard model.
Aarti, if I can comment.
Yeah, sure.
So I think you're right. We did think about it. So the issue is, see, at this slave rotor problem, the rotor problem is still very close to a boson problem. So my understanding is this: the way the lobes look are artifact coming from the bosonic or the rotor physics, whereas the topology part, which is this the yellow region with this band closing by dashed line, that comes from the spin-on part.
Okay.
So you're right that the reason the lobes look like that is coming from a Bose-Hubbard. Like, of course, the boson is strictly not a rotor, but for our purposes, it is. Let's assume it to be show. So, in my understanding, that's the reason it is.
Okay. Okay. Thanks.
Yeah. So, is there any other question? No. Then I'll ask one question, and I think that will be the last. So you are using this. Finally, it turns up into the mean field like treatment, right? And you are dealing with a driven system. How much confidence you have in these calculations? Because once you have a driven system, it involves all the excited states, right?
Yes.
So how do you like check your result that it is like giving you the correct result?
Yeah, so we always considered we are in the large omega limit. and so we based this experiment that I have shown somewhere, and you can see. So they have shown that as omega is large. Yes, sir, you are listening to me? Yeah.
Yeah,
So
yeah,
as
sure.
omega is large, yeah. So as omega is large, so this is the various time scales here. Okay. So 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 as long as you are within this time scale, and as omega is large compared to these other parameters, you are, I mean, our results are good enough. But if
Okay.
we just we increase our time scales, and if this, I mean, the gaps between the various photon sectors, I mean, just closes to each other as it can be closed, so then our results will be not valid. I mean, yeah.
Okay, 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 thank you. Okay, so let's thank Sayan for interesting talk. And with this session ends, and let's thank all the speakers of this session. And thank you very much. And I hand over this session to organizers.
Thanks, Manoranjan, for chairing the session, and thank you all the speakers for nice talks. So we are running a little bit late, so the next session was supposed to begin at 3:45. Should we start 3:50, if that is okay with the speakers and the session chair?
Yeah, fine with me, absolutely.
Yeah, fine with me.
Okay, so in the meanwhile, I'll sort of make people co-host, etc. So let's meet at 3:50. So session chairs and speakers, please stay behind. I'll just, if you want to check your this thing, I'll just make. So Navneet, I've made you the co-host, and I think Amrita Bhattacharya, you are also co-host. You can try your slide if you want. In the meanwhile, I'll make the other participants co-hosts as well. Who else? Kuljit, Animesh Panda. Yeah, I can see your slides.
Yeah, I can see it. Yeah.
Yeah, so your cursor is also visible, yes. So thank you. Maybe you can unshare, and I think Shashwat Bhattacharya, you can check your this thing.
I think you have to give me permission.
I haven't given you. Sorry about that. Just
yeah.
Sorry. Yeah, could try it now.
Yep. So.
Yeah, I can see your slide.
Yes, perfect.
You want to check the full screen mode?
I did possibly.
Oh, you did? Okay. No, that's okay. Maybe I was looking somewhere else. Yeah, I can see it. Okay, fine.
Yeah.
Sorry. Okay, so who else? Animesh Panda, you are around?
Yes, yes.
Go ahead and try to share your screen.
Yeah.
Yeah, I can see your screen. Go ahead, full screen. Yeah, it's fine. I can
Cursor
see your...
is fine.
Yes, correct. That is correct.
Okay.
All right. So Kuljit Kaur,
hello.
You can.
Yeah.
Yeah, you can try. I've made you a co-host, Kuljit. Please try to share your screen.
Yeah, can you see?
Yes, it's in the full screen mode. I can see your cursor as well.
Okay, fine.
Okay, thank you. Anirban Das is probably not here. So Anirban Das, if you are around, I don't see his name. So let's wait. We'll start at 50. So there is Navneet, this one speaker is not here, Anirban Das. He is supposed to be the fourth speaker in this thing. So if the person doesn't turn up, then we will skip.
But I see him in the
Oh,
list.
you see him? I'm not seeing him. This is Anirban
Oh,
Das.
no, I see different. I mean, no.
Aninda Das.
Correct. Yes, correct.
Yeah, maybe he will show up late.
Yeah,
If
so
he shows
let's,
up, I'll check when the third speaker is going, and if I
sure.
can find him, I'll
Okay.
ask him to continue. Yeah.
Sure.
Or can we just go to the, if I cannot find the person, can I go on to the next one?
Yeah, so I think if his time comes and the person is not here, perhaps we should go in. If he joins in, it's the last talk. We'll have that person's talk.
All right.
Okay.
Sounds good.
Just let me know when to share. I'll just share my screen.
Yes, so we'll start. Start at 3:50. If you want to keep it shared, since you are the first speaker, you can keep it shared as well.
But you could not test the other person who is supposed to join, right?
Yeah, the person is not here as yet. If you want to wait for a couple of minutes, that is fine as well.
Yeah, then I'll wait and then I'll share.
Okay.
Are you able to see my screen?
Yeah,
yes.
It's clear. Yes.
Yeah, okay.
I'm able to see your cursor also. So
yeah, good.
Yeah, we'll just wait for a minute and then we'll start.
Yeah, surely.
Okay, I guess we can get going.
Yeah,
So
sure.
this is session 2B in the post-lunch period. So our first speaker for the session is Amrita Bhattacharya from IIT Bombay, and she'll be talking about exploring the charge and heat transport in thermoelectric Heusler compounds.
Yeah. So this topic is a little bit different from whatever you have been hearing until now. It's mainly because I am a part of the MEMS department, which is the material science department. And I work generally in the material science aspect and making materials better for a designed purpose. So therefore, it will be a little bit different from whatever you've heard so far, but nonetheless, it will add a little bit new flavor to your conference, I hope. And I thank the organizers for giving me this opportunity to speak in front of you. And this is the first very work that we have published from our group. So this gives me immense pleasure to share these results with you. Yeah. So we are going to talk about the problem of thermoelectrics, which is very essential and is growing very fast day by day because of the energy loss that we are suffering. And you know that 66% of the energy that is produced in the world is generally lost. So whatever we can gain from the energy that is lost is going to be very essential for our purpose, for the purpose of mankind. So this brings me to the problem of thermoelectrics. So we'll go to a little bit deeper, aspect, and we'll try to go deeper and deeper. We'll see. So ideally, the device efficiency or Carnot device efficiency is just TH minus TC by TH, which depends on the temperature dependence of the two materials. However, in real device efficiency is very much limited by the presence of this factor, which is the ZT, which which is there in this device efficiency, which we see in here. So therefore, I have plotted over here the real device efficiency as a function of ZT, and you can see that ZT basically limits the device efficiency, and you need to maximize the ZT in order to get a very good efficient thermoelectric material. So we'll see what this ZT basically depends on. So this ZT that you see in here, the thermoelectric figure of merit, depends on the microscopic quantities, which are the Seebeck, the sigma, and the thermal conductivities, which are there in the denominator. And they all have specific dependence with the carrier concentration, and therefore, having a very good ZT is a very challenging kind of problem. So we should see how to get an efficient material with a very high ZT, and then you can try to do a lot of nanostructuring and experimental modeling and everything else to improvise on that specific ZT or that specific material. So to start with the Boltzmann transport theory, this is the semi-classical Boltzmann transport theory that I have shown you in this slide. So you can see these two terms over here, which is shown in here. So these are the gradient of F, which is nothing but the Fermi-Dirac function. So it shows the gradient of F, and these are the parameters which comes and goes into your Boltzmann transport equation. So in the absence of temperature, so this factor and this factor will be equal to 0, the first two terms. However, the electric field will stay, and it will act as a perturbation, and you will have to take into account of this in this Boltzmann transport equation. As once you take this, you can find the expression for sigma. So sigma from the J, so current density. So sigma is depending upon the group velocity of electrons, the equilibrium population of the electrons, equilibrium population near the Fermi, and then the relaxation time. And now this relaxation time, which is the electron phonon relaxation time that we are talking about, generally by neglecting the electron scattering. So this is also dependent on so many different parameters. So the real challenge is to model this relaxation time, and this is one of the aspect of this work that I am going to show you right now today. So, so in the first expression that I have shown you in here, we have neglected the first two terms. But if you keep the second term, which is this grad of F, grad of the Fermi function, because the temperature will definitely play into role if you're looking at Seebeck, then this term will be kept, and then you can arrive at the expression for Seebeck, which is shown in here. The expression of Seebeck, you can see that there is a only extra term which is coming in here, which is E minus EF by KT. And this gives this type of feature to your Seebeck coefficient, which is like this. So this here we have plotted Seebeck as a function of chemical potential. This is just a schematic diagram, but we will see. So these are all very essential, and that's why I'm showing you right now. So in the single relaxation time approximation, so this is the bootstrap code. So the ingredients are shown just in the manner that they come within the bootstrap code. So you can see the group velocity is found by the derivative of your dispersion, electronic dispersion in the band structure. The Fermi function can be also found by taking the derivative of the this equilibrium population. And then this tau is the ingredient, which is the scattering lifetime, the electron phonon scattering lifetime. It depends upon the electron phonon coupling. So it's very important and very, essential to find out from first principles. But we wanted to see whether we are doing, if we are naively, taking the single relaxation time approximation, how good are we? So every parameters that you see in here will be taken from an electronic band structure, except for the tau. And then we will want to, see how it compares with the experiment. So that will be the first part. And then we can, try to see how to exactly, get an ab initio approach to find this tau. So we started this work very recently, so I won't be able to show you the completed result, but some results to give you a flavor of this. So, okay, so going over here, so this is a test case, which is zirconium nickel tin. And see this band, there is only one band which is coming over here. So this is the specific band that we are going to talk about. So since this is a single band that you see in here in the primitive cell, so we can take at least the single parabolic band approximation to start with, because this is the simplest band. However, this is a simplistic picture. So these bands are not parabolic completely, and therefore one can, have different approximations depending upon the different curvatures of the band that one can take. So what we are trying to do in here is, from first principles, we have just investigated the band structure. We know that it's a single band which is coming at the Fermi. So we are going to take the single parabolic band approximation, and we have already the experimental results that we have published in the year 2018. From here, we have just grabbed the experimental Seebeck, sigma, etc. So how we use this single parabolic band model? So what we want to do is, we want to compare the tau from the experiment with the tau from the first principles. So how exactly we do is, we proceed with the calculated value of Seebeck, and from there we use the single parabolic band model. So this is the single parabolic band model that you see in here. And this particular thing is the Boltzmann expression for Boltzmann transport coefficient. If you just, put it equate with the sigma. So from here we find the eta, which is the chemical potential. And from the eta we find the Hall prefactor and the carrier concentration and density of state effective mass. And all these parameters goes into this expression of tau, and it gives us the experimental tau, so which is shown in here. So in order to make this experimental tau more, more relevant and more, more exact with the theory, what we have done in the next step is, we have, kept only these two factors that you see, the Fermi integrals, we have kept from, the experiments. So from whatever we have found by modeling from the experiments, we have kept these two factors over here. Except for that, all these factors that you see in over here, which is the longitudinal sound velocity, the density of the solid, the deformation potential, and the effective mass at the density of state, these all are, first principles that we are going to put. So we can also put it from the experiment, but there can be some, changes that we may not account for. Because of that, we have just kept it from the, we have calculated it from first principles. So how do we calculate this? In order to calculate this, we have to use the quasi-harmonic approximation, because see, all these parameters that you see in here, the density, the m star d, this changes as a function of temperature. And this temperature is not very small temperature. This is a range of temperature from 300 to 800, 900 Kelvin that we are talking about. So this temperature dependent relation of these expressions that you see in here are very important. So we have taken all those things into account, and we have, calculated the using quasi-harmonic approximation. We have calculated the alpha, which is the coefficient of thermal expansion of solid, and for different lattice parameter, we have calculated the band structure, and from that band structure, we have calculated the m star, the deformation potential, and of course, we get the density of the solid as a function of temperature, how exactly they change. We get all these parameters from there. So using all these parameters into the and with the along with the experimental Fermi integrals, we have calculated the tau, and we get the expression of tau, which is shown like this. Tau is the electron phonon relaxation lifetime. So okay, so we get the tau, which is shown like this. And similarly, we do bootstrap calculation, a single relaxation time bootstrap calculation, and we try to compare and find the tau from there. So this is a single relaxation time calculation. We do it for different temperature ranges, and then we find the tau exactly from there. So what we see is shown in over here. So this is what the experiment is showing. So the experiment is falling like this. However, the tau is very much different from the bootstrap and experimental procedure, which is shown in here. So this can be because of two different reasons. One thing may be because this parabolic band approximation that we had taken for analyzing the experimental result was not enough. We should have taken a cane-like model, because this is also having a kind of different dispersion than parabolic. So that can be coming from there. Also because of the fact that we haven't taken into account of the electron phonon scattering lifetime explicitly from the first principles. So we have to incorporate both of them. So we are writing a module in bootstrap 2 where we can incorporate quasi-harmonic approximation and electron phonon scattering lifetime. So this is in principle one ongoing work. So I will just proceed anyway further. So now talking about the transport coefficient. So as I told you right now, so this is the tau, the scattering lifetime. But coming over to the transport coefficient, it can be also modeled. Modeled and first principles can help enormously in order to model it. So let us see how it can be modeled. So in principle, so we know already that if it is a half-filled band or a band which is like this, which is near the Fermi, then only it will take part in transport. Otherwise, the fulfilled or fulfilled band, which are shown in like this, will not take part into the transport. So we'll have to model the features near the Fermi region, and if we can find it, and if we can model a prospective designed material, then that can be very good for thermoelectric application. So I'll give you a very small example of that we have done in the past, and probably with that I'll conclude this particular talk. So yeah, this is just to show you and remind you once more that see, typically people say like for a good thermoelectric material you should have a very narrow band gap, but this is not a very relevant logic, because see, in any case you are going to dope your system, and amount of doping and where you are doping explicitly, how it is how much it is easy to dope or not, those materials are determining the thermoelectric properties. It generally does not depend upon like whether it is a very huge high band gap or not. So it doesn't depend upon that. It depends only upon the doping amount of doping that you perform. So we go ahead with this much of knowledge. So we look into the materials depending upon their properties, like how many bands that are there available near the valence band or the conduction bands, what are the degeneracies of these valleys explicitly, and if there are degeneracies, so whether they are in the same same energy or not. So these are the factors that we see in a given band structure. And any material using this type of factors, you can manage, and you can do your calculation, transport calculation, and see if they are good for thermoelectric purpose or not. So I will show you one example. So here are the factors that I have just told, like number of pockets, band degeneracies, and the number of K points degeneracies. So we will go ahead, and finally also the curvature of these bands matter, because this is directly proportional to your M star. Okay, so this is our system, which is a Heusler system that I have shown you in before as well. So this has exactly 3 atoms in the lattice, as you see. So, and the lattice, these are the typical X, Y, and Z choices. So we have taken, the one, because we wanted to show a proof of concept. So therefore we have taken the most earth abundant ones, and these are the groups that are typically used. So X, Y, and Z. So we go ahead and we try to design it. So we did a lot of high throughput loops and all that to see which material is which one is more earth abundant, which one is, which can be, substituted at which position. So those I am not going into the details, but what we did typically is like we tried to, replace this, substitute this X with another element, which is say X from some other this thing, in order to increase the mass disorder into the system. Similarly, we did it for this Y side and similarly for the Z side. So we will go ahead one by one. So our first choice was this 3-host material, which was zirconium nickel tin, titanium nickel tin, and hafnium nickel tin, as you see, because nickel is most earth abundant out of the 3, and tin is also very earth abundant. So we kept it like this. We varied the first, at the first stage, we varied this element, these 3 elements, and kept Y and Z sides same. So you can see now what happens when we substitute the first site, which is this site X site, with the dopant, and you can see like at the at a stoichiometry of 0.5 we obtain the most degenerate case, which is like this, which is the case that we would like. But then we proceed to do this calculation so further, and we see that the Y side substitution, which is shown in this figure over here, with another Y side material or a Y side element, is not very good, because it's breaking the symmetry of the bands that you see in here. So it's a symmetry breaking that is going on. So on the other hand, if you do the same thing for the Z side, if you substitute another element in the Z side, it will still typically retain the symmetry. So we were quite like, this is also very interesting, because if you see all these Heusler class, you will notice like only the one which are substituted at the Z side and the X side are good for thermoelectrics, but the Y sides ones are not good. So they are not reported in the literature, and even if they are reported to be very detrimental for thermoelectric application. So we wanted to explore the reason, and we figured out. Yeah, this is the case for showing for Z side substitution, both X and Z, and you can see that the symmetry is still retained in here. So we wanted to find the reason behind this, and we found out that this particular is the the neighbor sides, neighbors to the first neighbors to the X side substitution, which is in this case with titanium. So if you see like zirconium nickel tin 50% titanium, which is going into the site just below this, you will see the neighbor is uniformly same, and therefore the symmetry breaking doesn't take place. Similarly in the case of Z side. However, in case of Y side, what happens is this neighbor is changed, and there are 2 different elements which are the direct neighbors, and because of this symmetry breaking, actually the Y side substitution is not very good and is not generally used for thermoelectric materials. But anyway, so we proceeded and we did some thermal transport calculation with so here I should tell you that we can do similar calculations that I have shown you in Bootstrap. So you can do Schenck-BT Boltzmann transport calculation for phonons, but it is much more easier in sense that you have to do a lot of calculations, but it's still easier because it takes place at a different time scale than the electron phonon interaction. So phonon scattering lifetimes are still more easily acquirable than the electron phonon scattering lifetimes. So we have used the standard packaged code, which are this PhonoPy and Phono3Pi and SHING-BTE, and from there we find the electron phonon scattering, phonon scattering lifetime. And using all those, I am showing you the transport coefficient, and here you can see, like as I said, the Y side substitution is not good for thermoelectric. So you can see the performance is very poor. So you have to see this side, which is the peak for p-type doping and the n-type doping. So because these are the doping levels that you can think, because either you dope it to the p-type or to the n-type, and we are seeing the intrinsic transport profile. So by doping, you can see, like, we can achieve a good figure of merit or good power factor for the X side dope and the Z side dope. Whereas for the Y side dope, you see that we are not achieving anything and we are having a very poor performance. And here I am showing you the lattice thermal conductivity. You can see that double side doping generally lowers the lattice thermal conductivity. So both way, this is very good for thermoelectric application. So but this doesn't end the talk over here. The fact that you still have to really dope the system with either p-type or n-type impurity, and you can also have small impurities which without breaking the overall symmetry. So then you can micro tune these lattice parameters. So that is the last thing that I will show you and then conclude the talk. So this, if you
Amrita,
just put yeah, just 1 minute.
Yeah, sure.
Yeah, just 1 minute. So if you just put a very small fractional quantity of same side dopant, say for nickel, in this case, a very small fractional quantity of nickel in there. So it's about 1.03. You can see that the transport, so the thermal transport coefficient, the total thermal transport coefficient is getting drastically reduced. So, and this is not coming, so this is experimentally. This is not coming from the electronic part, because electronic part is very negligible. It is coming generally from the lattice part. So we also have seen what exactly is the reason behind this type of small change with only a little bit self-side doping. And we can see that this small self-side doping, if you do, so overall it retains the lattice symmetry, and therefore it is very good for electronic all the retaining all the electronic structure, so that I told you before. But however, this is very good for the for tuning the lattice thermal conductivity, and with the small impurity that you see in here, you can really lower the lattice thermal conductivity, because here this is a avoided crossing that is taking over here, and this extra excess nickel atom is a rattling mode, and it doesn't really take part into hybridization. So with this I can so you can see the experimental lattice thermal conductivity was found to be like this, whereas DFT also does very well to explain the lattice thermal conductivity, which drops down and goes up again. So with this I conclude my talk. And I do not really have a conclusion, because I have kept so many slides already. So this is my group in IIT Bombay, and right now we have set up a HPC facility. We are in the process of setting up experimental facility of our own, which is for measuring the charge and heat transport coefficients. Yes, I thank the organizers for inviting me for this talk.
Yeah, thanks Amrita for a nice talk. So we can take a couple of questions now from the audience.
Yes.
Okay, maybe when the audience is getting back, I have a question on this slide. So when you have Y very small, right? So if you're trying to calculate thermal conductivity using this SHING-BTE or something, you have to take a very large supercell.
Yeah. Typically very large supercell.
Okay, so that makes it really complicated, right? In terms of
it's really complicated, but this is a phenomena which is very nice, because if you see all the thermoelectric materials, then you will see like this type of very small percentage of doping is done at any one of the site. The reason is because if you do more, then all the exotic properties of the bands will be lost. On the other hand, if you just dope a little bit impurity, then the rattling mode will really reduce the thermal coefficient, transport coefficient.
I see. Okay, and this rattling mode will persist at higher temperatures also, is it?
Yeah.
Okay. Do we have any other questions from the audience? Actually, I have one more. Maybe I can just ask that also. So in your electron phonon scattering rates, maybe I didn't catch it, but you were calculating the tau for different electrons, or it's just a single value for the entire band?
Actually, the first one is the experiment with a direct comparison with the experiment. So therefore, in this, we do not do anything. In case of bootstrap, so whenever we find it, so we are taking all the other parameters except for electron phonon coupling. We're taking all the other parameters from bootstrap directly and comparing. So this doesn't include the electron phonon coupling directly taken from first principles. Neither it does include the temperature relaxation of the lattice.
I see. All right. Okay. Any other questions? Okay, if not, thanks Amrita for a very nice talk. So maybe you can unshare your screen and we can have the next speaker share his screen. Do we have the next speaker? Yeah. Can we start?
Yeah, just a minute.
Sure.
Yeah, I'm all done.
Okay. Yeah, so the next speaker in the session is Shashwat Bhattacharya from IIT Delhi, and he'll be talking about self-energy and exotonic effects in undoped TiO2 anodase.
So thanks, Navneet, for introduction, and I'm also thankful to all the organizers for inviting me. So today I'm going to talk about something, a very old system, which is already well known for the last 2 decades or even more. That is TiO2. So almost all the people who are working on the materials physics or materials chemistry, they will all know it. But still, there are many things that people really do not care when they do the simulations, and that's why we are revisiting this old wide bandgap semiconductor TiO2 once again. So this talk is broadly on defects in semiconductors. So I will briefly introduce what they are actually, why they are important, and then the fundamental challenges that why and how one can sort of model defects in semiconductor and start understanding their properties, especially the electronic properties accurately. And then I will show some results and I will conclude. So once you try to synthesize a material in an experiment, so usually the experiment is under a reactive atmosphere. So suppose this is your chamber and this is the material that you are trying to synthesize. And usually you have an atmosphere which can be oxygen, which can be nitrogen, which can be hydrogen, or it can be any kind of ligands. And then what happens that this material reacts with this environment and it forms different types of defects. For example, you see that these are different configurations. So once you get to know that, then the next idea is that what are the structure of these materials and who are amongst all these possible structures, who are the most stable one and more likely to appear in the experiment. And that's the next step to understand. And once you get to know that, then only it makes sense to do the electronic structure calculations or to understand the excited state properties of that material. But this step is crucial. So one such example, for example, I'm showing you as a brief, like you see here, you have a clean surface, but this surface will not remain as a clean surface like this. It will have a vacancy as interstitial or a mixed interstitial, something like that. And then if you try to understand this from the theoretical perspective, just by employing a Fermi function using, say, Fermi-Dirac statistics, so then it will become a temperature function, and you will see that some defects will come down in terms of its concentration and some defects will come up from the concentration, and then in real experiment, depending on the temperature and pressure of the chamber, then different material will have a different properties. So for example, if we are talking about low temperature, then definitely you should try to understand the electronic properties of this type of defects out of this entire list. And if you're talking about high temperature, then maybe these two defects are more prominent. So understanding this step is extremely important before doing a full-fledged electronic structure analysis. Now, how we do that? So the first problem is that the structure, of course, and this is really important to understand. And if we have some experimental input to know the structure, especially from NMR studies and so on, then it is very good. But if we do not have it, then also it is not a big problem. I mean, we have developed a code which is cascade genetic algorithm, and using that we can sort of understand from scratch the different possible structure of the potential energy surface. And then we try to understand that, okay, these are the possible structures. But many times it also happens that the structure which are energetically favored are not actually the interesting structure appearing in the experiment. So in such cases, we have to understand the metastable structures also. So these are a completely different topic. I'm not going to go into that, but we have developed methodologies where we can, in principle, search metastable structures also very accurately to mimic with the experiments. So once we get to know the structures, then the next step is to understand the environmental effects, that where the material is stable or not. And that we do using ab initio atomistic thermodynamics, where we include the vibrational free energy up to harmonic approximations. But in some cases, we need to go up to anharmonic, I mean, at higher temperature, anharmonic effects are also sometimes crucial. So this we include using thermodynamic integration methods, and these are the references where we have developed these methodologies. And then once you get to know that after this step 1 and step 2, we do the electronic structure analysis using DFT and way beyond DFT calculations like GW, BSc, RPA kind of methodologies. So in this talk, I'm basically focusing on this particular aspect, like doped TiO2. And we are trying to understand that thermodynamically stable phases of the dopant, and if they are good enough to give response in the visible light. Because you all know that TiO2 is a wide bandgap semiconductor, almost like insulator. I mean, that's why it does not react within visible light region. And that's why if you can put some non-metal dopants, and if it shows this. And then there are certain challenges that this material is oxide material, and oxides are quite complicated material. And that's why I'm going to show you some results on that, how accurate methodology you really need to capture its excitonic effects. And then only you can talk about its optical properties. And then I will comment also on that, okay, what type of dopants you have, if it N-type or P-type, based on that, its optical property gets varied. So first, let us try to understand that what type of methodology is good enough for this type of material. So here what I'm doing is that I'm calculating the formation energy of a single oxygen vacancy at various charge states. So this is the expressions for the formation energy. This is the chemical potential of the oxygen or the defects that I'm making. And this is the chemical potential of electron, which means the amount of energy you need to add or subtract from the reservoir for doing that. And then I'm plotting here the formation energy, and here I'm varying the chemical potential of electron to mimic whether it is a p-type conditions or a n-type conditions. And then you see with semi-local functionals within the limit of DFT, you see here the +2 charge state is more stable, and this is -2 charge state when the material is highly n-type doped. But if you do include the advanced functionals, the real Hartree-Fock kind of exact exchange into HSC functionals, then you see the situation is different. It is only +2 charge state, which is always stable. Now, some of the researchers, they feel that they can correct everything of the limitations of the semi-local functionals by adding just a U. But adding a U can fix your band gap by arbitrarily localizing your d orbital, but it does not help to correct the energetics. So you see that even with GGA plus U, things are not at all improved. So this means that you have to do everything at least at the HSE06 level to include the electronic exact exchange kind of interactions. So then with that, we have tried to set up different type of models, like this is substitution defect, this is interstitial defect, and this is called split interstitial, and where you have substitution and interstitial both together. And X is the different types of non-metal that I'm going to add. And then if I just minimize the free energy of formations, and then I get a phase diagram which looks like this. And this μi is the chemical potential of the species, and it depends on the temperature and pressure. So depending on the temperature and pressure of the experiment, I can fix this μi. And at the lowest limit, when I have a very poor oxygen concentration in the environment, I call it O poor region. Similarly, I have a O rich region and O intermediate region, which is sort of mimicking the actual experiment, which is something not too poor, not too high. And then I see if I can club these three into one 3D phase diagram, which ends up like this. Here I have plotted the chemical potential of electron, and here I have plotted the chemical potential of oxygen. And then I can clearly say that, okay, which type of defects are stable at what temperature and pressures, because at the z-axis, vertical to the screen, and it is the formation energy, the negative formation energy actually. So you can clearly see that what type of defects are stable at what conditions. So you see, for example, this means highly N-type region, this means highly P-type region, and this is highly oxygen dense atmosphere, highly oxygen rarefied atmosphere, and so on and so forth. Now, if I do the same thing with all different types of defects like nitrogen, carbon, sulfur, selenium, then I have a clear phase diagram, and this red region is basically showing the interesting region for the experimentalist. And I see that in general, substitutional defects are quite stable, and that is also experimentally been synthesized by various groups. So I try to understand that, okay, if it is so, then what is the optical property of this type of defects? Are they really good enough to show visible light response? And then I did a simple configurational coordinate diagram where I tried to see how the structure is responding with respect to different charts, be it +1 or -1, and I can calculate sort of the emission energy that it requires to jump one electron from this to here. But this does not give me the real picture of the whole optical spectra. It just gives me the idea that, okay, they are responsive in the visible region. So S, SE, N, and C kind of defects, I mean the non-metal substitutional defects, they are good to show me visible light response, but not phosphorus. So these four can be taken up to study further. But the problem is that the methodology, because you see here in density functional theory, what I am doing is that I am trying to understand an interacting system by mimicking it with a non-interacting system, which is like this. And I am ensuring that the density is same in these two things. This works very nice to get all the ground state properties of the material, but at the cost of losing the interpretability of this eigenfunction and the wave function. So these are fictitious of this particular system. So this has no meaning. I mean, if I try to understand situations like this, like I want to probe, say, valence band region, I shine light, eject one electron from here. And if I try to understand that how much energy is absorbed, so this is typically a photoemission experiment. If I want to do the same thing in the inverse photoemission experiment, that means I bring an electron in the conduction band and I detect the energy emitted by the light, then this is also something is not possible, because this case, Consham, this thing is not having any proper interpretability. Now, if I want to do both, then I can sort of probe the conduction band and the valence band very well. And if I take the difference of I minus A, that is the ionization and the affinity, I can get sort of the optical gap. So this is what one can do under the framework of many-body perturbation theory, where we introduce a quasi-particle energy eigenstate, where we start from the DFT Consham exchange correlations, and then we actually update it from this self-energy operator by taking the difference of this Consham sort of potential into this matrix, and this is sort of quite expensive to do that, but it should be given like it should be done like this, because let me introduce why this quasi-particle nature is important. Because once I try to shine light to eject one electron, this hole is formed here, but it will not remain static here. So this will create a time-dependent polarization due to creation of that, and then at the end it will reformalize into situation like this, where you see that if you try to understand the electron and the hole, this interaction, and the electron is still here, but the interaction is pretty different, because now this hole is surrounded by these electrons, and these are sort of giving a kind of screening effect. So now if you do not really take into account this part, then you are doing something wrong. And that's the concept of quasi-particle. So this is why dynamical screening of hole is extremely important in the form of quasi-particle. And that is exactly the W of these GW approximations, which is screened Coulomb interactions. And if you do that, then in principle, you can write down this whole thing like the polarizability, which comes like this. And if you truncate to the first order term, and then you can calculate in principle susceptibility, conductivity, dielectric tensor, everything, I mean, quite accurately. So that's exactly what we do in these GW approximations to sort of probe the band gap pretty accurately. But that is also not sufficient to give me the spectra. So to get the spectra, I have to go one level up, I mean, of this. And these also come under the framework of many-body perturbation theory. But what we do is that we shine light, and then we eject electron from the valence band, but not as much energy as in the previous case, so that this electron and hole forms a bound state. And this is what we call the formation of exciton. And then you can, in principle, calculate this by solving a two-particle Schrodinger equations, where you have electron Hamiltonian, and then you have a hole Hamiltonian, and this is the electron-hole interactions. So this comes under the Bethe-Salpeter equations. So this is sort of the methodology that one really needs to go to understand optical property under this whole situations. And this sort of summarizes the whole thing. The GW improves the estimation of the fundamental gap, definitely compared to DFT, but it overestimated band gap calculated by GW should be, I mean, improved more by inclusion of the BSE. This part, this electron hole kind of interactions that one has to include within BSE. And then BSE introduces the excitonic binding energy to obtain the optical gap. And also BSE includes two-particle correlation and gives better description of the absorption spectra. So that's what the whole idea. So now let me get back to my system, that is pristine TiO2. And what I showed you in the previous slide, you see here, once I do GW, this also depends on the starting point, that is the Consham starting point. And then we are updating it. So if the starting point is a crap, then even if you keep on updating it, you will not get a good results. So that's why we showed here that if you do if you plot the imaginary part of the dielectric function and the real part of the dielectric function with respect to PBE, then this comes 6.88, which is not at all close to experimental value. But if you do it with the static part of the real part of the dielectric constant, if you plot it with HSE06, then this value is quite close to the experimental value. So even if you try to sort of correct it with GW or BSE, then it makes more sense to start with respect to HSE rather than start with respect to GW, unless and until you are doing self-consistent GW, which is extremely expensive. And then what we did is that we exactly tried to reproduce this TiO2, and these are the this is just showing the convergence. And then you see that the experimental number is 5.62 and the theoretical number is very close to that. So this means the methodology is good enough to reproduce pristine TiO2. Now with that, we can really try to understand that, okay, how it behaves once we are talking about the doped TiO2. So then what we did is that, so now this is the comparison. So we have taken a doped TiO2, no, so this is still TiO2. I'm just showing the exciton matching with respect to experiment. You see that this is the excitonic peak, which comes only with BSE, this line, and this red is the experimental part. And this matches very nicely and with this experiment. So this is sort of the validations that this BSE is really good to reproduce my experiment, and neither HSE nor GW are really good enough to reproduce the experiment. So that means you have to go to the highest level, that is within after inclusion of the electron hole interaction. So then I'm talking about some doped system. So here you see I'm showing two systems, that is S doped TiO2 and Se doped TiO2. So here you see that there is something important. So this part is the imaginary part of the dielectric constant, and this is splitted once E is parallel to XY direction, I mean the polarization, and when E is parallel to Z. And then here you see that this is responsive in the visible region once E is parallel to XY, but this is not responsive when E is parallel to Z. So there is definitely some optical anisotropy. And this is the same case where when I am talking about AC doped TiO2 also. Here also you see this optical anisotropy, which is not present in the Z direction. But if I do it with say nitrogen and carbon, then the situation is different. So they are optically active both in XY as well as in the Z direction. So this is Z and this is Z directions. Here you can clearly see that there is a response, and along Y directions also there is a clear response. So this means once we are talking about S or AC doped TiO2, so they are sort of optically inactive along Z, but once we are talking about N and C, they are optically active in all directions. So why this is appearing? They're appearing that one has to understand that some nonmetals are giving optical anisotropy and some nonmetals are not giving optical anisotropy. So is there anything with respect to the kind of dopants we have given? So what we see is that, so how much time I have? Another 2-3 minutes, I guess.
You have 5 minutes. So
okay, great. So then I'm having quite much more time than I need. Perfect. So you see here, I'm plotting the density of states for p-type dopants, and this is the system, the pristine system. The moment you dope it with say S or AC, you get, this is the density of states, and these are your defect level. Now you see that this defect level is close to the VBM, so the valence band. So that means these are p-type dopants. And if I try to understand its sort of the contributions of the px, py, and pz orbitals, for example, for this S-related defect, you can clearly see that the xy contributions is more in the Fermi region, and the Z contribution is far away. And the same thing is true for a selenium doped TiO2 also. Here also, if you see that px, py contribution is kind of here, and pz is a bit far from the Fermi energy. So that's why these two are optically inactive along the Z directions. But if I talk about the N-type dopants, so here you see that this is the pristine, and this is the defect level, and this is formed near conduction band. So that does mean that this is N-type dopant. So for N-type dopants, the situation is not that. Here you have simultaneously contributions from both px, py, and pz. And as a matter of fact, you get them all optically active in all directions. So for example, if I go back to this, here you see this is sort of optically active in all directions. And this one here, these two are optically inactive in these two regions. Now, to understand all these things, definitely you have to go to the highest level under the framework of BSc. And then let me conclude. So we are talking about doped TiO2. The basic intention was that we were trying to understand the thermodynamically stable defects, number one, and then for their good optical response under visible light. And then we tried to validate everything with pristine TiO2, and that's exactly what we did, because there are many experimental results which are available on pristine TiO2. And then we showed that, okay, we have found few dopants which are definitely good enough to show optical response within the visible region, but they are very much sensitive to capture the excitonic effects. And that's why we gave a clear idea of the comparison of the hybrid DFT vis-a-vis GW and vis-a-vis Bethe-Salpeter equations. And then we talked about the optical properties of the doped TiO2, the correlations with the nature of dopants. That's exactly that some dopants are optically active and some dopants are not optically active in all the directions. So then the main conclusion is that substitutional defects are the stable one. From there, optical response of AC, N, C, S are in the visible region. And then this is the main conclusion, that the PAC is indispensable to reproduce the experiment, and P-type dopants show optical anisotropy, and the reasons is explained in the previous slide. So with this, let me thank my group members in particular, especially the student, my PhD student Pooja Vasera. So she is going to join in the Claudine Cartan groups in France in next month. So just 15 days she is with us, and she has done all the calculations, the first work and also the second work. And with that, I would also like to thank my collaborators. Maybe all of them are not involved into this particular work, but in other works also they are heavily contributing. And I would also like to thank the funding agency for their generous support. And thanks for your kind attention. And these are the details of my contact. So in this online meeting, we do not have much scope to interact. So you feel free to write me whenever, if you have any questions or comments, or if you have, especially if you're experimental, if you try to understand this type of system, if you would like to collaborate, feel free to write to us. Thanks for your kind attention.
Thanks, Ashok, for a very interesting talk. So do we have questions from the audience? Okay, so while we wait for questions from the audience, I have a couple of questions. So, so the calculations that you showed used G0 W0 approximation, right? And
yes.
They had a lot of effect on the quasi-particle energy, right? So is there any, like, do you see any need to go beyond G0 W0?
Of course, yes. I mean, first of all, there are two things. I mean, one is that if your starting point is good enough, for example, if I open that slide, so here you see that this G0 W0 is very much dependent on your starting point.
Right.
So if your starting point is a crap, so then even if you keep on doing the corrections here, it will not going to give you the correct results. So here, particularly in our system, you see here the starting point is reasonable with respect to HSE06, but it is not still very good. So what happens that once you do GW on top of HSE, you overestimate. So then to counter the overestimate, you need to do the BSc. For example, if you see here in the previous here we have given the clear comparison of the whole thing. So this one is your HSE06. So that's what it is. You sort of overestimate it with GW, that is your G0 W0, of course, and then you underestimate it using BSc. So you need to add BSc, otherwise there is no option. And more importantly, you see that this sharp peak, which is usually the excitonic peak, which is also absent in G naught, W naught, and or in HSCO6. I mean, it's not that prominent. So this excitonic effect should also be captured very well from this type of interactions.
Okay. And one quick question is, in your first couple of slides, you showed about this genetic algorithm for predicting, or maybe I misread it. So
yeah.
To predict the phase. So there are lots of materials which are not stable at 0 Kelvin, but become stable at room temperature, right? Like lanthanum nitride is something I can immediately think of. So
correct.
Can that algorithm predict these stable phases without doing any thermodynamic integration?
The structures will be there, of course, in the pool. But the point is that since they are not thermodynamically stable, so we really need to do thermodynamics then to see that, okay, what is the contribution of the configurational entropy, and then we add it up and then we say that, okay, these are the most stable one.
Okay, so you need a more rigorous calculation later on to determine
exactly.
which one is stable.
I mean, it would have been the best if we could do the free energy kind of genetic algorithm. So that would include everything, but that is very costly. I mean, because iterating and then calculating vibration and redoing this thing, it is much easier that you do the genetic algorithm with a little bit crude way, and then you get all the possible structures, and then you separately do the thermodynamics on top of that. That is, I mean, computationally, it is much easier. I mean, to save CPU hours.
Okay. Okay. Thanks. Do you have any other questions, or? Okay, so if not, thanks Ashwath for a very interesting talk. So we'll move on to the next speaker. Can you unshare your screen? Okay, so Kuljit, do you want to share your screen now?
Yes. Hello, is it visible?
Yeah, it's visible. Okay, so the next speaker is Kuljit Kaur from IIT Bombay, and she'll be talking about absence of spin boson quantum phase transitions in transmon qubits.
Yes, thank you for the introduction. So first of all, I would like to thank the organizer for the opportunity to present our work. So this work is about the quantum phase transition in a transmon qubit, which we recently put on our archive. So I would like to start with this figure here, so which we all are very familiar. So this is a quadratic potential, and we know that how to handle such potential and what type of information it can give us. Now let's think that instead of x square, I have a cos x potential, and now it becomes challenging to solve the equation. And what type of physics it can give me. So on the top of that, I also like to add the complexity of the system, and I'm considering that system is not isolated anymore. And now the question is that how do we deal with this such a system, and what type of physics we can see in this system. So I will answer this question throughout my talk. So this cosec potential is not here the arbitrary choice as I am taking. So there are a few examples where we are facing such terms. So first of all, I would like to give an example of a Kane-Fisher model where we have where we studied the transport through the Luttinger liquid with the weak length. So this Hamiltonian is a well-known Hamiltonian for a Luttinger liquid, and G is a parameter which decides the type of interaction we have. So on adding the weak link in this Hamiltonian, we get effective action, which they showed like this. And this effective action is a contains a cost term, which is actually give the interesting information about the hopping throughout the weak link. So with this, they solved it by RG procedures, and they got this physics about the transport through the Luttinger liquid. They got that in a repulsive interaction limit, the system is a perfectly reflective, and in the attractive interaction limit, the system is perfectly transmitted. So this is what we get when we encounter this type of potential as an effective term in the Hamiltonian. But this is not always the case. So there could be the system where this cost term is present itself in a Hamiltonian. So such Hamiltonian is a Josephson junction Hamiltonian, and Josephson junction is a superconductor insulator superconductor junction. And the Hamiltonian is, I'm showing here, where EC is the charging energy and EJ is the Josephson energy for the system. So this Ng here is the bias voltage to the Josephson junction. So this cos phi potential here makes this Josephson junction a nonlinear element, and therefore it becomes a suitable candidate to use as a qubit because of the nonlinearity. So this, however, their nonlinearity can be studied within two different limits here. So here I am plotting the energy spectrum of this Hamiltonian and for the two different regimes of the charging energy and Josephson energy. So firstly, when we have a Josephson energy which is less than charging energy, this regime is a strongly nonlinear limit. So this regime is called Cooper pair box limit, or it is a spin boson limit because effective system is behave like a two-level system. However, there is another limit when we have a system which is where we have a Josephson energy is much greater than charging energy, and the system becomes more harmonic. So this limit is called a transmon limit. And we can see from this figure that in this limit, the system becomes independent of this charge noise. So energy is less dispersed in this system. So therefore, this system is much more stable for doing the experiment, as the NG variation doesn't affect the nonlinearity of the system. With this, therefore, people are using superconductor junction in this limit, which is a transmon limit in various experiments. And on the top of that, if we know that this is a qubit, therefore there is presence of dissipation, and dissipation can be, we can probe by using a path. And such an experiment is given by recently by Xavier et al., where they have a Josephson junction, which is actually in a transmon limit, which is shown here in a red color, and it is connected to the linear elements. Okay, and the Hamiltonian corresponding to such a system is written here in equation 3. So such a Hamiltonian, we can quantize it by quantizing the operator, which here is the charge operator, and the second one is the phase operator. We can quantize the Hamiltonian and we can map this system to a system which is like our spin bath systems, which is I'm showing here in equation 4. So first term here is the Josephson energy, which act as an level qubit. Second is H bath, which is a harmonic oscillator term and define the K modes. And the third part represent the interaction between the system and the environment. The system and the environment strength is given by alpha, where J omega is represent the spectral density function for the bath modes. So here this system is like a spin boson model, and instead of a two-level system, now we have a level system, and we can call it a transmon boson model actually. Okay. So now the challenge is that how to deal with such Hamiltonian and how to solve and what kind of physics it can give us. Okay. So we have implement a variational theory on this system, and we use the self-consistent harmonic approximation for the Hamiltonian. So here I'm just showing the schematic diagram that how the procedure is done. So here I'm considering a very simple potential, which is a cos phi potential, and we can go to by taking a harmonic approximation limit to the to this Hamiltonian, which is a diagonal Hamiltonian. Okay, and we know all about this Hamiltonian. We can write the solution of the system. Now, since the initial Hamiltonian is a periodic Hamiltonian, we would want that so therefore the wave function or the answers would also like that there should be some periodic nature. So therefore, we bring back the periodicity by introducing this phase slips on the operator, which is 2 pi w. So here w is an integer value. So this is now the answers that we use for the variational calculation. So since we change the wave function from the initial to the new which is a periodic one, therefore it cost us some changes in the Hamiltonian as well, and therefore we need to renormalize the parameter. So therefore we renormalize here the EJ star parameter And with this, we can get the energy by implementing this gravitational answers. So now this type of answers we implemented on our model, which is a full transmon boson chain, and then we now expect that it will work. So the question is that where it will work. So we already expect that it is since it is a harmonic approximation, working in a harmonic approximation limit. So there should that it should work for a system where there are weak linearities. So which is a transmon regime. Okay? And we for this we benchmark our calculation with the exact numerical minimalization group. And what we have, I'm plotting the ground state energy as a function of alpha, which is a strength measurement interaction strength parameter. So what we see is that indeed it is working when we have a weak nonlinear system, a transmon system, but it is also working quite well in a limit when we have a comparatively strong nonlinearity is there. So this is the here. So this is all about that the method that how we deal with the with this type of potential. So now I would also like to show that what type of physics that we get from such arrangement. Okay.
Kuljit, you have only a couple of minutes. So
yeah, sure. Yes, sir. So okay, so it is well studied when we have spin bosons models that in ultrasound limit there is a phase transition in the system, and it is proved by calculating the population inversion operators, which is like a sigma z operator. So here also we calculated that operator, which is a sigma, which is a charge localization operator, and which I am showing here. And this is the phase diagram for the full system that we got. So here we can see that there is some line which is shown with the dotted dots here. So this line is actually showing that there is some region which is electrostatically forbidden. So this is due to some electrostatic condition in the electronic circuit that we could not approach that limit. But within the stability limit, what type of behavior we got? So when we are in a strong nonlinear limit or a spin boson limit, then we see that there is a delocalized phase to localized phase transition. So delocalized phase is a phase where the all states are equally probable. Therefore, this charge localization operator is 0 here. And then there is a phase transition from a localized phase where now the system is locked to some states. Okay. And therefore we see some transition from one phase to another. However, if we go to the limit which are more experimentally promising, which is a transmon limit, there is a no phase transition is observed, and system will always remain in the delocalized phase. However, since this the behavior in both the cases is quite surprising, so we would like to understand it, and so we would like to understand the difference between both the limits that we can see in the fluctuations. So here I'm plotting this cos phi, which we measure of the phase fluctuation in the system with respect to the ratio as well as with the alpha. So what we are doing here, we have when we are in a weak nonlinear limit, then if we increase the alpha parameter, which is a coupling, then we see that cos phi is a decreasing with respect to alpha. So which shows that this is here in this limit, the phase fluctuations are dominant and the charge fluctuations are suppressed. Therefore, this phase is a charge localized phase. However, the other limit, which is a transmon limit, there we see that with the increase of alpha, so there is an increase in cos phi, which shows that this limit is a phase localized limit, as the phase fluctuation are suppressed due to charge localization. Okay? So we see that there is a crossover at Ej by Ec equal to 1 in this limit. Okay? And with this, localization, we can think that the system is in one limit the system is phase localized. However, in another limit it is a charge localized. Okay, with this I would conclude here that in an experimental condition, the transmon is a more promising candidate, but it doesn't show the a strong limit physics of a phase transition in the system. So at the end, I would acknowledge my collaborator, Professor Soumya Vera, Professor Serge Florine, Theo, Nicholas, Isaac, Simon, and also IRCC, IIT Bombay. Thank you for the listening.
Thanks, Kuljit, for a nice talk. So we have time for one quick question from the audience. Okay, so it looks like there's no other question. So maybe we can move on to the next speaker. We're already running short of time. So do we have Anirban Das?
Yes, sir.
Okay, can you share your screen?
Yes, sir. Sir, some problem is here. It's written host disable participant screen sharing.
Oh, okay. Is the organizer here?
Anirban.
Yes, sir.
So you're around, so I have made you a co-host. Can you try and share your screen?
Yes, sir. Now I can share.
Okay, thanks.
Sure. So the screen is visible?
Yeah,
Yes.
screen is visible. You can get started. So the next speaker we have in the session is Anirban Das from IIT Madras. So he'll talk about edge-state superconductivity in epitaxial quantum spin-Hall heterostructures of WTE2.
Good evening, everyone. So the title of my talk is Edge-State Superconductivity in Epitaxial Quantum Spin-Hall Heterostructure of WTE2. So it's a collaborative project with experimental group of Nanyang Technological University led by Professor Bent Weber. So our main motive of this work to see the induced superconductivity in the edge state of a topology of a quantum spin-Hall insulator WTE2 and to find the Majorana fermions if or any kind of bound state in the system. So the main motive of our work starts from the theoretical model that provided by Fu and Kane, which said that topological superconductivity can be induced in a quantum spin-Hall insulator if a topological insulator, when it brought into tunneling contact with an ordinary SF superconductor. So to model our system, we have chosen SF superconductor, which is a 2H NBAC2 with the critical temperature of 7.4 Kelvin, and the quantum spin-Hall insulator, which is 1T prime of WTE2. So here in the left figure, we can see the formation of this heterostructure. The blue surface is the NBAC2 surface, and over which the yellow islands are the 1T prime WTE2 islands, which are grown epitaxially. Now the unit cell of this WTE2 is shown here, right hand side. So the unit cell of one WTE2 contains basically four type of atoms, where are those blue atoms are the tungsten atoms and the white ones are the tellurium atoms. And this WTE2 is contains the Rajbhai spin-orbit coupling, because of which it has a spin-Hall gap of 56 MeV. This is the band structure of WTE2, where we can see without the spin-orbit coupling, that is the red line shows there is no spin-Hall gap, but with spin-orbit coupling there is opening of clear-cut spin-Hall gap of 56 MeV, which shows here. So now in our theoretical study, we have used realistic Hamiltonian of the entire system, which contains the normal state Hamiltonian of NBAC2 and the normal state Hamiltonian of WTE2 plus the interaction Hamiltonian and the superconducting Hamiltonian of NBAC2. And the delta S and delta P shows the superconducting gap of S wave and P wave type of superconducting order parameter, which is written in terms of electron creation and annihilation operator. And we have used Bogoliubov-Dijon's formalism, where we transform this C operators, that is the C basis, into the UV basis to calculate the various parameters like delta S, delta P, or the local density of state of this heterostructure. So here's a picture of our model that we have chosen. So here we can see that the blue and green dots are basically the NBAC2 lattice system, where it is infinite in both direction, that is x direction and y direction, over which the orange and sky color dots represents the WTE2 WTE2 lattice. And here we can see it is basically edge terminated in the both sides, and this is the edge of this system. So we have first used this Bogoliubov Dijon's formalism to study the normal state LDOS. And here in this picture, in the bottom of this picture, we can see the normal state LDOS of the edge and the bulk of this heterostructure. So we have chosen, for example, 2 points. One, the blue line represents a edge point of WTE2, and the red line represents here a bulk point of WTE2. So here we can even see the upper picture is basically from the STM analysis we have got from the STM analysis from our experimental group, and we can see a good agreement at the higher energy state, at higher energy with these experimental results. And even we can see the spin Hall gap here in our theoretical model, although it is quite a bit high due to the effect of NBAC2. And next, we have studied uh, uh, superconductivity in this heterostructure, where in this top figure we can see the superconducting gap in NBAC2. This vertical bar basically shows the edge in this heterostructure, where the right hand side, this is the effect of WTU. This is because of the inverse proximity effect. We can see this superconducting gap is different in the various NBAC2 atoms. And in this figure, we can see the inside WT2, the induced superconducting gap, which we have found the maximum superconducting gap has been induced in the top tellurium of this WT2 unit cell, which is about 0.6 MeV. And the local density of state that we have calculated for this top tellurium, where we can see this 0.6 MeV induced superconducting gap, and even the NBAC superconducting gap of NBAC2, which we have chosen about 1 MeV, which is also seen here. And this is the experimental STM result, where we can see that which agrees with our theoretical model very well. After that, we have studied this heterostructure under the electric field. So first we have seen first we have studied that in this electrical field region, that is about minus 0.114 volt per angstrom to 0.11 volt per angstrom, in this electric field region, which is applied perpendicular to the system, the pristine WTE2 remains in the topological region. So we have varied this electric field for this heterostructure, where we have found with this predominant S-wave gap, there is a triplet superconducting gap in this heterostructure, which is confined at the edges only. It's in the left edge and right edge. And this triplet superconducting gap has a phase has this phase in the both edges 180-degree reversal. So basically, this is a non-trivial triplet superconducting gap. And according to Fu and Kane, and one more thing is that when we change this electric field from minus 1.114 volt per angstrom to plus 114 volt per angstrom, we have found that at a voltage of about at an electric field which is about 0.04 volt per angstrom, the maximum amount of triplet gap induced. So the reason behind it lies, according to Fu and Kane in their model, that when the surface band crosses the Fermi level, and if it is if it has a Dirac-like spectra, that is a linear relationship, then the maximum superconducting gap of triplet type of superconducting gap is induced. So, and this creates the base to find the Majorana fermion or this kind of bound states in the system. So in summary, we report the proximity induced superconductivity within the helical edge of quantum spin Hall insulator 1T prime WTE2, and we have found it has a large varying amplitude, which is about 0.6 MeV within the WTE2 bulk. And this mean field theoretical calculation confirms the magnitude of magnitude and the symmetry of superconducting pairing being predominantly S wave, and predict a P wave component whose magnitude can be controlled by the application of the particular perpendicular electric field. And such electrostatic control of topological edge-state superconductivity may have implications towards the quantum spin Hall-based topological quantum computing, in which all electrical control of Majorana bound states could potentially be realized. And these are some references that I have used for my work. Thank you.
Thanks, everyone, for a very interesting talk. So we have a couple of minutes for one quick question from the audience.
Yes, sir.
Okay, so maybe I'll ask a quick question. So is there any other material combination that you can think of where you can see similar effects?
There were some other materials. Currently, I can't remember. Probably some material with CD, like cadmium heterostructure.
Okay.
So currently, I can't remember actually.
I guess the question is, what motivated you to like choose these two materials?
These two materials, mainly the reason is the 1T prime WT is a good quantum spin Hall insulator, and which has a quite a large gap, that is 56 MeV, to control with the electric field.
Okay. All right. So thanks, everyone. So we'll go to the next speaker. The last speaker for the day, Animesh, are you around?
Yeah. So I should share my screen.
Can you share your screen? Okay, so we'll get started. So the next speaker and the last speaker for the day is Animesh Panda from IISc, and he's going to talk about entanglement in non-equilibrium steady states and many-body localization breakdown in a current-driven system.
Okay. So so let me start by thanking the organizers for giving me the opportunity. So you can see the title, and I will straight away go to the project that we did. So what we know and what we seek to know. So basically, if you see this system where these ups and downs basically represent on-site disorder, and these arrows represent hopping between sites, then what you get is Anderson localization. So basically,
Animesh,
above some,
you're not able to see your title. Can you?
Yeah.
Some header is hiding it. Okay. Maybe you can continue. It's fine.
This is the first slide. Is fine.
No, I meant the slide title, slide header is not visible. Something is hiding.
Okay.
But it is fine. Continue. Yeah. Sorry.
Okay. So I am. So it's here. The title. Maybe. Okay. It should come. Okay. So what I was saying is that if I take a system like this, where you have on-site disorder and you put some hopping, then what you get is called this Anderson localization above some critical disorder, and below that critical disorder you get these extended states. And if you put interaction on top of that in the same system, then what you will get is a phase diagram which looks like this. So basically, in this axis, I am plotting the energy density, meaning here is my energy minimum and here is my energy maximum. And in this axis, I'm increasing the disorder. So so for very high disorder, you get the states which are called many body localized, and then for low disorder, you get states which are called ergodic. And then you have in the middle, you have some states in which you get for a given disorder, you can get ergodic and MBL states. So what we want to study, is a system which looks like this. The same system which is disorders, hopping, and interaction. On top of that, we want to drive some sort of current through that system, and we want to ask these following questions: that what happens to the entanglement properties of this driven system in a non-equilibrium steady state, and these non-equilibrium steady states that we will find, whether you can characterize them by their entanglement properties. And given the system has many body localization at higher disorder, so can that many body localization break down under some current drive? So with these questions in mind, we proceed. So first, let me define this thing, entanglement entropy, which others also have already defined. So I can just quickly go through it. So if I take a system like this, the whole system divided into two subsystems, A and B, then for a pure state psi, if I want to calculate the entanglement entropy of that state, so this is so this is the entanglement of entropy of this state psi for the subsystem A. Then this is defined as this minus trace of rho ln rho ln rho a, and this density matrix of reduced density matrix of A rho a is defined as tracing over the B subsystem on that pure state that we had initially. And what is known is that in this interacting disorder system, below some critical disorder, you will get these states called delocalized states, which show basically volume law entanglement. And above that critical disorder, you get these many-body localized states, which show area long entanglement. So I already told you the question, and what can we do? How can we approach this system? So there are ways that people have already suggested. So you can start with some Floquet Hamiltonian or some Lindblad like formalism or some boundary dependent circuits. But here, what we do is we start with a non-Hermitian toy model for two reasons. So first is in this way we can get a non-equilibrium steady state. We can get a non-equilibrium steady states of which we can calculate the entanglement properties easily. Obviously, since I have a proper Hamiltonian to start with, the calculations are also will be easier. So so we start with this non-Hermitian toy model, which basically looks like this. This first part is with so we take this size 0 for the normal case when we have some hopping T, and then you have some on-site disorder, and you have some interaction P, nearest neighbor interaction P. And on top of that, if I put this term C to the power psi, where psi is real, then what it does is it favors hopping towards one direction more in comparison to the hopping towards the other direction. It makes the system non-Hermitian, but you can see that why I'm saying that the system is under some sort of drive, because the hopping towards one direction is more favorable. And this Hamiltonian, just by doing a Jordan-Uyghur transformation, we can write it in this form given here, where this SIs are basically spin operators for two spins. So if you have a spin with 2 degrees of freedom, then these are SIs are basically those spin operators. And SI plus, SI minus, SIZ have usual meaning. And this J is basically the current in the current for this system. Okay, so we start with this model, which I'm basically restating here. And here, this my non-Hermitian Hamiltonian can be written in this form, where both HH and this J are Hermitian. And what happens if I take this JZ equal to 0, meaning if I take interaction is equal to 0. So what people have already studied, this Hatton and Nelson, these people they have studied, is that if for this non-interacting model, if I take JZ equal to 0, this system becomes non-interacting. For this non-interacting model, if I plot the imaginary part of the complex eigenvalues and the real part of complex eigenvalues, this looks something like this. You have some clear, you can say, mobility edge. And the mobility edge term is also not ill-defined here, because what you actually get is that if you calculate the current expectation value of those states, these states, then what you get is that exactly where your imaginary part of complex eigenvalues goes to 0, you get your current going to 0 as well. Okay, so this is the result that people get for non-interacting version of my model. And basically what I want to say is that if you have complex eigenvalues, then people are getting finite current, otherwise they get 0 current. This is my system that I wanted to study, and what we have made is that we have changed this system to something like this, where you have your sites sitting on a ring, and you are putting some imaginary flux through that system. And if I want to write this system, this is exactly how it will look like. And yeah, people have earlier studied non-Hermitian models to explain the breakdown of Mott insulator, and this paper that I also said, some non-hermiticity induced delocalization, meaning if you have complex eigenvalues, you are getting finite current. So these people, they have studied on different non-Hermitian models. So yeah, it gives us some confidence that we might be in the right direction. Yeah. So what are my results? So I calculate 3 different quantities here. So first I calculate my current, and I try to get an system size dependence of entanglement entropy with change in disorder. And this phi term is basically the fraction of the complex eigenvalues in the system. So these are the 3 things that I use to get the phase diagram of this model that I have. So this is psi equal to 0, psi is my non-hermiticity strength. And for psi equal to 0, what I get is the usual Hermitian case. So you can use this entanglement entropy to distinguish between your thermal and localized states, which I am just doing here. But for finite size, these things also come into picture, this current and fraction of complex eigenvalues. And from those two, you get 2 different phase boundaries. So this first one is from current, this middle one is from entanglement entropy, and for this final one is from fraction of complex eigenvalues. And what is interesting is that these boundaries, unlike the non-interacting model, these are all different. You remember in the non-interacting case, what you had is that this transition from thermal to local states collapsed on top of this thing, right? Current being finite and fraction of complex eigenvalues. But here basically we have 3 different critical disorders at which different phase transitions happen. And yeah, so this result basically is different from non-interacting model. And dynamics also we can do on this system. So if you have a system with complex with non-Hermitian Hamiltonian H, then the density matrix of this system can be written in this form. And to write this density matrix, all I'm using is that the system evolves under this non-Hermitian Hamiltonian. So this is not that difficult to show. Anyway, so with once I have the equation for the dynamics, equation to govern the dynamics of the system, what I can do is calculate time dependent things. And one of the things that I'm showing you here is this Snell order parameter, which is defined in this form. So basically what it tells you is that so if you have spin balance, so remember my system is 1D system with spins sitting at each side, and each spin has only 2 degrees of freedom. And this term, what it can do is basically quantify the spin imbalance of the system. Yeah, so if I start with a state which looks like this, which is basically called this Snell state, then the Snell order parameter for that particular state will be exactly 1. It is defined in that way. So yeah, so so now again this size are so what I'm doing here is basically I'm calculating this Snell order parameter for this state as a function of time. And this size are defined in such that this psi 1 is less than psi 2 is less than psi 3. In fact, this psi 1 is actually 0, the Hermitian case. And these three things are for basically different disorders. So this one is for the lowest disorder, this one is for moderate disorder, this was for the highest disorder that I'm considering. And I have basically this whole plot. And in between each of in between also here there are 4 different lines which are for different system sizes. You can ignore that here. Anyways, so if I do a time evolution of this state and try to calculate this Snell order parameter, what I'm getting is it starts from some 1, and this is for the Hermitian case. You get some local memory doesn't get lost for large disorder, meaning if you have higher disorder in the system, you have this many body localized states which even at long time preserve the local memory. So that is already known. But for the what happens for these non-Hermitian cases, this Psi2 and Psi3, is that you have this long plateau where you have your for a relatively long time. You can see that time is pretty large here. Relatively long time in comparison to your energy scale of the system. Your local memory is not getting lost, but eventually at the end, your system goes to some non-equilibrium steady state, saturates. But in the intermediate state, your system is not forgetting about its initial thing. And for very high non-hermeticity, you are bringing in, you can say, more and more delocalization. That's why your local memory is getting lost. But even here, still you get your intermediate time range where local memory is not getting lost. So this is
almost out of time.
Yeah, so I will take one more minute.
Sure.
Yeah. So this is the local memory remains for intermediate time range, and for a long time your local memory gets lost, and non-equilibrium steady state is raised. And this is the final summary. So you start with this complex eigenvalue, non-Hermitian Hamiltonian, and this is the system that we want to study, and this is the system that we finally end up studying. And this is the kind of phase diagram that we get, and the summary, the conclusions that we reach are this: non-hermeticity brings in qualitative difference between interacting and non-interacting models, and we are able to calculate the entanglement properties of the non-equilibrium steady state. We find non-Hermitian MBL, which is interesting in itself, and the evolution of a state shows a long plateau in time during which the initial memory is retained, but eventually the system goes to non-equilibrium steady state. Okay, thank you.
Thanks, Anmesh. So we have time for one quick question. From the audience. Okay, if not, let's thank all of the speakers of this session and also today's speakers. And maybe I can request the organizers to say a few words.
So thank you, Navneet, for chairing the session, and thanks all the speakers for very nice talks. So we will resume tomorrow at 9:15 and with the session chair Amit Ghoshal. So I request the session chair and the speakers to come in around 9 to test things. So today, thank you everybody. So I'll end the meeting for now.